Greetings and thank you for watching the Linux System Administration live lessons. My name is Ben Whaley and I'm a professional Linux system administrator. I use Linux to power the cloud-based web systems for Anki, a consumer robotics and artificial intelligence company based in San Francisco. I'm the co-author of the Unix and Linux System Administration Handbook from which the contents of these video lessons are based. When I started administering Linux systems for a small computer services company in 1999, the world was only beginning to understand the deep impact that the internet would have on our daily lives. I was mesmerized by the dynamism of the consumer internet experience, and yet even more fascinated by its flexible and powerful underpinnings. Linux provided the perfect conduit for me as a tool to learn operating systems, networking, and the internet. System administration is a respected discipline needed at organizations of all shapes and sizes. In a small business, the administrator may run only a few Linux servers that coordinate the internal network. At an internet technology company, Linux is often the critical infrastructure on which the business and its products or services are built. At a hospital, Linux might run medical and clinical software, administrative systems, and research labs. In all cases, the administrator is responsible for keeping the systems running smoothly and for meeting the business's technology objectives. Administrators should be communicative, curious, and diligent. Organizations depend on administrators to be the steward of its systems, and as such, administrators should freely discuss concerns and desires about the system's environment, opportunities for improvement, and mistakes made. New tools and technologies should be carefully explored and embraced when appropriate. Administrator diligence may be the difference between a company that values the security of its customers' data and one that exposes it. The line between software development and system administration is increasingly blurry, particularly with the prevalence of programmable cloud systems. Repetitive tasks on computers, such as installing operating systems and configuring software, are nearly always avoidable through automation. Administrators shouldn't be afraid of learning how to write software to automate these manual tasks. I prefer to learn the configuration of an unfamiliar software package by first installing it manually, and then use code to automate the installation for future use. The saying in the industry is, automate or be automated. In this video series, we'll explore the fundamentals of maintaining and administering modern Linux systems. Lessons will be a mix of conceptual content followed by examples and command line demonstrations. Most of the examples are based on the CentOS distribution, a Red Hat Linux derivative used by many businesses. Each lesson will use the teachings of previous lessons to demonstrate the power and utility of the command line. I encourage you to use the Unix and Linux System Administration Handbook as a text reference to this video and to rewind and rewatch any sections that move quickly. You'll notice that I make extensive use of shell shortcuts and tricks throughout the video. Learning these techniques will impress your friends and colleagues and improve your efficiency on the command line. This live lesson comprises 9 lessons on Linux system administration. In Lesson 1, we'll get started by understanding the basic duties of a system administrator. I'll introduce 2 tools, Vagrant and VirtualBox, that you can use to experiment with Linux. I'll also point you to additional documentation and resources for learning Linux. In the second lesson, we'll discuss the Linux shell. We'll learn how a Linux system is organized and how to use the shell to navigate the system. We'll also touch on scripting languages that can be used to automate common administrative tasks. Lesson 3 is about the startup and shutdown procedures of a Linux system. We'll cover the material at a conceptual level before we dive into the details of the Linux initialization process. In Lesson 4, we'll learn about controlling access to the system. The administrator is the go-to person for controlling who has access to what, so understanding this material will be useful. We'll cover what happens when users log into the system and how their access is controlled. In Lesson 5, I'll discuss processes, which are the running programs on the system. The Linux kernel controls the execution of programs, but the administrator influences processes through signals and kernel configuration. We'll learn how to use strace and the /proc file system to fully understand the internals of a process. In Linux, the motto is, everything is a file. In Lesson 6, we'll explore the Linux file hierarchy. We'll discuss the various types of files and their attributes, as well as controlling access to files using permissions and access control lists. Lesson 7 focuses on log files, which are the first source of information that an administrator should turn to when diagnosing a problem. We'll discuss where log files are kept and how they're collected. In Lesson 8, I'll demonstrate how to configure a Linux system for the network. We'll review both current and deprecated tools since they're both in common use. We'll also discuss how to configure DNS, the domain name service, and how to troubleshoot network problems. You should understand the basics of TCP/IP networking before viewing this lesson. Lesson 9 is about security on Linux systems. We'll discuss some of the steps an administrator should take to secure a freshly installed Linux system. We'll explore some tools for managing Linux system security, such as the Secure Shell and the iptables Linux firewall. By the end of this video series, you'll be equipped to begin administering Linux systems yourself. I hope you enjoy the videos as much as I've enjoyed putting them together. Welcome to Lesson 1, Where to Start. In this lesson, I introduce the role and duties of a Linux system administrator in a professional context. I tell you what knowledge might be useful to you before watching this video series. After briefly covering the history of Linux for context, I introduce you to Vagrant and VirtualBox, which you can use to set up a Linux lab environment for practice and testing. Finally, I point you to additional sources of documentation and information about Linux, and I discuss Linux tools that help you install software. Welcome to Lesson 1.1, Understand the Duties of a System Administrator. In this first lesson, we're going to understand exactly what a system administrator functions in an organization. We're also going to understand where a system administrator fits in the greater ecosystem of an IT organization. One of the first responsibilities of a system administrator is provisioning new user accounts. Those accounts might exist on a Linux system itself or on applications that run within a Linux system. What I have on the screen here is an example of a command. You'll notice a hash mark or a pound sign on the first two lines of the command. This simply indicates that it's a comment. The next line shows a $sign, indicating that this is a shell command that you can run in the terminal. In this example command, we're adding a new user. This user's name is bwhaley, and the user ID is 1001. The user has a home directory of /home/bwhaley and a shell of /bin/bash. This is the type of command that you might use when provisioning a new account. Another responsibility of a system administrator is adding and removing hardware from the system. This might be new disks, storage devices, network devices, or other peripherals attached to a Linux system. This example command shows the partition table for any disk attached to the system. Sudo fdisk-l is how you might pronounce this particular command. Performing backups is a critical responsibility of a system administrator. In the event that data is lost due to some catastrophic failure, such as crash of a hard disk or a data center flood or a similar disaster, backups and restores are an essential function. Here's an example command of creating a compressed archive backup of a specific path on disk. This is a very common way to compress and archive a large amount of files on the file system using tar. Installing and upgrading software is another common task of system administration. You'll need to release new packages, update the system for security vulnerabilities, or install new software as requested by users. This example command, which we'll learn more about, updates all of the packages on a Red Hat type of Linux system. One responsibility you'll have is to monitor the system to ensure that it's performing and at an acceptable level for users. Top is one command used to monitor the system. It shows CPU statistics, memory usage, and how processors are using the system. Monitoring is a deep and complex, involved task and often involves many systems collaborating in order to collect data. Troubleshooting problems is a common task that you'll find in day-to-day administration. You'll use various network utilities and system utilities to identify bottlenecks in the system and problems that might occur as you are going about your daily system administration duties. The example command I've chosen for the troubleshooting step is tcpdump. tcpdump is packet capture software used to capture network statistics. In this particular command, we're showing all TCP packets on the HTTP web port, which is commonly used as port 80, and also showing UDP packets on port 53, which is used for DNS traffic. As a system administrator, you'll need to maintain site documentation in order to educate other people on your team and throughout the organization about how you've set up the system. The documentation might take the form of wiki pages, of Word or Google documents, web pages, or whatever your team agrees is the best way to keep system stakeholders and yourself informed about how the system operates. Remember, just because you set something up once doesn't mean you'll remember exactly how that was done 3 months down the road. You might need a reminder just for yourself. Maintaining site security is of absolute paramount importance. One security compromise can damage the reputation of a business permanently. A system administrator is in a key position to ensure that the data is kept confidential, is kept with high integrity, and is kept available and up for users to use at all times. There are many tools and entire professions dedicated to keeping security intact. This is one example Linux command of doing what's known as a port scan on the network. In this particular example, we're port scanning the example where the system www.example.com resides. All of the /24 network of this host will be scanned. We're also going to try to guess what the operating system is of the remote system. This is a common way to determine what your exposure is on the network and how an attacker might leverage the network to gain a foothold. And of course, the daily site operational duties will consume a lot of your time as a system administrator. You'll field requests from incoming users, need to firefight problems, and use all of the tactics in the previous slide to understand exactly how your site is being operated. You'll have to communicate with many interested parties around the organization and ensure that you're meeting the organization's goals. As a system administrator, you'll interface with lots of other people on your team. Here's a few of the types of people that you'll be working with in your day-to-day system administration duties. One is administrators of other operating systems. This might be Windows administrators, or Unix administrators, or Mac administrators. You'll also be interfacing with network administrators. A network administrator's duty is to ensure that the network is configured correctly for systems to run on. They're the people that manage routers, switches, and connections to internet service providers. You'll be working with DBAs, also known as database administrators. These individuals maintain the persistent stores on the network, things like Oracle databases, or MySQL or Postgres, or other persistent data stores. Application developers are a key stakeholder for your system. They are the people that write the code that run the sites running on the Linux system. You'll definitely interface with site reliability and NOC engineers. These individuals have a primary focus of keeping the site up and available at all times. They often sit in a dedicated room with monitors mounted on the wall and watch the monitors for any delays or problems in the site operation. You'll work with and interface with security ops, also known as SecOps. These people use security tools to maintain and ensure the security of the data on the network. You'll need to work with these individuals to install new tools and to make sure that the tools are meeting their needs. You'll interface with storage administrators, whose primary goal is maintaining SAN and NAS and other remote storage devices and mass storage devices as they reside on the network. Finally, you'll also work with data center technicians. These individuals receive new hardware as it's unboxed and mounted in racks and cabled throughout the data center. Maintain a tight relationship with all of the different individuals in this slide, and you'll ensure the success of your IT organization as a whole. There's some background you should have as you start approaching the various videos in this lesson. We're going to go through some of the experience and background you should have that will prepare you for success. On the command line, you should understand a few different things about using the command line. First, you should have some familiarity with using any kind of a text terminal. This could be the terminal app on your Mac, it could be a DOS prompt on Windows, or maybe you've already used a Linux system before, in which case you've almost certainly seen a Linux command line. You should also know some really basic commands about moving around the system on the command line. This could be changing or creating new directories. Maybe you know how to download files. You should just have some experience with running commands. Some basic programming logic will also help you here. You should understand conditionals, like if statements or case statements. You should understand loops, such as for loops and while loops. You should understand variables and how to assign them. It doesn't really matter what language you know, as long as you have some familiarity with how programming languages work. You should conceptually understand some things about operating system. You should understand what a kernel is and what its role is in managing CPU, memory, and input-output devices. You should know that the kernel is responsible for handling device drivers as the interface between the user and the hardware. You should understand that the kernel has a scheduler that allows processes to have a certain amount of CPU time. You should understand that the kernel also assigns memory to processes as they start up and stop on the system. You should know that the kernel mounts and unmounts and manages file systems, which are on devices attached to computers. You should know that the kernel manages the network stack. It is responsible for communicating with the network and is your interface to other systems. Linux is a monolithic kernel. The definition of a monolithic kernel is one single program that contains all of the code necessary to perform every kernel-related task. Now, strictly speaking, very few operating systems are entirely monolithic. Usually things are broken up a little bit. But as a whole, Linux is certainly considered a monolithic kernel. If these concepts don't make sense to you, make sure you go back and learn about kernel and operating system basics. You should have some background in TCP/IP networking. You should know what protocols are part of the IP protocol suite, such as IP, TCP, UDP, and ICMP. You should understand some terms associated with those protocols. You should understand what dotted quad notation is. When you read an IP address such as 10.0.0.1, you should know what that means. You should understand the CIDR network notation format. You might also need to know what a subnet is and what a route is and how that is important on a Linux system. You should understand at a high level what the purpose of DNS is. Now, DNS is a really complex system and you don't need to understand all of the ins and outs of it, but you should understand some basics such as what a hostname is, what a DNS record is, what a DNS server's purpose is, and what a reverse DNS lookup is. So if you don't understand some things about TCP/IP networking, read an introduction on TCP because it will be useful throughout this series. In this section, we're going to explain what the history of Linux has been and how we got to where we are today. It's nice to have some background on the operating system so you understand some of the quirks and eccentricities of how it works. We're using this Prezi presentation as a format to show this in its geographical context. The story begins in Finland, in Helsinki in particular. In 1991, Linus Torvalds, a student at the University of Helsinki, started tinkering with an IBM x86 compatible computer. He had just started using the Minix operating system, which is a microkernel and is meant for educational purposes, but is not open in nature. Linus wanted something that he could tinker with and use himself, so he started building his own kernel and his own operating system. Eventually, it got mature enough to where he decided to announce it, and he put it up on a Usenet post. In his initial post, he claimed that Linux would never be big and professional like GNU Herd, which was sort of a competing operating system that eventually turned out to be vaporware and never quite came to life. In any case, lots of volunteers and community contributors around the world quickly started adapting and adding features to Linux. That's where it got its start and started to take off. Fast forward a couple of years to 1993 at Minnesota State University in Moorhead. Patrick Volkerding developed and released Slackware, which is one of the first Linux distributions. A Linux distribution is a package of software that makes an operating system. Linux itself is just a kernel, just the core of the system that manages the hardware and the scheduling and the things that we talked about in one of the last sections. But there's a lot more than just that to make an operating system work. You need a shell to manage commands. You need software to run on that system. You need things to edit text files. In general, there's lots of software that needs to be working in coordination in order for an operating system to work. And in Linux, an entire operating system is pulled together into what's called a distribution. Patrick Volkerding wrote Slackware, which is one of the first and most long-lived distributions. It's still managed and maintained today. Fast forward to North Carolina in 1995. By now, Linux is starting to make inroads with tech enthusiasts, although it's not yet really popular among businesses and enterprises. The first Linux Expo was organized by Donnie Barnes at North Carolina State University. The entry fee, $4. Mark Ewing was present at this expo. He later went on to start Red Hat, which is today one of the most popular and widely used distributions in enterprises. Now we move to Silicon Valley in 1997. Linus Torvalds moved from Finland to Silicon Valley to work for Transmeta, which is a CPU manufacturer. By now, Linux version 2 is released. It contains a number of advanced features needed by networks and used by businesses. In addition, many major distributions are starting to form and gain a larger user base. Popular distributions that people use today, such as SUSE, Red Hat, and Debian Linux, are gaining momentum. Now we move to Oregon in 2003. Torvalds has now moved from Silicon Valley to join open source development labs and is paid to work on Linux full-time. Linus's role now is as a kernel maintainer. He accepts code from many other contributors around the world, merges that code into the mainline kernel, and ensures that everything is operating and building smoothly. Enterprise use of Linux is accelerating and really is widespread at this point. The desktop environment for Linux, in particular the desktops GNOME and KDE, are ubiquitous. If you are a desktop Linux user, meaning you have it installed on your desktop at home or on your laptop or even on a tablet, though those weren't popular yet by this time, you're most likely using the GNOME and KDE window-managed environments. By 2007, of course, the Linux story has already been widely told. The Open Handset Alliance, of which, of course, Google is a large contributor, unveils Android as a Linux-based operating system for mobile devices, cementing Linux's place in the embedded systems market. In addition, the One Laptop Per Child project aims to ship low-priced Linux laptops to children in developing countries. The target price for these Linux laptops is around $100, though at this point it still hasn't made it past $200. So that brings us to Linux today in 2013. Linux-based web servers today account for nearly 75% of market share. The most common Linux servers in use are Nginx, a very fast and efficient web server, and Apache HTTPD, which has been around since the 90s. Valve Software, a gaming company, released its Steam gaming platform for Linux this year. The stable version of the Linux kernel at this point is version 3.10 and supports dozens of CPU architectures. Linux is on the bleeding edge when it comes to new operating system technology and new networking support. It is also a leader for jobs. 93% of surveyed businesses are said to be hiring Linux professionals, and sysadmins are the most sought after in this space. This is according to a job report from the Linux Foundation just this year. Hopefully this section gave you some context about how Linux got to where it is today and why it's absolutely imperative to the success of the internet. In this section, we're going to start actually practicing using Linux. I want us to set up a lab environment that we can use throughout the rest of the lesson to refer to the sections that I'm about to talk about. So, to get the lab environment set up, there's a few choices we have to make. First, we need to pick a distribution to use. As we learned in the History of Linux section, there's a variety of distributions that have gained popularity. First, there's the Red Hat family, which is composed of Red Hat Enterprise Linux, Fedora, and CentOS. Red Hat Enterprise is used by many large enterprises, is paid for with support, and is often a very stable distribution choice. Fedora Linux is the free version of Red Hat, often containing more bleeding-edge software, but is not supported. CentOS is a binary-compatible exact replica of Red Hat Enterprise Linux. It is not supported, but it has all of the features of Red Hat Enterprise. Next, we move on to the Debian family. Debian, Ubuntu, and Mint Linux. These have different package managers and other slightly different standards of how the distribution is used. They're extremely popular among desktop users and even among enterprises. OpenSUSE is a European-based distribution run by Novell. Next up, there's Arch and Gentoo Linux. These are meant for power users. Arch Linux lets you customize your system to your heart's content. Gentoo Linux builds everything from scratch and it's compiled precisely for your system. To get started, I recommend the use of Ubuntu or Fedora or one of the Red Hat or Debian family Linuxes. For most of this lesson, we're going to be using CentOS as our distribution of choice. We also need to choose a terminal emulator. I'll just put it out there that I'm highly biased in favor of Mac systems for Linux administration. In particular, I like iTerm2 as my favorite Linux terminal emulator. It's highly customizable, it has all the features that I need, it has tab support and multi-window support. You should download it, and you should use it, and you should contribute if you like it. Mac also comes with the Terminal app, built into Mac OS X. It's an okay terminal emulator. I used it when I started using Macs, but I quickly switched to iTerm2 as soon as I found out about it. If you're unfortunate enough to have to use a Windows system, I recommend using PuTTY, which is widely accepted as the most common freely available terminal emulator for Windows. I find it hard to use PuTTY without some of the additional add-ons, such as Kitty and PuTTY Tray, to just make it a little more powerful. Another terminal emulator is called Terminator and has some advanced support, much like iTerm2 does. If you are up for paying for a terminal emulator, Secure CRT is an excellent choice for Windows systems supporting session management and multiple tabs. So, now that we've made some decisions about what we're going to use, we need to download and install some software to set up our lab environment. There are two pieces of software that we're going to rely on. One is VirtualBox, which is free virtual machine software from Oracle. VirtualBox lets us run a virtual Linux instance within our system, so we don't even need a connection to the internet in order to play with Linux. We're also going to be using Vagrant, which is open source software that gives us really nice, clean, simple virtual machine management. Once you start using Vagrant, you'll see the power of spinning up and stopping virtual machines at your heart's content. Find lots of boxes or virtual machine images for Vagrant at vagrantbox.es. You can see in the example command here that starting up or initializing a Vagrant box is as simple as just running a single command, vagrant init, and then you specify a box name and a URL. So let's see an example. We'll start by making a new directory to hold our Vagrant boxes. Make dir vagrant. Now I'll change to that directory with the cd command. To get started with a new virtual machine, it's as simple as initializing a new box. Vagrant init, and I'll just come up with a new box name, CentOS. And then I need to paste in the URL of a Vagrant box. I'll switch to a browser window, and I'll visit www.vagrantbox.es. There's a large variety of boxes and distributions to choose from here. And I'll just pick one of these CentOS boxes. Paste in the URL. Vagrant creates a new file called a Vagrant file. We don't need to go through every line in the Vagrant file, but we can look at some of the contents. All it really does is specify that I want to start a new box called CentOS and where to find the box if it's not already loaded. In order to start, I can just say Vagrant up. If the machine doesn't already exist, Vagrant automatically goes out to the website, begins downloading the box. We'll skip the download here. Once the download is complete, Vagrant will proceed by starting up the virtual machine in VirtualBox. You'll never even need to see a VirtualBox window as it's handled behind the scenes by Vagrant. At this point, since the operating system has finished downloading, I'm just booting up the virtual machine. It will only take a minute. Once the virtual machine is booted, it shares some files so that you have access to your Mac system as well, and it makes the Linux system available for you. Now that Vagrant up has finished running, I can run Vagrant status to show me the status of the box. In my case, I have two Vagrant images running, a CentOS box and an Ubuntu box. If I want to log in to one of my new Linux boxes, I can type vagrant ssh and then the name of the box, which I'll copy and paste. It'll be the CentOS box to start with. You can see that it's logged me into Linux and it greets me with a message. At this point, I'm on a Linux system and I am no longer running on my Mac. I can exit back to my Mac by typing Ctrl-D or exit. To halt my virtual machines, I can say vagrant halt. This will stop the virtual machines, but will not remove them from the system. It only takes a minute. Feel free to start, stop, destroy, or initialize new boxes as needed. These boxes are all temporary. You can use them for development purposes, for testing new software or features, or for whatever purpose you see fit. In order to list the boxes I've already imported, I can type vagrant box list. This shows me several boxes. I have a CentOS box, an Ubuntu Precise 64 box, which is a specific release of Ubuntu Linux, and a raring box, which is also a specific release of Ubuntu. In order to initialize one of these machines I've already imported, I can type vagrant init and then the name of a box, such as Precise 64. This creates a vagrant file just as it did in the previous example. I can now type vagrant up. It will import this box. In other words, it will make a copy of this box and import it into this directory and then boot the virtual machine. It's never been easier to get started with Linux than using VirtualBox and Vagrant. There'll be many times during your administration work and duties that you'll need to refer to documentation. Google is always your friend when it comes to using and learning about Linux. However, there are other sources that you can turn to specifically for deeper questions or if you need a quick answer. The traditional way to learn about Linux and Unix systems is through man pages. The man command formats and displays online man pages on your Linux system. It usually comes in a variety of formats. In particular, these sections are almost always present in a man page. The name displays, of course, the name of the command that you're looking up, as well as a succinct, really concise description of what it does. A synopsis is a little more detail about how the command is run, including what arguments or options are passed to alter the command's purpose. The description field goes into detail about what the command is, what its functionality is, and what it's meant to accomplish. The general options section goes into detail about all of the arguments and flags available to the command. There are often several examples presented of how to use the command and what files are associated with that command. The See Also section will refer you to similar commands, and authors is just what it sounds like. It's whoever wrote the utility. So let's look at an example man page. The Mac terminal is a Unix system, and so it has man pages available to it. However, we're going to go ahead and log into one of our Vagrant Linux boxes and take a look at the man page there. Now that the box is booted, I can type vagrant SSH in the name of the box that I want to log into. This is only necessary when you have more than one box running, such as in my environment where I have a CentOS box and an Ubuntu box. Now we can type man and the name of a man page that we'd like to look at, for instance, SSH. The top of it, this should match very closely what we saw in the slide. We have the name of our command, a synopsis of all of the options available to that command, a description of the command and its options. I page through the man page with the spacebar. We can see that SSH has lots of options. We can also see that there are some high-level sections that are command-specific. For instance, we have escape characters and TCP forwarding as being specific to the SSH command. We see the See Also section, which refers us to lots more information about SSH, and we see an authors section. This is a very typical man page, and I usually use it to quickly refer to a command syntax. It's even faster than using Google. In addition to the online man pages, there's lots of places online on the web to learn about Linux. Some of the sites I like include linuxquestions.org, which is a great forum-style communication tool. Ubuntu Forums, which is somewhat Ubuntu-specific, but has lots of generally relevant information. JustLinux.com, which, similar to Linux Question, has lots of active forum members and a thriving community of Linux users. And of course, my favorite, the go-to lwn.net, which provides detailed coverage of Linux, the open source community, the kernel development process, and is run by a really great group of active Linux developers. If you need real-time support for Linux or the software running on Linux, you can turn to IRC, and in particular the Freenode network. Freenode has been established as a common chat and communications channel for all sorts of different software, Linux included. So when you need real-time support from friendly people, log into IRC. In this lesson, we'll learn about how to find and install software on a Linux system. Now, we should keep in mind that software and packaging is a very broad topic. There are people who dedicate their entire career to making sure that software is easy to download and access and install. So our coverage here is really just to get you familiar with what's available. So first, we should understand the concept of a software repository. A repository is a collection of software packages, often for a given operating system or even for a given CPU architecture, like a 32-bit processor versus a 64-bit processor. On Linux systems, the most common packaging systems are RPM and Deb. Red Hat systems use the RPM format, and Debian systems use the Deb format. RPM packages are usually installed and managed with a program called yum. Debian packages, known as .deb files, are usually managed with a system called apt. These systems allow you to search the internet and the software repositories that host packages to install new software on your system. There's lots and lots of software available. You'll often need to use these repositories not only to install new software packages, but also to update your system in the event that there's a security vulnerability with one of the existing software packages. This is, in fact, very common. New security vulnerabilities are found in packages almost every single day. In addition to these common Linux package management repositories, there's more software available in the format of Ruby gems, Python packages, and Perl modules. There are many sources for various scripting languages that are specific to programming languages. A Ruby gem is a gem file for Ruby that includes libraries or applications written in the Ruby language. It is managed with the gem command. Python packages are usually installed and managed with a tool called pip. Pip searches Python package repositories for new Python packages. CPAN, known as the Comprehensive Perl Archive Network, is a collection of libraries and tools available for Perl. GitHub is a very popular repository for collaborative open source software development. You'll find projects large and small on GitHub. You can create your own projects on GitHub and easily share it with other developers. It's a common way to access bleeding edge or new software. SourceForge.net is more commonly used for downloading binary files. GitHub is often used for source code, while SourceForge.net contains various software that's in binary format ready to use. And of course, sometimes you might need to compile software from source. This means downloading the source code from the internet and using Linux to build that software using a compiler. We won't cover that here, but we will talk about using yum. I'm already logged into my Linux Vagrant box. I can use the yum command to search for a specific package. For example, I could use yum to search for the Linux kernel itself, using yum search Linux. This command connects out to the software repositories configured on my CentOS system and searches available packages that might contain the keyword Linux. You can see that there are a lot of hits. I can use rpm -qi kernel to show what packages that are the Linux kernel installed. I can use rpm -qa, pipe it to grep for Linux, to show all of the packages installed on my system that contain Linux in the package name. Don't worry if you don't fully understand this syntax. We'll learn more about it in a later lesson. Just know that when you need to install packages, yum and rpm on a CentOS system, or apt on a Debian system, are your most common commands. Welcome to Lesson 2, the shell. In this lesson, I cover the purpose of a Linux shell before going right into demonstrations and examples of using the shell. You learn what a regular expression is and how it's useful as an administrator. I introduced Vim, which is a powerful and versatile text editor that you can use to edit files and write code. I go over a basic shell script so you can see the utility of automation. I also provide pointers to powerful, full-featured programming languages used frequently by administrators. One of the best places to start learning Linux is by learning the shell. Learning the shell in detail will help you become a more efficient and effective system administrator, so it's important to spend a lot of time on this concept. So, what is the shell? The shell is an interpreter. It takes commands from the user and executes them on the system on the user's behalf. Importantly, the terminal is not the same as the shell. Your terminal, like we talked about before, being perhaps iterm or secure CRT or PuTTY, depending on which system you use, is just a window to the shell system. The shell is an executable that interfaces directly with Linux. It is a command line interface, unlike a graphical interface or a graphical user interface, a GUI, that you might be familiar with on Windows or Mac. It has a long and sordid history, with various shells being claimed as the best shell or the worst shell, depending on who you ask. The SH, or the Bourne shell, is a very common and basic shell written at AT&T, and then there's a competing shell known as CSH, written at UC Berkeley, originally for Unix. Today, the usual default on a Linux system is Bash. Bash is highly powerful and is shipped as the default on nearly every Linux distribution. In addition to Bash, there's a very committed fan base among power users for the shell ZSH. It's backward compatible with Bash, but it extends it and adds additional features. Some eccentric types of sysadministrators might use TCSH, or some administrators with an IBM AIX Unix background might be used to the Korn shell KSH. Any of these shells will help you accomplish your system administration duties, but for convenience, I recommend sticking with Bash, the Born Again shell. That's what we'll spend all of our time in this lesson covering. It's super important to understand the shell. The shell is your window to the system. Most of your administrative time on a Linux system is spent on the terminal typing shell commands. It's also useful in the form of automation through scripts. The shell can be used as a programming language to automate system administration tasks. In fact, it is commonly used to do just that. So, with that said, let's get started using the shell. In this section, we're going to explore the basics of using the shell. You'll learn how to move around the command line effectively and efficiently. We'll also use a text editor, VI, which you'll spend a lot of time in as an administrator, and we'll write a basic shell script. So let's get started directly on the shell. First, we need to learn how to move around the file system. You want to learn to list files with the ls command. ls lists the files in your current directory. To make a new directory, you type makedir and then the name of your directory. You can change into that directory with the cd command, change directory. We will cover the file system in more detail in a later lesson, but you should know that it's a hierarchical structure. If I type the pwd command, it shows me where I am in the hierarchy. The shortcut dot, just a single period, refers to the current directory, in this case /home/vagrant/neudir. The shortcut dot dot refers to the parent directory, or in this case /home/vagrant. So in order to move to the parent directory, I type cd dot dot. If I type ls again, I see the files I saw initially as well as my new directory. I can type to a new path, cd space /temp, And in order to go back to my home directory, I have a number of options. I can type cd, which is just a shortcut to take you to your home directory. You can type cd tilde, which is also the shortcut to the current user's home directory. Or I could type cd minus, which takes you to the last directory you were in. Let's look at the shell prompt itself. We have the username, in this case vagrant, and we have the host name. In this case, the host name is localhost. This will vary depending on the system you're in. The next section is the directory you're currently in. Tilde represents the user's home directory, and notice that when I was in temp, shell prompt showed temp instead of tilde. So the prompt changes as you move about the file system. The bash shell prompt is highly configurable, and people like to make all sorts of adjustments to suit their needs. Let's learn about how to edit some commands. On the bash shell prompt, the hash character indicates a comment. The $sign at the end of the prompt indicates that I'm a regular user ready to type commands. By convention, when you become the root user, which is a highly privileged user in Linux, the prompt changes to a hash sign to indicate that you're root and you should be more careful. We'll learn more about user privileges in a later lesson. In general, you should always log into the system with your normal account, and if you need to execute privilege commands, use the sudo keyword. We can run a command just by typing it, and of course if we want to run multiple commands, we can separate them with a semicolon. For instance, we could list files, and then we could change directories in a single line. Notice that the files listed out, and then my directory changes changed. I can go back with cd minus. I can put a process in the background with the ampersand character. For instance, I could open Vim, a text editor, but I could put it in the background so it's running not in my current context. So in this case, Vim opened, it's running with process ID 1762, but we're still in the shell. We'll learn more about how to control processes and what a process ID is later. If I wish to now access the program that I started in the background, I can type FG for foreground. Now I'm in the Vim text editor. We're going to cover Vim in just a few minutes. Something that will really help you become an efficient system administrator is using shortcuts on the command line. Let's learn a few shortcuts that will help us move around the command line quickly. We can use the echo command to echo output to the terminal. For instance, echo, the quick fox jumps over the lazy dog. This just echoes that output to the screen. Now if I hit the up arrow, I can recall that previous command. I can use Alt-B to move back a word, and I can use Alt-F to move forward words. You can use Control-A to quickly move to the beginning of the line. You can use Control-E to quickly move to the end of the line. If I use Control-U, it erases all of the text that I just typed and puts it in my paste board. I can paste it back with Control-Y. We'll have a handy list of shortcuts for reference available with the lesson materials. Now we're going to learn about a concept that is essential to understand for a Linux or a Unix system administrator, and that's pipes and redirection. Pipes and redirection is a concept that has given the Linux command line some of its most powerful features. So, for example, the ps command shows us the running processes on the system. I can pass it some arguments like ps, ax, to list processes in more detail. Don't worry if you don't understand the ps command, its arguments, or the output. That's not the focus here. If I type ps, aux, and I use a greater than symbol, that will take the text output from the ps command and it'll redirect it. So for instance, I could redirect it to a new file called processes. Now the content from that command has been captured in this file called processes. I can see the type of file that it is by typing simply the file command and giving it whichever file I want as its input. For instance, file processes shows me that it's just ASCII text. Now I can search within that file and I could perform operations on the text within that file. For instance, I can use the grep command and search for a specific keyword within the processes file. In this case, it found that there was a process in the list called bash within that text file. We're going to learn about grep and its purpose in a little more detail later on. You should also be aware that you can use tab completion on the command line. So when I start typing something, for instance gr for grep, I can hit tab and it completes other possible commands for me. If there's only a single option, it will finish it completely. For instance, if I continue to type grep bash and I type pr for processes, if I hit tab, it automatically expands the file name. This will save you a lot of typing. Now comes piping. Piping allows you to string a series of commands together using the output from one command as the input to the next command. For example, I can use the same command we did before, psaux, and then the pipe key, which is the vertical bar usually situated above the return key, and I can pipe it to grep for some specific command like bash. So this is running the process list and searching for very specific output. Using the pipe, you can connect any two commands together, or you can string many pipes together to perform very complex operations. For instance, I could echo a brief statement in quotes, and I could use greater than to append it to the processes file I already captured. Now if I use the tail command to look at just the end of the processes file, I can see a brief statement as the final line of input. Next, let's learn about variables and quoting variables. To assign something to a variable, you simply type the name of a variable, the equal sign, and then whatever you want that variable to contain. For instance, I'll assign the quick brown fox to the text variable. I can view the variable contents with the echo command. Now, importantly, I can also capture the output of a command into a variable. For instance, if my variable name is ls_text, I can capture the contents of an ls command into that variable using this syntax. So let's just make sure we understand this. ls_text is the name of the variable. Equal sign indicates that we would wish to assign some contents to it. And then we have $ with an open and closed parenthesis and the command in between them. This will take the output from ls-l and assign it to the ls_text variable. Now look what happens when I try to echo the contents of this variable. It's the same contents that we would expect from the ls-l command, but it's all glued together with no line breaks. This is due to how the shell has interpreted this variable. If I instead use double quotes to echo the output of this command, I get the exact format that I expect. Now note that if I use single quotes rather than double quotes, I get the literal ls_text variable output. So quotes are important to the shell. When you use a single quote, the variables are not interpolated by the shell. When you use a double quote, the variables are interpolated by the shell. We should also distinguish between environment variables and regular variables. An environment variable is available to all processes on the system. You can use the command print-env to view all environment variables. We see several environment variables here that are set automatically by the system. You can use the export command to make shell variables available to sub-processes on the system. For instance, in order to capture an environment variable, we type export and then the name of the variable. By convention, environment variables are always uppercase. So if we wanted to export ls_text, we would probably name it uppercase, and we could use the same command we used before. Now the ls_text variable is available to any sub-processes that I start with in my shell. To remove a variable you've already created, you can use the unset command. You type unset and the name of the variable without the $, and then that variable is removed. If you try to echo it, it has no contents. Next up is learning about filtering. Linux has a powerful variety of filtering commands available at your disposal. We'll use the cat command to cat out the etc passwd file. This file contains all of the user accounts on the system. We don't need to parse through each line of the file now, but we should just note that each field is separated, otherwise known as delimited, by a colon. The first field is the username, the last field is the shell. Just for example, we don't need to go through each field, but look at how we can manipulate this file using filtering commands. I can use the command cut to pick out specific fields in the output. For instance, if I wanted just the username field, I can use cut minus F1 minus D, and then in single quotes a colon, and then I pass the name of the file to print out only the first field of the file. So just to make sure we're clear, minus F is the field, we want the first field, minus D is the delimiter, in this case the colon. You can learn about all of the arguments and flags available to the various commands using the man pages. We can continue to use pipes and redirection to add on to this command. For instance, I can repeat the previous command by pressing the up arrow. I can use the pipe character to pipe this output into the sort command. Now the output is sorted alphabetically. I can continue this by adding another pipe and piping it to unique. Unique will remove any duplicates that are in the output. In this case, it actually didn't do much since there were no duplicates. Finally, I could pipe the output yet again to filter out for just, say, the first 5 results. I could do that with pipe to head minus 5. Now we're only printing out the first 5. Similarly, I can use tail minus 5 to print out just the last 5. Filtering commands are very powerful and you'll find yourself using them regularly. Next, we can look at shell history. Shell history will help you recall previous commands that you've already typed on the terminal. It becomes very useful because you'll find that commands are often repetitive. History is stored in your home directory in the file .bash history, which we'll look at right now with the less command. This shows all of the commands that I've typed on this terminal. I use Q to quit out of the less command. You can access the shell history interactively in the terminal with the up arrow and the down arrow. Notice as I push up and down, I parse through the commands that we've already been typing. You can type the history command to quickly, at a glimpse, see all of your shell command history. We notice that there is a number in advance of each command. This lets me quickly access a command in my history. For instance, if I wanted to access the file processes command in my history quickly, I could use exclamation point, often called just simply a bang, and then the number, 499. That runs the same command again. I'd like to encourage you to become familiar with the Control-R search history function of the bash shell. If you type Control-R, your prompt changes and it says reverse I search. What this means is that it's going to search in your history for case-insensitive content of whatever you type. Let's go back and type fox. We see when in the past I assigned text equal the quick brown fox in the variable assignment example. If I hit Control-R again, it continues to search in my history. This is a really quick and efficient way to access your shell command history. Now if I just press enter, it executes that command again. If you become proficient at using Control-R, you'll find that moving around the bash shell is very quick and efficient. I can execute the last command that I just typed with the bang bang shortcut. I can also refer to just the last argument on the command line. For example, if I type ls-l processes, that shows me a long detailed listing of the processes file. Now I can, as a shortcut, type file and then bang $sign to refer to the last argument on the previous command. This runs the command file processes. I hope that this brief introduction to Linux hotkeys was useful for you. Next, we're going to learn about regular expressions and shell globbing. Regular expressions are a language used to parse strings to pull out specific content. System administrators and developers alike use regular expressions in their everyday lives. First, some definitions. A string literal is any character that we use in a search or a matching expression. For example, to find the NUX in the word Linux, The NUX is a literal string. It is literally the string we wish to find. A meta character is one or more special characters that has a unique meaning and is not used as a literal in the search expression. For instance, consider the caret character, which is the Shift 6 key on your keyboard. This is a meta character that matches the very beginning of the line. Next, the search expression, also known as the regular expression. This is the expression that we will be using to search in our target, or in other words, it's a pattern that we use to find what we want to find. Consider, for example, the string bwhaley@gmail.com, my email address. The search expression caret bwhaley@ followed by $* matches any line beginning with bwhaley@ followed by any character at all. So if we wanted to find bwhaley@gmail.com in a text file, and where bwhaley starts the line, this is the search expression you could use. An escape sequence, or just an escape character, indicates that we wish to treat a meta character as a literal. So this is a little confusing, bear with me. Consider the case of the word persons, where the S is in parentheses, meaning it would be person or persons, plural. If we wanted to find just the S in the target string, we need to escape the parentheses since they're also regular expression meta characters. The search expression becomes then \, open parenthesis, S \, close parenthesis. And in this case, the \/ character is the escape sequence. Let's look at an example on the command line. I'm already logged in directly to my Vagrant Linux box. I can use the egrep command to search within the etc passwd file, which is the same file we used before when we were learning about how to filter commands on the command line. In this example, we're using egrep, the Extended General Regular Expression Parser. Actually, grep comes with many definitions. That's the one I chose here. In this case, we're matching any of the characters W, Y, or Z as they appear in the etc passwd file. Note that all of these lines contain at least one of those characters, but it doesn't mean that those characters are all in a row. It just means that the line has to contain the character somewhere. Similarly, we can use some shortcuts like capital A through Z, which matches any uppercase character. In this example, the output shows every line contains at least one uppercase character. We can show an example where we need to match a certain number of occurrences of a character. Consider this example. We're using egrep to find X and then a colon, which as we can recall is a field separator, followed by 0 through 9 at least 3 times. We can see that in each of these lines of output, there are at least 3 digits in a row, and that these are all of the lines in the etc passwd file that match 3-digit user IDs. We can match the beginning or end of the line with the caret and $. For instance, if I use egrep caret_r and search in the etc passwd file, I find all the lines that begin with R. Similarly, I can match lines that end with H by using $. In this case, the results are all where the shell is bash for that given user. We can use the pipe character to separate words. For instance, we can search for either the word bash or the word false with a $, indicating it's at the end of the line. Note that all of the output we matched either ends with bash or with false, which is just a false shell. It doesn't do anything. We can combine these techniques to search for very specific things. For instance, if we wanted to search for the string starting with an R, continuing with any character, and ending with bash, we can use this syntax. caret_r $bash $. The shell also supports a limited set of regular expressions, or regular expression-like language, known as shell globbing. The shell itself doesn't support a really large number of regular expressions, but you can do some subset of the commands, such as ls*, which lists all of the files, and in this case a directory, nudir, in this directory. We can also move things around. For instance, if I wanted to move n*, which should match the nudir in this directory, to /temp, Now I've moved the new dir to /temp. So that's a brief introduction to shell globbing and regular expressions. If you familiarize yourself with regular expressions, you'll find it to be very convenient on the command line. To really become an effective system administrator, you must become proficient in using text editing. There are a number of text editors on the Linux platform. A few of the most popular ones include VI or Vim, related projects, Emacs, as well as Nano and Pico, which are simple text editors. I strongly recommend becoming familiar with Vim, which is the most popular among system administrators and can be found on virtually any Linux system you'll ever use. We're going to spend a few minutes learning Vim, since it can be a little confusing to somebody who hasn't used a modal text editor such as VI before. You'll find a file called Gettysburg Address, which contains the actual text of that speech. We can list it on the command line. To open the file in VI, we use VI or Vim, which is an enhanced version of VI, and then pass the file name. This opens the contents of the file. In a normal text editor, you might just start editing and deleting words and characters now, but that's not how VI works. VI is a modal text editor, and so in order to edit text, you need to be in the editing mode. The default mode, which you can always reach with the escape key, or called normal mode, lets you move around the file, but doesn't let you edit. In order to edit, you type I. Now look at the bottom of the screen and you'll notice the file name, Gettysburg Address, in quotes, followed by the number of lines and the number of characters. As soon as I press I, it changes to say that I'm in insert mode. This means I can start typing and editing text. To get back to normal mode, I hit escape. There's also command mode, which you reach with a colon. Notice when I type a colon, the bottom of the screen changes to a colon. Using command mode, I'm able to issue commands to the terminal. One useful command to know right away is how to quit. If you type colon followed by Q, enter, you quit the file. You need to know how to open and close files, so that's a critical one to keep in mind. Let's open it again. A final mode is visual mode. I type V to go in visual mode. Now I'm able to highlight lines, which I can use to copy and paste or make edits to the file. Hit escape to return to regular mode. Now we need to learn to move around. You can always move around with the cursor keys, the arrow keys in the bottom right part of your keyboard, but that's not the fastest way to move around in Vim. You can use H, J, K, and L, the keys on the home row of your keyboard, to move around. L goes right, H goes left, J goes down, and K goes up. You can move entire words at a time by typing W, or B to go back. You can type a $sign to go to the end of the line, or a 0 to go to the beginning of the line. Moving around with these hotkeys will make you a much faster and more effective text editor. I can search for a very specific letter on a line using the lowercase f. For example, on the second line, the word liberty starts with a capital L. If I type F capital L, I go to the first occurrence of the L, the capital L on the command line. Now in Vim, very commonly you can inverse the search with a capital. So for instance, the very beginning of this line starts with a lowercase a. In the word nation, there's also a lowercase a. So if I wanted to go to the a at the beginning, it's 2 a's over. In order to reach that, I will say 2, capital F to search backward, and then lowercase a. And it takes me to the first A on the line. This might sound cumbersome, but it's actually very effective once you become proficient at it. You'll recall that if we press I, we go into insert mode to begin typing characters. If I use capital I go to insert mode at the beginning of the line. I can also use A, lowercase a, to start appending to the text where my cursor currently is located, or I can use capital A to start typing at the end of the line. Sometimes you need to move your cursor around the file quickly, maybe even to specific lines. I can use the capital G for that. For instance, I can use capital G to go directly to the end of the line. I can type 2 capital G, to go to the second line in the file. If I have multiple pages of text, I can use Control F and Control B to page between the text. You'll also sometimes need to search within a file for something specific, and in order to search, you can use the / key. For instance, if I search for the word "and" in this file, I find several hits, and Vim highlights them for us. You can use the lowercase n key to switch between all of the hits, moving your cursor directly there. And if you use capital N, it searches backward. It's quite consistent. Next, we'll learn some basic editing with Vim. You can, of course, go into insert mode with a capital I and begin typing some text. You then hit escape to switch back out to command mode. Now, that's not necessarily the most efficient way to manage all text. You can use the X key to start deleting text. So if I'm on the B in begin, I can type X, and each time I type it, it deletes one character. If I decide I want to undo what I had just done, I can use the U key for undo. And if I use Control R, I can redo what I had just typed. I can delete entire words at a time by typing DW, or I can change a word, which means delete the word in front of my cursor and start inserting a new word. So for instance, if I'm on the S in the word score, I can type CW to delete the word score and type a new word. I can delete an entire line at a time using DD, or I can change a line using CC. If I need to open a new line, I can use lowercase o to open a new line below my cursor. Or if I need to open a line above my cursor, I can use capital O. I can also repeat the last command by simply typing the period. Finally, you can copy and paste in Vim using yanks. I can use YY to yank a line to my clipboard, and then I can paste it using P. I can paste it above my cursor using capital P. That's really the basics of using Vim. You can type :help in Vim to get to a help screen that will teach you how to move around and how to use the editor in more detail. It is a highly customizable and powerful editor, useful even for programmers who are power users and need to navigate around the file system. Let's quickly learn how to edit and use multiple files at a time. Now, I've made a bunch of changes to the Gettysburg Address, and I don't really want those reflected in history. So I'm going to quit without saving my changes. In order to do that, I use :q bang. Now, if I want to open multiple files, I can simply list them out on the command line, one argument at a time. In this case, I'll open 3 files: the Gettysburg Address, a script called postinstall.sh, and another script called passparser.sh, which we'll go through in detail in a later lesson. I now have 3 files open. In order to list the files, I can type :args, ARGS, which lists all of the arguments I passed to Vim. Notice at the bottom, it shows that I'm on the Gettysburg Address, indicating that that's the current file with square brackets, and that there are 2 additional files. I can type :next to go to the next file in the list. And I can type :prev to go to the previous file. Just as before, I can type :q to quit. We're going to take all of the knowledge we have from the previous lessons and formulate a bash script, just an automated way to execute multiple commands and perform some function. The script that we're going to use is one that I've written called passparser.sh. You would never use this script in the real world since it doesn't do anything particularly useful. However, it does demonstrate several features of bash that you'll commonly encounter when writing real scripts. Passparser.sh, all it does is read the /etc/passwd file, each line at a time, sort it by user ID, and print the output in a very specific format. You can refer to the man pages anytime you're confused about the syntax of any commands used within the script, but we're going to go through it line by line. So first, we want to check what the permissions on the script are. In order for a script to execute, it must have the executable bits set. We haven't learned about file permissions yet, but let's quickly look at the permissions on this file. If we run ls-l, we see a lot of output on this command line. In particular, we're interested in the beginning of the line. We see several rwx. This means that the file is readable, writable, and executable. The first 3 are for a user, the second 3 for a group, and the last 3, which doesn't have a W, is for everybody else who might use the system. We're going to go through that in detail later, but importantly, the X is turned on, meaning that this file is ready to execute. Now let's see what the output looks like. We'll remind ourselves first by looking at the raw etc-passwd file. Remember that it contains a list of users with a colon-separated field. If we run our script, which we preface with /, indicating that we wish to run the script within this directory, the thing that it does if we don't pass it any arguments is give us a usage statement. This is very common in Linux systems. The usage statement indicates what flags and arguments you need to pass to the script. This takes /etc/passwd as its only argument. What happens if I try to pass it two arguments, like etc-passwd and then the number 1? It also prints out the usage statement. So it's doing some smart things about checking the flags. So let's pass it what it's expecting, just the etc-passwd file. It prompts me, do you wish to parse etc-passwd? And then it indicates that I should type yes or no. I'm going to type something else, blah. It prompts me again, do you wish to parse etc-passwd? Yes, I wish to parse it this time. So we can see that it looked at the output of /etc-passwd and printed the output in a very specific format. It says that the user root has UID 0 and has home directory /root. Let's look at how it worked. I'm going to open the script with VI. We'll start at the top. The first line indicates that this script should be interpreted with the bash shell. The hash bang, the # and then the exclamation point, is called a shebang. It just indicates that this is meant to be an interpreted script, and then the next section says the interpreter is bash. Here we're on the first conditional. This is what an if statement looks like in bash. It's doing the syntax check, the bit that says we need to make sure that we are accepting one argument. So we have an if statement, and then we have our 2 conditions. One condition is that the number of arguments passed must be exactly 1. If it's not equal to 1, then the test fails. Then we have an or, and then there's another condition. The first argument minus h. So if either one of these conditions is true, then we will follow the next 2 lines. We'll echo the usage statement, and we'll exit with exit code 1, which usually indicates an error. Next, we're reading the command line argument, which we pass, in this case etc-passwd, into a variable. The variable in this case is file. In bash, when you need to read a command line argument, it's always starting at $1. $0 indicates the shell file itself, the script itself. Next, we have a function. This is a reusable bit of code. We have an until loop. The purpose of this loop and this function is to determine when the answer is yes to the question, do you wish to parse the file? So until the answer variable contains either yes or no, this loop will just continually prompt, do you wish to parse the file? And then it will read the variable, and then it will test it again forever. Next, we have a conditional. If the answer was no, then we just exit. So if they don't wish to parse the file, then we'll exit. After that, the function just returns. Now we call the function using the parse prompt. So again, this isn't really how you would run a script in the real world. Most commonly, any code contained within a function will be called more than once. In this case, we're only calling it once for demonstration purposes. Finally, we get to the real meat of the script where the parsing happens. I always like to copy and paste an example of the line that I'm looking to parse, so I have it for a handy quick reference. So I've copied and pasted one of the lines from the etc-passwd file here. Next comes the looping logic that sorts and prints out the parsed lines to the terminal. First, we sort the file by its user ID, and then we loop through each line, matching the desired fields and printing the output. So first, we have an example of running a command and piping it to the loop. we use the sort command to sort the file by the third field. So the field separator is passed to sort using -t, and -k indicates that it's the third field, and -n is the file that we wish to parse. In this case, etc_passwd has been assigned to the file variable. We take the output of that sorted file and we pipe it to this while loop. The while statement reads each line at a time. The 3 lines starting with user followed by user ID and homedir parse the line. So we use the echo command to pipe the output to the cut command, which pulls out the first field. Next, we want the user ID, which, looking at our example line above, we can see is the third field, so we cut out the third field. Next up is the homedir. The homedir here is the 6th field, which you can count with those colon delimited field separators. Once we have all 3 fields, we can echo that output to the terminal. Notice that we use $sign and then curly braces with the variable between them. This is a common way to use a variable in a script. Finally, just to demonstrate how a regular expression can work in Bash, we check that if a user ID contains at least 3 digits, then we print out this user has a UID with at least 3 digits. Finally, we close the loop with a done statement indicating that the loop is finished. So that's a simple Bash script. You'll find these all over Linux systems in order to automate and make more efficient many tasks. We've just learned all about the Bash shell and about writing a quick script using Bash. In reality, when a program gets a little more complex, we need to turn to another programming language, and there are many, many programming languages available at our disposal. We'll cover many of the common system administration languages used for quick scripts in this section. First up is Perl. Perl was written by Larry Wall, one of the leaders in the open source software movement. Perl was originally derived from the C programming language, as well as some shell programming concepts, the Lisp language, and the string parsing tools awk and sed. Perl's motto is, "There's more than one way to do it." Larry Wall is a linguist at heart and has built Perl based on the principles of natural language design. Perl is tried and true as a programming language and is used in many large websites and projects. It has CPAN, as we indicated before, the comprehensive Perl archive network, including a huge base of modules. You can reuse those modules as libraries in your own programs, so you can avoid writing software that's already been written. There are many reasons to use Perl. A couple of them include extending, updating, or contributing to an existing large Perl project. Perl is also still a good choice as a portable, cross-platform language since it's available on nearly any Unix and Linux system around today. Python is another very common language.
It was created by the Dutch programmer Guido van Rossum, who, along with several others in the open source community, is known as the benevolent dictator for life.
This term is lovingly given to open source authors who maintain projects that are used by a large user base. Python differs from Perl in some important ways. In Perl, we talked about the saying, there's more than one way to do it. In Python, there's one, and usually only one, obvious way to do it. In Python, they also believe that beautiful is better than ugly, which is kind of a ding against the Perl syntax. In Python, indentation is meaningful and is intended to help with readability. So if you have a line and the line below it is indented by a few spaces, that means something in the Python language. Python has excellent object-oriented support. It's used in large-scale web applications and is great for sharing readable code among a large team. The final language we'll mention here is Ruby. Ruby was written by Japanese computer scientist Yukihiro Matsumoto. His stated goal with Ruby is that it intends to make programmers happy by focusing on creativity. In Ruby, everything is an object, just like as in Python, and there's more than one way to do it, just like as in Perl. Ruby is great for native integration with some of the really popular configuration management tools out there, such as Puppet and Chef. It has a very low learning curve, an obvious syntax, and is very simple to read. Many open source projects are coded in Ruby. Welcome to Lesson 3, Booting and Shutting Down. One of an administrator's basic responsibilities is to safely start up and shut down the system. After any major changes, an administrator should reboot the system to ensure it can survive a power outage or other unexpected crash. However, if something goes wrong during the boot process, you should know how to fix it. In this lesson, I discuss the bootstrapping process in the Linux bootloader grub. I point out how the kernel is loaded and begins execution. I talk about Upstart, the software used to manage processes on the system. I also cover init scripts, which are a legacy method of managing the startup and shutdown procedures. So far, we've talked in detail about the basics of using the Linux command line. Now we're going to talk about how the system starts up and subsequently how the system shuts down. Understanding how the system starts and stops will really give you a lot of insight into how Linux works. So we'll start from the very beginning, which is around reading the bootloader. The bootloader is a small piece of software, usually at the very beginning of a large format like a disk or a large format external storage device that contains only enough code to launch the operating system. Typically, the bootloader is located on the master boot record or the GUID partition table. Importantly, there's a transition happening in computing right now from the old way of doing it, which was the master boot record, to the new way of doing it, which is the GUID partition table. In either case, the concept is the same. Load the operating system into memory so that it can start executing. So to start with, the firmware, which is the embedded software that's on the chip in your computer, commonly called the BIOS or the UEFI for GUID partition tables, provides a list of boot devices to the system. So you could boot from a DVD, from a USB thumb drive, from your hard disk, which is the most common, or even over the network via a protocol called PXE. Once the device is chosen, the BIOS reads the bootloader from the very beginning of that device, and how do you define the beginning depends on whether it's the master boot record or the GUID partition table. The first thing that happens once the bootloader is up is that it opens and initializes the kernel. The kernel image as it sits on disk is compressed, so the bootloader needs to decompress the kernel image. It detects all sorts of memory in the system, how much RAM is available basically, and then creates the kernel's internal data structures. All of that kernel memory, where the kernel's data structures reside, is not available and is protected by the kernel to user space applications. That is an important thing to distinguish. Kernel memory is separate from user memory, and this is for security purposes. The next task that the kernel performs is to detect and configure the devices in the system. It starts by probing devices to look at all of the inventory attached. So this might be the number of processors available, the buses that are available in the system, such as the PCI bus, any I/O subsystems, which stands for input-output, anything coming to or leaving the processor, such as network interfaces, and other storage devices. Then the initial RAM disk is decompressed and mounted. Some essential drivers are loaded that the kernel needs to proceed. RAID drivers to ensure that if there are multiple disks and the file systems are spread among multiple disks for redundancy or performance purposes, RAID drivers make sense of that. LVM stands for Logical Volume Management. This is a technology that enables disks to shrink and grow. Any encrypted file systems, basically the bare bones that is needed for the kernel to mount and continue the boot process happens at this phase. Next, the kernel creates some important processes that it uses internally. Things like you'll see in the process list kjournald, kswapd, and khubd. All of these processes start with a K. Next, the init daemon, and most recently Upstart as a replacement for the init daemon, is the parent of all processes. It's spawned by the kernel with the process identifier 1. From there, the Upstart init daemon can start up all the other processes on the system. It emits an event called startup which then begins the system startup process. Next, the local file systems, virtual file systems, and swap, which contains an overload area in case the RAM is full. Those file systems are all mounted, and the services can begin to start up. So the init process, which is started by the kernel and is managed by the upstart system, runs a variety of jobs and scripts to load different system services. So these are things like power management. If you're using a laptop and you close the lid, the computer goes to sleep, the kernel has to manage that. Also the hardware clock. Of course, you know that each Linux system, every system really, has a clock that ticks by, and this is used for all sorts of purposes beyond just looking at the time. The kernel starts up the hardware clock and manages it. It starts and attaches network interfaces and any other network daemons that might be running, such as the SSH server or a DNS server or any other services running on the box. Traditionally, in Linux, the startup process has been handled by something called the System5 init. This is for historical reasons. System5 was an old type of Unix, and Linux, having been evolved from Unix, inherited System5 by default. But System5 has a number of limitations and is no longer very well suited for today's modern computing world. It's starting to be replaced by a much more flexible, powerful, yet still simple daemon called upstart. The historical System5 style init scripts are in the directory /etc/init.d, or sometimes, such as in the case of Red Hat systems, in etc/rc.d/init.d, while upstart maintains its jobs in the directory etc/init. For each run level, and we'll talk about run levels in just a moment, there is links to the etc/init.d directory in rc.d. So we're going to dive in and see all of this in detail. Don't get too hung up on memorizing all of these directories now. Run levels are really just a numbering system to classify what boot state we're in. And we can just see really quickly what that means by looking at the run levels themselves. 0 represents that the system is shut down and is just not operational. Run level 1, or sometimes referred to as S, represents single user mode, meaning that no network services are started, no other users are able to log into the system. Levels 2 through 5 are a bit redundant and are mainly just multi-user modes used for networking. Some systems distinguish between run levels 2 or 3 and run level 5 by indicating that level 5 is for window managers, like running GNOME or KDE, and run level 2 and 3 is just a command line with no window manager running. Level 6 can be used to reboot the system. The run levels are a bit of an antiquated technology at this point and are mainly still implemented just for compatibility purposes while the system transitions to a pure upstart and start event-based system. We just learned at a high level what the PC boot process looks like. We can actually use our Vagrant and VirtualBox setup to see that in real time. As you might recall, Vagrant is a virtual machine manager that uses VirtualBox to actually run and execute the virtual machine. What that means is that we can see the Vagrant managed machines through the VirtualBox interface and see the system start up and shut down, manipulating it and learning about it as we go. So let's dive in by looking directly at VirtualBox. So the first thing to notice is the Oracle VM VirtualBox Manager. In order to open this, I simply open the VirtualBox application. You can see on the left side all of the Vagrant virtual machines that I have running, or that I have listed even. 4 machines total are running. We're only going to pay attention to the 4th one down that I have showing running. We can also see that here's the operating system login. If you were to walk up to a server in a server room and you open a Linux command line prompt, this is what it would look like. Vagrant hides all of this detail for us. Before we reboot the system and start to look at the boot process, let's look at how it works from the Vagrant command line interface. I can log into my Vagrant box, and there's a few important directories and things to be aware of. First, let's look at the mounted file systems. I'm just going to pick out a few of them by running mount and piping the output to grep for ext3, which is specific file system format. This highlights two file systems to be aware of. One is the root file system. In this case, it's an LVM file system, which we can tell because it says vol group. Root is where it's mounted, /. This is the beginning of the file system hierarchy. We also have /boot, an entirely separate file system, and that's what we're going to learn about for the rest of this lesson. For extra credit, just type the mount command and learn about what all of these other file systems are for. Now we'll change directory to /boot. If we type ls, we can see that there are a lot of different files in here. These are all kernel and boot related files. Another command to be aware of is the uname command, which shows system information. If I type uname -a, it shows me some output about the system. In particular, the section that I've highlighted here shows that this is kernel version 2.6 and then some other numbers. This is the running version of the Linux kernel on this system at this time. I can show just that version using uname -r. Now, if I want to just see the files in /boot associated with this, I can use some of the shell tricks we learned in the last lesson. I can use ls/boot, and then I can show all of the files that match this string, uname -r. So this uses shell globbing and embedded command execution, this $parenthesis syntax, to show all of the files related to the current running Linux kernel. So let's look at what each of these files does. The boot config file, if I run file on it, is just a plain ASCII text file, meaning we can look at it with a text editor. This is a lot of configuration about how the Linux kernel is running. You can see that it's 4,564 lines long. The Linux kernel is highly configurable. We have symvers, initramfs, and system map, which we don't need to talk about in a whole lot of detail now, but these are important for the boot process. The most important file here is the vmlinez file. This is the actual compressed kernel image. When the bootloader starts, it opens this file and decompresses it. Now let's look at the grub bootloader. We talked a lot about what the group bootloaders do in the last section. Now we're going to learn about grub, the Grand Unified Bootloader, which is the standard bootloader used on Linux systems. At this point, we're in /boot/grub. There are several files in here, most of which we can safely ignore, but we will go ahead and view the grub.conf file, which is the configuration file for grub. This configuration file shows which kernels are available to grub to start up. Let's look at it line by line. Skipping over the commented lines, which are indicated, of course, by the hash marks. Default equals 0 says start with the first listing. Programmers often start counting from 0 rather than 1 like the rest of the world. Timeout is 5, meaning you have 5 seconds to select a kernel to start. And then hidden means it's not going to show the menu for selection unless you interrupt the boot process. We'll see that in just a minute. Next is our actual kernels that we can choose from. You could use this to set up multiple operating systems on a single disk. For instance, I could be running CentOS on one partition, Ubuntu on another partition, or even Windows on a third partition. In this case, we actually have two operating systems. We have CentOS running a specific kernel version 2632-358. It's a very specific kernel build. And we have the second one running 2632-279. These are very similar related kernels, probably just with some security or bug fixes in them. This kernel flag shows exactly where the kernel is in the boot file system under vmlinez, and this is what we saw a moment ago when we were looking at the different files available. And then a whole lot of flags, which we don't need to cover in detail right now. Finally, it shows us the initial RAM disk, and then we can select the other kernel if we want. So most likely you won't need to edit this file very often, but when you do, the format is actually pretty simple. So we'll quit out of VI now, and we'll look at the boot process using VirtualBox. So here we are at our running, this is our Vagrant box. This is the same box we were just logged into, only this is as if we're sitting at the console. I'm going to go ahead and restart the system. This menu under Machine, Insert, Control, Delete indicates that I'm about to restart. Just as if you'd typed a Control, Delete on your Windows system. So we can see the Linux system starting down, we can see the VirtualBox BIOS interface, and I interrupt the boot process by just pressing any key on the keyboard. Now we're seeing the grub boot menu. As you recall, we saw two options in the grub.conf file indicating the two different kernel choices that we have. This is what that was indicating. We can switch between which kernel we want to boot with the up and down arrow, and we can edit the kernel options right here if we want to. Type E to edit. Now you see the same lines that we saw in the grub.conf file. This is indicating where the kernel can be found. This is indicating the path name and all of those other options we saw. And this is indicating the initial RAM disk. Now I just want to boot, so I can type B, and it boots the system. That's the most common startup sequence. All of the complexity is hidden away by that nice splash screen, and then we get this login prompt. Let's restart it again. Let's see if we can interrupt it and see a little more detail about what's going on. I can interrupt the boot process, and I'm going to hit E to edit this kernel, and E again on the kernel line, and I'm going to delete this section right at the end, RHGB. What that little argument does is hide all of the boot process complexity from us so we don't see it. Instead, I'm going to replace it with the confirm command. This is telling the system that I wish to confirm every service as it starts up. This is mainly so we can see how the boot process works. So I edited that, I hit return, and now I can press B to boot. It initializes all the hardware devices, that's what's happening now, and it starts mounting the file system, so at this point you can see some detail about what the system's doing. Starting at the top, you can see remounting root file system in read-write mode. So this is telling the Linux kernel is accessing the root file system, that slash file system that we saw from the mount command, and mounting it so that it's writable. We mount some other file systems, we start some services that are important to the kernel, and at this point it's prompting me. Start service LVM2 monitor. So I can say yes or no. If I'm having a problem with some service, I can interrupt that and not accept that service now. Now this is an important thing to know about because if you're making changes to grub.conf or to services that start at boot time and you make a mistake, suddenly the system will no longer be bootable. So this allows you to bypass anything you may have broken, but not everything. So I'll say yes to this one, and here it's trying to start an iSCSI service, which I'll just accept. We're gonna probably accept just all of these options because we're not trying to debug a problem. IP tables is the Linux firewall process. We'll accept that as well. Here it's asking me start service ETH0. This is always the first network interface on a Linux system, and we'll learn more about network interfaces in a later lesson. So I'm accepting all of these options so that the system comes online, starting various services that are managed through the upstart process, the init process. And once all of these processes start up, we're going to see that command, that login prompt come again. And finally, we're at the login prompt. So that's what the Linux boot process looks like. And this will be the same on virtually any Linux system you encounter. Now we'll go ahead and restart one more time so we can demonstrate what it means to boot into single user mode. As you recall from the run levels, single user mode is when the system doesn't have any network access and doesn't allow multiple users to log in. On some systems, you don't even need a password to access single user mode. I encourage you to enable password access to single user mode. So let's restart it again. As the system starts up, I interrupt it again, and I press E to edit, and I want to edit the kernel, so I highlight the kernel line and press E. And this time I'm going to delete the RHGB and type single, which will boot me to single user mode. I press enter and then B to boot, and it's going to go ahead and run through the device initialization and some of the services. But notice that it right away drops me to a shell prompt that says root at localhost. This indicates that I am now the root user on the system. There's nobody else logged in. There's no network up. So I can't do anything, but I could debug a problem that existed only in one of the other run levels. This is a great and handy way to debug problems during the boot process. If I want to change to another run level from here, I can type init3, which will switch me to a run level that has multi-user mode and networking support. So at this point, it's going through all of those same services that we accepted before and gives me a login prompt. That's the basics of the Linux boot process. Now that we learned some of the basics of the Linux boot process, we'll just take a quick peek at the kernel as it runs on the system. We're not going to spend a lot of time learning about the kernel in this live lesson, as it's usually somewhat transparent to the system administrator, but it is good to know some important things about the kernel as it's running. So we'll switch over to our Vagrant box. We'll log into the CentOS system. If you recall from the last slides, we remember that the kernel starts up several processes. These are internal to the kernel and are transparent to the user in most ways. However, we can still see them with the PS output. We'll use the PS command and the AUXW flags, which you can look up in the PS man page, and we'll take that output and search for just the special square bracket character, which you recall from our regular expression tutorial. The backslash is indicating an escape character. So these processes are all kernel processes, not used by users directly. We don't need to go through the details of what all of these kernel processes do, but we can pick out a few examples. kthread-d manages kernel threads. md/0 manages the RAID subsystem. kswapd manages any swap space available for overflow from the RAM. There's many other kernel processes in this list. These generally don't impact the system administrator. Sometimes if a system is misbehaving, you'll see some process like the kswapd process running out of control. You'll see that in the top output, which we'll talk about later. That's really the only time during standard administration duties that you'll encounter these processes. Next, I briefly wanted to touch on kernel modules. Modules are located in /lib/modules. There's one directory for each kernel. As you recall, we're currently running the 358 build of the kernel. So if we change to that directory, we can see a whole lot of files. These are all very specific drivers that the kernel has available for hardware attached to the system. Not all hardware is created equal. For instance, a network card created by Intel differs in many details from a network card created by Cisco, or yet again from a card created by some other company, perhaps Broadcom. The drivers for each one of those cards is located in this directory. Again, this is a place where most administrators don't need to edit very often. Modern hardware comes naturally to the Linux kernel. However, there is the occasional situation where you might need to make some kernel changes. In that case, it's good to know where these directories are. Now, these modules are loaded by the kernel at the boot time. It doesn't make any sense to load a Broadcom network card if we don't have any network card attached to the system. So you can see which modules have been loaded by typing sudo to run this as the special super user, and then we type lsmod. It doesn't matter that you don't understand all of the details of this output, but we can see on the left side which modules are loaded, the size that they're taking in kernel memory, and what other modules depend on it. In the event that you need to edit drivers on the system, lsmod and the modprobe command are how you accomplish that. Modprobe adds and removes modules from the kernel. One place that system administrators do encounter frequently is the concept of synthetic file systems. Most file systems, like the boot file system or the root file system, are real file systems that live on some disk. Synthetic file systems are virtual or fake file systems created by the kernel. It's a way for the administrator to access the internal variables within the kernel. One such file system is /proc. The /proc system is meant for process information. It's an interface into the kernel's data structures. If I list the contents, there's a whole lot of files in here. You'll see a lot of directories with numbers. These are all just process IDs. If you recall from our last slides, process ID 1 is the init process. So there's a directory /proc/1 that contains details about that process. If we looked at some command within there, for instance, if I cat out proc1 and then the file command line, that shows me exactly how that process was invoked. In this case, it's the init process. In addition to the process ID file systems, there's many other tunable kernel configurations that we can access in /proc. For instance, in /proc/sys/net/IPv4, kind of a mouthful, this is a commonly accessed place for a system administrator to change IPv4 tunables. If I list the contents of this directory, you'll see a lot of very special files that I can use to change how TCP or IP or similar protocols work. If I type cat TCP mem, this shows me a specific TCP tunable value. A common one is IP forward. In this case, this system doesn't allow IP forwarding, but often on a system that might act as a firewall, for instance, you would enable this by setting IP forward to 1. Another synthetic file system is /sys. /sys is much like /proc, but it's really meant for devices and buses and drivers, also known as kernel modules, as we just learned, and how you can configure those. So it has a slightly different use case, but the intention is the same. You use it to manage configurable values used by the kernel. Now that we know what the boot process looks like, we're going to look at the system that manages the boot process, known as Upstart. Upstart is fairly new to the Linux world. Most administrators are very familiar with using System 5 style init scripts. We're going to look briefly at those in the next section, but Upstart is the new up-and-coming replacement for init, and it's important to become familiar with it. Some systems are further along in the transition process than others. CentOS runs Upstart, but mainly in a System 5 init compatibility mode, in which Upstart is managing the boot process, but really runs it exactly as if it were a System 5 style. We're going to explore that next, but first we're going to look at a system that has implemented Upstart in some detail, Ubuntu. Thanks to Vagrant, we can really quickly get up and running with an Ubuntu box. I've posted an example here, but you can go and find more boxes at www.vagrantbox.es and experiment for yourself. On my system, I have 2 boxes running. If I can see that with Vagrant status, I have a CentOS box and an Ubuntu box. This lets me log into either one of them at will. I can use Vagrant SSH to bring up the Ubuntu box that I already have prepared. Notice that the command line looks quite a bit different than we've been seeing with the CentOS box. We're still using bash, but the command line has been customized, as has the initial display screen, often called the message of the day, or the etc.motd file. We can see all of the Upstart jobs with the initctl command. If we run sudo initctl list, we see all of the Upstart controlled processes and what their current state is. Don't worry about understanding each one of these right now. The jobs are all kept and controlled in /etc/init. If I list the contents of this directory, you'll see that there's a config file for all of the processes that we saw in the job list when we ran initctl list. Let's look at an example startup file. A good one to use as an example is SSH. As you might already know, SSH, or the secure shell, is a method used to remotely access systems. Vagrant is in fact using SSH in order to log us in from our terminal system into the running Linux box. So if I cat or concatenate the SSH conf output to the screen, you'll see that It's a fairly short script that shows how to start the OpenSSH server. Let's look at a couple of the sections in the script. We have a description indicating what service this is. We show what run levels it starts and stops on. As you recall from our run level screen, levels 2 through 5 are all multi-user, fairly similar run levels. That's all of the run levels we're starting it on. Respawn tells us that if this process dies, we want to start it back up. Remember that oftentimes you're managing systems that are not physically proximate to you. They may be in a different state or a different country entirely. If SSH is your only method to access the system, you won't be able to manage it if SSH goes down. So this line tells it to start up if it stops for some reason. Next, we have the pre-start script. This is doing a few things to test if SSH should be running. It's checking to make sure that the executable that runs SSH, called sshd, is on the system. That's what the test command does. It's then testing whether we shouldn't start SSH. This is an Ubuntu customization. We do a couple of other steps in the pre-start script. But the real important bit is right at the very end, where we're just saying exec sshd -d. That's telling the SSH server process to start as a daemon in the background. So if we look in the process list, running psauxw, the command that's starting to become second nature to us, and we search for sshd, we can see an sshd server process running just as we saw in the exact output at the end of that script. Let's look at another example, network interface.conf. This example looks somewhat similar to the SSH config in terms of the sections that are available. We can see that the description is to configure a network device. However, there are some subtle differences. First, under emits. This is an event that Upstart emits when a certain script is finished running. In this case, this particular event is net device up or net device down or static network up. This is a way for different events to communicate with each other. For instance, we don't want to start the SSH process before the network is up. It wouldn't make any sense since having the network up is a dependency for SSH. So this is a way for the networking process to indicate to SSH and other network daemons that the network is available and those processes can now start. Further down in this script, we have what we saw, similar to what we saw in the SSH process. We have some pre-script activities, and then the important line is this exec line, saying bring up the interface if all of this other stuff has already happened. Next, let's take a look at how we control the initctl processes. So again, if I type sudo initctl list, I see all of the running processes. And let's look just for the TTY processes. TTY processes are the terminal processes. If you're sitting physically in front of a Linux computer, you can type in Alt and F1, F2, all the way through F6 on the command line in order to access multiple terminals onto that Linux box. Of course, this doesn't work in a virtual machine like we're in now. It only works if you have a keyboard attached to a physical console. So we don't really need all of these terminal processes running. We can start and stop them with initctl. We can say sudo initctl stop tty6. Now if we check our list again for the TTY processes, we can see that 5 of the 6 are start running just as they were before. It even tells us the process ID for each of them. And then TTY6 is stopped. So if we were now sitting in front of a Linux terminal and we pressed Alt F6, nothing would happen. It would no longer work. In order to start it back up again, I can use my up arrow shortcut to get to the history, and I can change stop to start, and it starts it again. So that's what Upstart looks like on Ubuntu. Let's look at how CentOS has run Upstart. We can run vagrant status to see our boxes. We want to access the CentOS box, so we type vagrant SSH to our CentOS box. Now if we run sudo initctl list, there are far fewer processes running under CentOS's implementation of Upstart than under Ubuntu's. Remember, CentOS still has just implemented Upstart in a very simple form that mostly maintains System 5 init capabilities. If we change directory to etc init, where all of those config files live, there are also far fewer config files. The TTY process is actually very similar. It's saying we don't want all of the TTYs running in any mode except the multi-user modes, which are 2 through 5. It uses exec to spawn each TTY process. That's the essence of what this script does. But the important one for the CentOS system is the rc.conf. This is what maintains compatibility with the System 5 style init. So all this does really, you can see right at the end, is it executes this script, etc rc.d rc. So let's take a quick look at that script. Whoa, there's a lot of stuff here. We don't need to go through all of this in detail. But let's look at the very end at least, because that's where the interesting stuff happens. Right where this comment is that says, now we run the start scripts. So this is going to run through each of the System 5 style startup scripts one at a time and execute them. Now let's take a look at System 5 style startup scripts. We'll use CentOS for our example system since CentOS is the most common system that still uses System 5 style init. We left off by looking at the rc.conf file for Upstart, which basically just pointed to the System 5 style init scripts in etc init.d. This is the traditional location for System 5 style init scripts. It contains all the startup scripts for the various services needed by the system. Let's look at a few of the examples. iptables is firewall software. It's built into the kernel and it blocks certain traffic destined for an address that you specify or a port that you specify or a given network from traversing the system. Linux kernel is embedded in many common firewall devices, whether you see the kernel and the Linux side of it or not. Network is the script used to stop and start the network. Puppet is a configuration management system that comes pre-baked as part of this Vagrant box. You can use it to configure software when the system starts or stops, or make sure that the kernel is at a very specific state. rsyslog is a syslogging service. Anytime an application sends logs indicating maybe that there's a problem or just telling you some information about what the application is doing, rsyslog will capture that log data and manage it for you. SSHD, which we spoke about before, is a common network daemon for remote access. These VBox scripts at the end are specific to VirtualBox. The specific contents of etc init.d vary greatly among not only various distributions, but even on systems within a distribution, depending on what services are installed. You can start and stop these scripts using the service command. We don't want to stop and start anything right now, but we'll say sudo service sshd status to see what the status of the SSH process is. As you guessed, we could stop it by saying stop, or if it was already stopped, we could start it by saying start. We don't want to stop it now since it would terminate our connection. The run level process is key to understanding the System 5 boot process. Run level startup scripts are maintained in the rc files in etc rc. We're going to use ls-ld, where the d flag shows that this is just lists the directories and not the contents of those directories. The traditional location for the rc run level directories is in /etc. Red Hat-like systems have moved them to rc.d. This is indicating that these are just symlink directories. So let's go take a look at the actual directories. Let's look at the contents of the run level 3 directory. What we see here is a long series of symbolic links pointing to the scripts in the etc init.d directory that we looked at a minute ago. When you change to a new run level, for instance, when you're booting the system, you enter run level 3, it starts processing these scripts from top to bottom. The simple alphabetized list here is how it accomplishes that. So it starts with K02 and continues processing each K script. These are kill scripts indicating to the init process to stop that service when that run level is entered. So none of these services will be running in run level 3. When the kill scripts are finished running, we use the startup scripts, indicated with an S. These are also processed alphabetically and point to the corresponding startup script in etc init.d. In this manner, you can carefully control the order in which services are started and stopped. You can see that this is kind of a simple but still pretty effective way that Unix used to start up processes for 20 or 30 years. Let's look at an example script, the sshd script. We can pass the full script to the less command to view the script. At the beginning is just some comments, set some variables and read some additional files. The syntax should look pretty familiar after we looked at the bash script earlier. As you might recall, all caps is commonly used as an environment variable. In this case, it's just used to indicate that this variable is a static constant, a variable whose value doesn't really change and is just meant for reference purposes later in the script. Here's a couple of functions that we don't need to go into too much detail on. But we will go to this start section. Most init-style startup scripts contain start and stop functions, as well as sometimes reload functions, so that you can reload the service if the configuration changes, or alternatively, or in addition, restart function, which simply performs a stop and then a start. It's a start to restart the service. So in the startup function, we process a few SSH configuration and other config values, and then we actually start the process. You can see that this startup sequence is considerably less obvious than the upstart process. Upstart was designed with the intention of making the boot process easier to understand. Hopefully this information on the stopping and starting init-style startup scripts helps you manage your Linux system startup process effectively. Welcome to Lesson 4, Access Control, Accounts, and Rootly Powers. This lesson is about the Linux user account system. You learn how to log in, switch between accounts, create and remove accounts, and manage groups of users. I also discuss sudo, a method of controlling access to privileged commands. I talk about what happens when an account logs into the system and how the administrator can fine-tune login activities. Welcome to Lesson 4.1, Understand the Linux Access Control Model. So, we're going to talk about the traditional access control model, which is really based on early versions developed for Unix. It was a pretty simple model to start out with, and Linux and other Unix-like operating systems haven't changed it a lot because it mostly works. We'll learn at the end about a few alternatives that improve security for the access control model, but in general, most administrators use traditional access control just as back in the day with old-style Unix. First and foremost, objects, which are generally processes and files, all have owners. An owner is a user account on the system. The user might be an interactive user, like an administrator or a developer or another user of the system. It might be a service account, for instance, to run the Apache web server or another daemon on the server. When an object is first created, the creator is the owner. The superuser account, known as the root account, is also the owner of all objects. So in the example I have on the slide, we're searching the etc passwd file for the root account, and this shows the root account in the system. We'll learn how to read the password file and all of its fields in just a little bit. The root account is the only account that can perform certain administrative operations, anything sensitive on the system generally. Let's take a look at an example of file ownership. I'm listing out the passparser.sh script that we learned about in the previous lesson. In this example, we'll learn about the first section where it says RWX, the file permission bits, later. But for now, we're focusing on the owner of the file and the group. In this case, B. Whaley is the owner, and the group Vagrant is the group owner. We can then search for the B. Whaley user account in the etc passwd file. We can see in this example that B. Whaley has an account there. And then we can search for the Vagrant group in the etc group file. etc passwd and etc group are the authoritative sources of user accounts and groups on Linux systems that haven't been configured to use something else. There is also the concept of process ownership. So if we look in the process table, which we'll learn about in the controlling processes lesson in detail, we can search the process table for bash, and we can see that the Vagrant user has launched bash in this example. The very first field says Vagrant. That is the user account that is running the process bash. An owner of a process, Vagrant in the case of this bash example, can change the scheduling priority of the processes as well. Root can change the scheduling priority of any process. We'll learn more about scheduling priorities, but the general idea is that a process has some relevance to the system, and it either needs to be prioritized or deprioritized to make resources for other processes. Owners can send signals to processes, so you might start or stop a process. Only the owner is permitted to do that. Of course, this is a pretty simple example of how access control works. We'll dig in a minute and see examples on the command line. Of course, there are more complex models of access control for more advanced needs. One example is mandatory access control with the SE Linux system. SE Linux was developed by the Department of Defense and gives you very precise, fine-grained controls of different users, processes, and what can access what on the system. SE Linux can be a bit of a pain to troubleshoot. It comes enabled by default on many Linux systems, but a lot of administrators simply disable and turn it off because it ends up causing problems. There's another system known as PAM, the Pluggable Authentication Module system, that provides advanced authentication services. For instance, you could use a PAM module to add two-factor authentication, maybe a biosensor like a fingerprint reader, or a text message that gets sent to your phone when you log in, a form of multi-factor authentication. PAM is also used by default, and you can see all of the configuration in the etc pam.d folder. In addition, there's Kerberos, which provides network-based authentication using very strong cryptography. Kerberos is used by default in the Microsoft Active Directory system, and certainly in any large, complex network, there will be something more complex than just a local file on the system to authenticate users. We won't cover Kerberos and its configuration here, as it's a fairly deeply involved and complex system. Finally, there's access control lists, which we'll learn about in detail in the file system. You can set additional controls rather than just a user or a group owner of a file. You might want to have a specific user in addition to the owner of the file have access, or you might want to give access to several groups. You can do this with access control lists, which are a POSIX compliant access control system. So let's dive in and see some further detail on how the access control system works on the command line. In this lesson, we'll learn how to switch between user accounts on a Linux system. For this example, I'm going to bring up the VirtualBox VM screen. This is the same system that we use with Vagrant when we use Vagrant SSH from the command line, but we're looking at the VirtualBox screen. This is the general Linux login prompt. We see the release of the system, which kernel it's running, the host name followed by the word login. Here I can type my username, B. Whaley, and my password, press enter, and I'm logged into the system. To log out, I can type Control-D, or I can type exit. In addition, there are multiple terminals, known as TTYs, on the system at any time. So now I'm logged into the system. I can use Alt and a function, for instance F2, and I can switch to another terminal. You can have up to 6 terminals by default, but of course it's configurable. There are many other ways to log into the system and switch between accounts. I can use the su command. I use su space dash space some username. In this case, I'll switch to the Vagrant user. It will prompt me for the password, and now it's asking for the Vagrant user's password, which I'll type in now. And now you can see that I'm the Vagrant user. I can use Control-D or exit to switch back to my own user account. I can also use the sudo command, which we'll learn about in detail soon. I can type sudo su minus vagrant, and now it didn't ask me for a password at all. The root account never has to enter a password. So for instance, I can type sudo su dash to become root, and now I can type su dash vagrant just like I did before as the bwhaley user, only this time I'm not prompted for a password. You can see who's logged into the system at a given time by typing w or typing who. Here you can see that the bwhaley user and the Vagrant user are both logged into the system. You can see your current account by typing who am I, all lowercase and one word. It shows me that I am the user account bwhaley. In addition, I can type ID to show my identification. This shows my user ID, my group ID. It also resolves those numbers to names, the groups that I'm in. That's all there is to switching between user accounts. Welcome to Lesson 4.3, where we'll learn to add users and groups to the system. First, let's talk about the etc passwd file. This file is used at the time of login, as well as additional times during the use of the system, to determine what the user ID is of the logged in user, what that user's home directory is, and additional meta information about that user account. We'll look at the password file in detail, but the fields are as follows. The login name, so this is the name you type at the login prompt, a blank password or an X for the password as a placeholder. The actual password is stored in a different file called etc shadow. We have a user ID field, which is a numeric ID identifying the user and is used to map a username to a user account. A group ID field, which identifies what your primary group is. The GCOS information, which is a free-form text field where you can type information about the user, for instance, their real name or their office information or whatever you wanted to put in that field. The password file specifies the user's home directory, which is by default under /home on most Linux distributions. And finally, the login shell. By default, bash is the shell for most Linux systems. There's, of course, CSH and TCSH and ZSH and many other shells. By default, when you add a user account, you'll be adding an account with the bash shell. The group file under /etc/group lists all of the groups on the system and their members. There are several fields in the group file as well. The group's name, a group password placeholder, which is basically unused and not used by any application anymore, a GID number, the group identifier, and then a comma-separated list of all of the members of that group. So let's take a look at some examples. Let's start by adding a user account to the system. The first thing I can do is type which user add to show me where the user add command is in my path, if it's in my path at all. We can see that it's under user sbin user add. There's also an alias add user. I can list these files so we can see what they look like. In this case, the add user command is simply a symbolic link to the user add command. So that means they're exactly the same command. To add a user, it's very simple. I can simply type user add and a username, for instance, live lesson, to add the live lesson user account. At this point, that account exists, but it has no password. I can view the account if I search for live lesson in the etc passwd file. Here we can see the user live lesson. We can see all the fields I discussed in the slide a moment ago. The user account is live lesson. The password placeholder is simply an X. This is not an actual password, of course. We can see the user ID field, which is 1002. we can see the group ID field, which is also 1002. Groups are added with the same name as the user account by default. So when I typed user add live lesson, it created the user account live lesson as well as a group live lesson, which you can see in the etc group file. We can see that the group ID is 1002, which matches to the user account group identifier field. We have a blank field. We can see two colons next to each other indicating that the GCOS information is blank. We have /home/live lesson as the live lesson user's home directory. And at the end, we have /bin/bash, which is that user's shell. So let's take a look at the live lesson and bwhaley account in the etc shadow file, which is where the actual values for the passwords are stored. I can type, using our grep experience, I can type egrep, caret to search at the beginning of the line, and I can use a pipe to say either live lesson or bwhaley, and I specify the file to search in. So we see two username matches here out of the etc shadow file. We see the bwhaley account and the live lesson account. You see the colon, and then you see a hashed value for the password. So this is the bwhaley account's hashed password. We see some additional identifying information. Notice that in this example, the live lesson user's password is simply ! or bang bang. This indicates that the password is currently not set. There's no password for the live lesson user. So we need to go ahead and set it. We can type passwd live lesson, and I can give it some password, anything I want. I typed a very simple one, so the system warned me that it's based on a dictionary word. It's not a very complex password. And now if I search for live lesson again in etc shadow, we can see that there's now a password value set. So this user account can now log into the system via one of the methods we just discussed and use the password to log in. So now let's back as our vagrant user account. We are no longer root. I've logged out with Control-D. I can check out the live lesson account directory. cd/home. I can ls to see all of the user accounts. In this case, there are only three: bwhaley, live lesson, and vagrant. And if I try to switch to the live lesson directory, it says permission denied, which is exactly what you want, of course. You wouldn't want one user account to easily access the files of another user account. We can see that if we do a long listing, ls-l, of the directory, live lesson directory. In this case, D gives you a directory listing. We can see that the directory is owned by the user live lesson and the group live lesson. So how could I see this directory if I was an administrator and I really needed to get in and look at it? Well, I can type sudo su- as we learned how to switch between users, and I can just go ahead and change to that user account as the root account. I can switch into that user's directory, and I can explore. The root account has global permissions across the system. It can see any file, make any changes that it needs to. The root account needs to be very carefully protected as a result. We can also go ahead and add a group account. I can type group add admins. Now if I search for the admins group in the etc group file, I can see that it exists, but notice at the end there is no users currently in this group. So I need to go ahead and add some users. I can do that with the vi-gr command. This stands for vi group, or we use the vi editor, which we learned about previously, to edit the group file. So I can see all of the different groups on the system here. And if I go to the end, I used Shift-G and VI to go to the end of the file, and I can see the admins group that we just added. We can see that it has a group ID of 1003. And I can go ahead and add some users to it. I might add vagrant and live lesson and bwhaley. Type escape, and I'll quit with :WQ to save the group file. Okay, so now the group file has been modified. I did that, all that work as the root account, so I'm going to log out of the root account back to my vagrant account. If I type ID, it shows me, the vagrant user, in the Vagrant group, as well as the wheel group, which is added automatically by default as a privileged group. So notice that we just edited the group file and we added the Vagrant user to the admin's group, but we don't see that in our group list. That's because changes to groups do not take effect until you next log into the system. So I'm going to log out using Control-D. Now I'm back on my own laptop system. I'm going to go ahead and use SSH, Vagrant SSH, to log back into my CentOS box. Now I'm logged in, and if I type the ID command, we can see that I have the admins group added, as expected. Just as easy to delete a group, I'll do it as the Vagrant account using the sudo command. We can use sudo to perform an action as root, user del live lesson. Now the live lesson group has been removed. However, if I list the home directory, I can see that the files for live lesson have not been removed. I can search for the live lesson user in etc passwd. It's gone, but the directory still exists. So by default, the user del command does not delete the user's directory in case there was any valuable files in there. That's all there is to adding and removing users on a Linux system. Next up, we'll learn how to elevate privileges using the sudo command. Let's go into just a really quick history since it's applicable to this lesson. Sudo, in concept, was first conceived in 1980 in Buffalo, New York. It was enhanced and maintained at CU Boulder by Garth Snyder and Trent Hine, who are additional authors of the Linux System Administration Handbook on which this lesson content is based. It is now maintained by Todd Miller, who's a professional developer at Quest Software. This is a famous comic next to it by Randall Munroe of XKCD fame. This is one of his more famous comics. It's just kind of funny because it indicates exactly what the sudo command does. It gives you privileges and powers you otherwise might not have. So you pronounce sudo as sudo. It stands for super user do. There's some debate over what it actually stands for. This is the version that I like the best. It gives you very fine-grained, granular control over what privileged commands a user may run. You can control sudo commands on a user, a group, an individual command, or a host basis, so you could allow a user to have specific sudo access on a set of hosts or set of sudo access to just a certain set of commands. Maybe I want to give one user account access just to edit user's passwords, so he can have sudo to the passwd command, but he can't do other things, like he couldn't add a new user. It gives you really clear auditing of who ran which command on a privileged system. And this becomes important, certainly in regulated or security-sensitive environments. You'll often set up logging and monitor the sudo audit log to make sure that users are using their sudo permissions appropriately. When you type the sudo command, it gives you a ticket that lets you use sudo for an additional 5 minutes without typing your password. By default, sudo expects a password when you type it the first time. The sudoers file is what configures the sudo usage. Generally lives in /etc/sudoers. Let's look at some command line examples. We're logged into the CentOS system as the Vagrant user account. I'm going to simply use sudo to switch to the bwhaley user account. Now, let's see what I can and can't do as bwhaley right now. Let's take a look at the var log directory. This is generally a very privileged directory. Only system administrators can have access to it. So we can see, for instance, if we look at var log messages file, this file is owned by root, and the group is also root. All users don't have any permissions to look at this file. And if I try to do so with the less command, I get permission denied. So I might want to use sudo to do that. So if I type sudo, I can use the bang bang shortcut to say run the previous command again, sudo bang bang. It prompts me for my password, which I'll type in here. And it tells me bwhaley is not in the sudoers file. This incident will be reported. So that sounds very ominous. It just means that I haven't been added, the bwhaley user account hasn't been added to sudoers yet. So let's go ahead and add bwhaley to sudoers. So I'm logging out of the bwhaley account and I'm back as the Vagrant user now, which you can see on the shell prompt, I can type sudo and vi sudo, just like we saw with the vigr command. A similar command exists for the password file. You can type vipw. Vi sudo will edit the sudoers file with vi. So we only have a single line in this sudoers file. Vagrant makes sure of that. So in this example, the first line here, the Vagrant user has all access to all commands on all hosts with no password. So this is very open, wide open permission. I can add permissions for the bwhaley user as well, just by adding a new line. Or even better, I can use a yank to copy the previous line. And I can change the Vagrant user to the bwhaley user with cw and vi. And let's just make a quick change. I don't want the bwhaley user account to just have full access to sudo without typing a password. So I delete this part of it. And now the bwhaley user is able to run all commands with sudo, run any privilege command, but a password is required. So I'll save that. Now let's go test it out. Switch back over to the bwhaley user account. I can now try to type my sudo less var log messages command again. Type in the password, since I left off the no password flag in the file. And now we can see that it went ahead and let me run the command. So a file that I couldn't previously view, I can now view using the sudo command. The ticket file, sudo now knows that I've typed my password in once, and it's really annoying to run many commands typing sudo repeatedly. So if I try to look at the file again, I didn't have to type my password in this time. And it knows that because there's a ticket. If I look in var db sudo, this is where tickets are stored. There's a bwhaley user. We can see that there's this file 0 and 1. This is how it knows that I've been granted permission to run sudo, and I don't have to be prompted. So that's a very quick introduction to using sudo. In this sublesson, we'll learn how to maintain the home directory and the automatic shell startup files that are processed when you log into the system. Let's dive right into some examples. I'm logged into my CentOS box as the Vagrant user account. First and foremost, you can see the tilde character at the end of the command line right here that I've highlighted. The tilde character is just shorthand for the home directory. If I type pwd to print working directory, it shows me that I'm at home Vagrant. I can type cd/temp to switch to the temp directory, but then I can type cd tilde to switch back to my home directory. I will do a long listing of the home directory with the -a flag to indicate that I'd also like to view hidden files. Those are those files that start with a dot. .bash star. So I want to see all the files that start with .bash. So there's a few of them here. We have the bash history file. So we learned before that you can type the up arrow, like I'm doing now, to scroll between previous commands that you've typed. That command history is stored in the .bash history file in your home directory. So if you ever wanted to clear it out, you could type history -c, and it clears out the bash history. Now if I type the up arrow, nothing happens. .bash logout is where you can put commands that you want to run when you log out of the system. The .bash profile and the .bashrc are just a little bit subtly different. .bashrc is executed by interactive shells whenever you're typing bash on an existing shell. For instance, I'm logged in right now as the Vagrant user. I have a shell. I can type bash again, and I have a new shell. I could keep doing this all day long. And so now I have this sort of Inception-like nested shell situation. In order to log out of the shell, I type Control-D. But notice it doesn't log me out of the system back to my laptop. It just logs me out to the prior shell. I type it again, and now I'm back at my original shell. So those are known as interactive shells, and those would read the .bashrc file. The .bash profile, which I have highlighted now, This file is for personal settings and variables and things that get executed whenever you use a remote login to the system. For instance, if I use SSH to log into the system, the .bash profile is executed. So we can take a look at these and see what's in them. If I cat out and print to the screen the .bash rc file, it does a few things. First, it checks if a file called a global file in /etc called bashrc exists, and if it does, it reads it. This dot syntax is simply a shortcut in bash for reading that file's contents into the current shell. I haven't defined anything user-specific, but if I needed to, I could put it here. We can also check out the .bash profile. Really similar. The only thing that's added is that we're modifying our path to add our own ~bin directory. So this would say, add my home directory /bin to my path. So any default commands I needed to run, I wouldn't have to prefix them with ~bin. So let's add something. Let's add an alias to our bash shell. So I'll just edit the .bash profile with vi, and I'll type in a new alias command. So I'll say alias hello equals echo hello there. So notice we're using single quotes and double quotes to make sure that our shell is going to interpret this properly. Now there's one of two ways that I can reread the .bash profile. By default, hello isn't going to do anything for me right now. I haven't reread the file yet, so I can write the dot character like we just learned, which reads that file's contents into my current shell. I could type dot space .bash profile, or alternatively, I could type, rather than the dot, I could type source. Those are equivalent. And now if I type hello, we can see that it's just an alias to echo hello there to the screen. So that's a quick introduction to how to edit bash startup files. It's very similar for many shells. These bash profile and bashrc files are important to know for the bash shell. Welcome to Lesson 5, Controlling Processes. This lesson helps solidify the previous lessons. You learn what a process is conceptually from the kernel's perspective. You learn the life cycle of a process from the moment it starts through execution and termination. I cover the tools used to interact with processes through signals and additional tools to learn how a process is behaving. We dig into the /proc file system, which exposes the internals of processes. I cover the powerful strace command that exposes system calls, allowing the administrator to debug and troubleshoot processes at a low level. Finally, you learn how to use the cron daemon to execute processes on a scheduled basis. Welcome to Lesson 5.1, where we will review the components of a process. So on Linux, a process really just represents a running program. Its resources, the memory and CPU and the input-output it needs, for instance, to and from storage, local disk, or to and from the network, are all managed by the kernel. So a process is code loaded from disk or from some storage into memory. And in memory, a process consists of a couple separate components. First, references and data structures used by the kernel. The kernel needs to manage all of the processes. One of the kernel's main jobs is to make sure that each process is getting some of the CPU time and that processes are handled appropriately. So it needs to have a map of how a process is executing. In addition, there's the address space used by that process itself. For instance, for its stack, for its heap space, for all of the data, its variables and such. For the code, the actual source code used has got to be loaded up into memory. The metadata maintained by the kernel in memory is composed of a few distinct phases as well. It has the address map, so the kernel knows where an executing process's stack is. It knows where the data and text spaces are, so the kernel is kind of keeping track of all of that. It knows the current state of the process. We'll cover each of the existing states, but for instance, it knows if the process is running or not. It knows the execution priority of the process. So is my shell prioritized above a database daemon, for instance, or does the NTP daemon get time? It knows where each process's priority is with relation to all the other processes in the system. It has information about the process's file usage and network usage. Anytime a process is running, it needs to open some files on disk. It needs to communicate to and from the network, open network sockets, connections to other systems via some port. The kernel maintains a map of what files and network information that process is using. And of course, the owner of a process, which we just learned about, the kernel maintains a list of what user or what account started a process. Each process has a process ID and a user ID associated with it. So a process ID is a reference number associated with a process. We call it a PID. When you look in the PS command, which we'll review in detail, it shows you the process list, you'll see the very first field is the process ID, the PID. The fork system call is important to understand about processes, and we'll see a little bit more about that in a minute. A new process doesn't just get created out of thin air. It starts by being a clone of some existing process. So an existing process is cloned and then remapped by the kernel and becomes a new process. The very first process is init, and an original process, when the process that is cloned, is called the parent. So there's a parent and a child relationship. The parent PID is then, of course, the ID of the parent process. So there's the parent process ID, the PPID, and then the child process ID, also just the PID. The user ID of a child process is the same as the process of its parent. So think about when you start a process with bash, for instance, you have your bash shell open and you type the vim command. Bash makes a copy or a clone of itself using the fork system call and then starts up the vim process with the same user ID. In lesson 5.2, we'll understand the life cycle of a process. So we talked about fork just a minute ago and how it's a system call that clones a process. So the moment that the process is cloned, the memory and the code of the clone is identical to that of its parent. The new process, the forked process, receives a return code of 0. So it checks its return code when making the system call, and if it receives return code 0, then it knows I'm the child process. And this is really just this is information necessary for a programmer who's writing software that clones out new processes, forks new processes. The original process, the parent, receives the PID, the PID, of the new process as its return code. And this way, the parent process can keep track of all of the other processes that it's cloned because it knows what their process ID is through the return code. And then for the child process to start execution of a new program, it calls the exec system call. There are a number of process states, and the kernel maintains this map of process states. The first process state is that of runnable. A process is ready to be executed. In addition, there's sleeping, where a process is waiting for some resource. So it doesn't have anything to do. It's waiting for disk, or it's waiting to load something out of memory, or it's waiting to receive data from the network. CPUs are, of course, very, very fast. And so the time it takes to execute code is extremely fast in comparison to the time it takes to retrieve something from memory or even to go all the way out to disk. That takes a really long time. So during that time, the kernel doesn't want to waste cycles loading that process, having it do nothing. So it puts it in the sleeping state. There's a process state known as zombie, and this is a strange state where a child process has terminated execution. It's quit for whatever reason. And the parent process hasn't yet reclaimed that process. It hasn't reaped the child process. So that's known as a zombie state. It doesn't happen very frequently. It usually indicates some kind of a problem. And then finally there's stopped, which is a state known as administratively forbidden to run. It means that the administrator or the kernel has stopped execution of that process for some reason. Maybe just for intervention or for whatever reason that process shouldn't be running. So let's take a look at what this might look like on the command line. I'm logged into my CentOS box here. First thing, let's look at the process tree using the pstree command -h. So here we can see the very first process, the parent of all processes, init. init has cloned itself into a number of other processes, and you can see that in this tree hierarchy. Init is the master daemon, and it spins up all other processes. So we can kind of scroll our way down here, and we can see that this tree where SSHD is. We see a number of SSHD processes, followed by bash, followed by pstree, the very command that I just ran. So let's explore this in a little more detail. Bash has an environment variable, a built-in environment variable called bash PID. This is the process ID of the current bash shell, my logged-in shell that I'm using right now. So I can use the ps command to check out this bash PID, and I can see what its parent PID is, right? The parent process ID would be the parent process of this current bash PID. So the parent process of my current bash shell is 1892. And I can keep following this tree all the way back. So now I'll repeat the same command, only I'm substituting my parent processes, which we just discovered. And we should be able to trace this back all the way to init. So at this point we're right about here. We're following each process back up to its parent. So now I'll look at 1891 and 1889. I'm now looking at SSHD, and that cloned. These are all just process IDs in the process table. And so we finally got to 1. 1 is, of course, the process ID that's always assigned to init. And so in this way, we started here with our bash shell and traced each parent process up the tree back to the init daemon. That's all for understanding what the life cycle of a process is all about. Welcome to sublesson 5.3, sending signals to processes. So a signal is an interrupt request for a process. It's a means to communicate between processes. Signals are sent by various entities on the system. It's, for instance, sent by terminals to take some action. For instance, maybe I'm logging out of my terminal, and a signal needs to be sent to kill the current processes running under my user. It can be sent administratively by the system admin. I can tell a process, it's time for you to stop, or I'm going to terminate you, or I'm going to interrupt you in some other way. The kernel sends signals for a number of different reasons. It might send a signal to intervene on a process's behalf. If an instance has data waiting for it, it might tell the process you have data waiting. Or it might notify it for a different reason. Processes define what are known as handler routines when a signal is sent. This is known as catching a signal. So if the kernel sends a signal to a process, the process needs to plan for that signal. It needs to know this might happen, so it needs to catch that signal. If there's not a handler routine present, the kernel might take some action by default. Programs can also request that most signals, but not all signals, can be blocked or ignored. If it doesn't care about being interrupted, or if it wants to ignore a stop request, it can signal the kernel that it wishes to not do anything. There's a really large number of signals, and many of them are just unused. But here's some of the most important ones here in this table. We'll quickly go through them. The HUP, or the hang-up signal. This means that the controlling terminal has exited, like I logged out of my shell account. The interrupt signal is something like a Control-C. So if there's some process running and you want it to stop, you can say Control-C, and that will interrupt it. This is the type of signal that a process might catch and ignore in some cases. You can send signal 9, which is a really mean kind of kill, terminate the process immediately. This signal can't be caught by processes. So if you send a kill -9, that's sending a signal to a process, it will not be able to stop receiving that. There's also a term, which is kind of a nicer version of the kill -9 signal. And there's a segmentation fault, which you'll sometimes see. This almost always indicates some bug or problem in the running process. So let's explore on the command line a little bit. Here I'm logged into my CentOS system. Let's experiment with the term signal first of all. In an earlier lesson, we looked at this Gettysburg Address file when we were learning about VI and Vim. So I can use the Control-Z command to stop that process. Now it's you can see that it's running. If I type jobs, I can see that that process is stopped in the background of my shell. And we learned before that I could use FG, foreground, at this point to bring that back up to the front. I can also use the pgrep command to search for this process. I can use pgrep -lf, which will search the process tree for the vim command, and I can see that process 2113 is running vim Gettysburg Address, which is exactly what the information I requested. I can kill it at this point. I could type kill 2113. So now it's dead. If I try to bring it back to the foreground with the FG command, you can see it it's kind of mad. It says caught deadly signal term finished. So vim caught the signal and then it quit. Let's view a little more aggressive version of this signal. I will go ahead and vim the Gettysburg Address again, and I'll use Control-Z to get back to my shell. I'll use pgrep. Notice that I'm using Control-R, the case-insensitive reverse history search. This is a really nice shortcut for me to get back to the pgrep command quickly. I can type Enter, and now it's running with process ID 2115. I can type kill -9. This is a shortcut for which signal I want to send from that signal table we saw on the slide. I can use kill -9 on that process ID. Now if I type jobs, it just says killed. And if I type foreground, there's no job running. That process is dead. So notice the difference between just killing the process, where it caught the signal and finished on its own, versus kill -9, where it didn't have a chance to catch the signal. It was just killed administratively by the kernel. So let's look at a hup, which is like a reload command. Syslog is a good example for that. We'll learn more about syslog in a later lesson. For now, it's just good enough to know that syslog is a logging daemon. It's running on the system. I can type pgrep -lf syslog. The rsyslog daemon running with process ID 1104. So I want to see what happens when I send this process a hup signal. So I'm going to look at the system log file, which we'll learn more in detail about later. Just going to tail it and put it in the background so it's just sort of running. This shows me things that are happening on the system. It's the system log. I already know that process ID 1104 is rsyslog, and what I want to do is send it a hang-up signal, a hup. I want it to reboot, reload itself. So I can type sudo kill-hup, and I can give it that process ID 1104. And remember, I have the syslog varlog messages. I'm looking at that in the background. That's what this tail -f is it's running, but it's in the background. So I killed rsyslog, and it logged. It made a log statement, and it says rsyslog was hupped. So basically that means it's reloading itself. Hup is often used to reload configuration. If you edited the configuration of some running daemon, like you changed your syslog configuration, you could send it a hup signal and it will reload the configuration. So I'll use foreground and I'll cancel out my tail of the varlog messages. So now it's not running in the background anymore. This was just a few examples of how processes interact with signals. In this sublesson, 5.4, we'll learn to use PS and top to look at, inspect, and monitor processes. These are very commonly used administrator commands, one of the first tools in your tool belt that you can pull out when you need to log in and start using a Linux system. So I'm logged into my CentOS box with the Vagrant user. First things first, I'll run the PS command. You can see that there are 3 processes running. By default, PS just shows the processes running under my current user account. So there's a bash process, there's a PS process. So I can use, let's just add a little CPU time. You can see there's basically no time being used so far. Bash shell doesn't take up too much CPU time on its own. So let's add a little time so we can just kind of see that increment. So I'll just use a loop for that. So the yes command, its only purpose in life is to echo yes to the terminal. You might wonder why that's useful. It is occasionally useful, in fact, as it has a nice exit code. usable for scripts. In any case, I'm just letting it run here for a second to accumulate some CPU time, and I'll use Control-C to send it kill signal to stop the process. And now I'll just type PS again, and we can see that the bash process at this point has accumulated a little CPU time, 16 seconds. So that means that the bash process was actively being executed by the processor for 16 seconds. Just kind of a little side trip there for you. Now let's check out another example. I'll open up the Gettysburg Address again with Vim, and I'll use Control-Z to get back to my shell and put it in the background. We'll just type PS and look at the table again. You can see that we have Vim running, and PS shows us that it has process ID 2148. So I'll go ahead and close out of it now. Let's look at something a little more interesting. The flags I like to use, and there are a number of variants of what flags you can use. I'm using the BSD style syntax. PS is steeped in Unix history, so in this case I'm using BSD. Some people like to use an alternative -EF flags, which accomplishes basically the same thing. I'm going to go ahead with AUXW, and I'm going to pipe the output of this to less so that we get it one page at a time. And let's just kind of take a look at the command here. So we have a number of fields. We show all the users that are running the processes. We show their process ID, the PID that we just learned about. We show what percentage of the CPU and memory that the process is using. So that's really important. Sometimes when you need to debug or diagnose a problem, you might see that a given process is using a lot of CPU or memory. And that could be expected or unexpected. It just tells you information. It shows you the virtual size and the resident size of memory that the process is using. It shows you what terminal it's running on, and just some additional information. Interestingly, of course, it shows you the command that's running. So this very first command in the process table is init, which has process ID 1. It's taking up some space in memory. It shows you what time it started. All of these processes that show a square bracket on either side are kernel processes. So the kernel is automatically managing them. They are represented here virtually. We can pretty much safely ignore them. I'm going to go ahead and filter them out for now, in fact. And we can do that with our handy grep. And so now we've filtered out all of the kernel processes, and all we see are the actual running processes on the system. Back towards the bottom of the list, we can see a few differences. Most of the commands are running as root, but we can see also the commands that are running as the user vagrant. We can see the SSH process. We can see that SSH cloned itself and started a bash shell when I first logged into the system. We can show that there's another bash process running. We can even see our running PS and our less command in the output here. Right? That when we run PS, AUXW, and we pipe it to less, we actually, those should show up in the process table because they're actively running processes. So that's why we see them here. Next up, let's check out the top command. So first, I can just run top. And let's run through some of what we're seeing in this list of information. There's a lot of really good details about what the system is doing in top. Up here in the left, it shows me how long the system has been up, 3 hours. It shows me that there's one user logged in. It shows me the load average, and this is showing me 1, 5, and 15-minute intervals, I believe. So the load is the number of processes waiting to run on the system's run queue. And so this is a subtly challenging number to interpret. A system that's really bored and not very busy doing things will have a very low load. For instance, this system is just a virtual machine running on my laptop. It's not really doing much. It has a very low load of 0. On a busy system, say a system that is running a database or handling a lot of web connections or some busy server doing things, this load number will be really high. Really, a safe load number is anything that is below the number of CPUs on the system. So for instance, if you have a 4-core system, 4 CPUs on your server, a load average of 4 or below means that the CPU has some idle capacity. It means it has some room to grow. If it has a load of higher than 4, it's overwhelmed. Every processor on the system is busy, is fully pegged, and there are some processes waiting to run that can't run because the CPUs are busy servicing something else. So you want to keep a really close eye. This is a good one to measure and monitor. We see the total number of tasks or running processes, basically, 86 of them total, 1 running, 85 sleeping, meaning either they don't have anything to do or they're waiting on the disk or the network or something else. We see CPUs here. If I type the number 1 on my keyboard, notice that it changes from CPU 0, CPU S, CPU 0. What that's indicating is if I had more than one CPU on this virtual machine, I would show both of them. I would show CPU 0, and right below this would be CPU 1. If I hit 1 again and it shows me CPU S, that's a cumulative number. That's how busy the system is across all of the CPUs. Then we divide this next section into kind of several percentages. We have user, so this is user processes taking up CPU time. And then we have system percentages. So this would be the kernel taking up CPU time. And you'll often see a busy system marking some of its time in user space and some of its time in system space. This is very normal. We see this is not very important one necessarily. This is percentage nice. This is processes that are niced or are deprioritized or prioritized by the kernel in some way. We see idle. This is taking up most of the CPU on my system right now because it's just not doing very much. So most of the CPU is idle. If you see idle on your system, it means one of a few things. It might mean that the system is in fact not doing very much, or it might mean that you have one processor currently being fully utilized and another processor not being utilized at all because the system's not multi-threading very well. So this can be an interesting percentage to look at. This is also an important one. The WA here stands for wait. So this is CPU wait time. It means that some processes are waiting for I/O. They're waiting for the disk or they're waiting for network traffic. In some case, there's a process that wants to run, but it's got to wait for something that's really slower. And if this number is really high, it often indicates that you're bottlenecked on disk somehow. So those are the most important fields out of this list. Finally, there's the memory. So this is telling you what's going on with the memory on your system. It's telling you how much you have total, how much you have used, and how much you have free. And then swap space is virtual memory available to the system. It's generally a kind of a rule of thumb is it's double the amount of memory that your system has. In some cases, it might be 0. And then below that, we have an always changing list of commands. So these are the same commands we see in the process table when we run PS, but this is showing us a little more detail about what process, it's sorted by default by what process is using the most CPU. And you can change which column it's sorted by if you look at the top help. Look at the man pages for top or type the H key to see some quick help. In sublesson 5.5, we will browse the /proc file system. /proc is a virtual or a pseudo file system created by the kernel that represents the current processes on the system. It's a way for administrators and the kernel to keep track of running processes. So I've cleared the screen with Control-L so we can start fresh, and we'll start by jumping right into /proc. We'll list the files in this directory. First, we see on the left a whole lot of numbers. And so these numbers they all map to the process IDs. When we looked at the PS command and we looked at all the processes, those all had process IDs. They're mapped here in this list. We also see a bunch of other information that the system is telling us. For instance, we see the mem info. So you can go ahead and print these files to the screen. I'm going to use cat mem info. And this prints a whole lot of kernel memory information about how much memory is available to the system and what it's being used by and all sorts of deep technical details about the memory usage. I can do a similar thing for the CPU info command. So if I had more than one processor, I'd see multiple processors. In this case, my virtual machine has only one, so it's identified by processor 0. It tells me it's an Intel processor. It tells me that it's a 1.7 gigahertz Intel chip. So it gives you all sorts of details about what kind of CPU it is, actually. There's some information in the /proc file system, but sometimes you also want details about a running process. So let's check out one. For instance, let's look at, we learned about the bash PID variable, which says the process ID of my current bash shell. We should have a directory here for this process ID, 2040. So now I'm in /proc/2040. And if I list this, I've got a whole bunch of files. All of the details and all the contents of the files in this directory are specific to my bash shell. I can type cat limits, and it shows me the limits applied to my bash shell. So it says I have unlimited CPU time. I can have unlimited max file size. The system administrator might want to limit my file size or my CPU time, and that would be reflected here. Maximum number of files that I can have open is soft limit of 1024, and a hard limit, meaning don't ever exceed this limit, of 4096. So if I tried to open more than 4096 files, it would fail. The kernel wouldn't allow that. This is just telling me what my limits are. I can cat the command line file, and we can see I'm running home vagrant nudir bash. So I'm running a bash. This is the bash executable that I had copied into my nudir directory in an earlier example. I can cat the status command, and this shows me all sorts of information about the status of my current process. It shows me that the process is sleeping. It shows me the process's ID, the PID is 2040, which we already knew. It shows me my parent PID, which we also already knew because earlier we used the ps tree command and followed the process tree back up, so we figured out the parent process each step of the way at that time. It shows me the user ID, so that's the user ID of the current process. If I type ID on the command line, my ID as the vagrant user is 500. And all sorts of other technical details about this shell. There's some also system-wide settings under /proc that you can use to customize how the kernel is behaving. It's a way to configure and interface with the kernel. Now, any changes you make under /proc don't persist. So if the system is rebooted, anything under /proc starts over from scratch. It's not saved. So you don't make setting changes that you need to make permanently. You don't make them in /proc, but it's a good way to test something or to make a change without rebooting the system. One good example of settings that are configured in this directory is under /proc sys net IPv4. This is showing me my TCP IP settings for this system. And there's a whole bunch of files in here that I can configure the TCP stack to my heart's content, or UDP settings, a number of various TCP IP settings. We don't need to dive into these too much because we'll cover them in detail in the TCP IP lesson later. So hopefully this sheds some light on the process table and what processes look like from the system administrator tool perspective. In sublesson 5.6, we will learn to trace system calls and signals with the strace command. strace is a very powerful command that shows you at the kernel system call level, or just the general system call level, what a process is attempting to do. It can be a great tool for diagnosing problems. So logged into my CentOS box here, I can start by, let's just pick an example command like ls-l. We know already that this gives me the list of files in long format of the current directory. So what if we strace it? strace ls-l. Printed out a lot of information that looks kind of pretty hard to read, but it's not so hard if you just spend a minute looking at it. So I'm scrolling up to get to the beginning of the output. First things first, we see execve. So this is a system call that says open up the /bin/ls process. Here's the arguments, -l. So it's basically just starting the process. It's creating some memory for it. It's loading up some shared library files. So these are some dependencies that the ls command has, some library dependencies. Can pretty safely be ignored. Scroll down a bit. It's going through all of the content. We can see here that the open system call is inspecting the /proc file system, which we just learned about. So it's just learning about file system information. It's reading the locale archive file, which I'm not sure the details of that, but based on the name, it sounds like it has something to do with printing things out in the right language or the right format, possibly. Yeah, here it's found out that my preferred language is US English in Unicode format. It's finding all sorts of details and dependencies. And now, here's the real fun bits of it. It's looking at all of the files on the system and using a dir system call to get details about it. So this is just all the system calls that the ls command uses when it lists the files on the system at a very low level. So it's finding out, for instance, the time of a given file. And then we can see here the time that a given file was last accessed. And here we can see that it's actually writing content to the screen. So when we run -ls-l, we see a lot of details that look just like this. And so this is the actual printing that out to the screen. So it gives us low-level diagnostics as to what's happening with the command. Let's see another example. This time we'll do a network-based example. Let's try running strace against a ping command. So when we run it against the network, we have to give it a special flag, -e trace equals network. All of this information is, of course, available in the strace man pages. Now I'll just use pinggoogle.com as an example. And the first thing we notice is, oh, operation not permitted. Network traces, network captures, or getting details about this are not available as a regular user, so we need to use sudo. I'll use our favorite shortcut, sudo bang bang, to run the previous command with sudo prefixed. Now we have all sorts of other details. We can kind of see it's still going on. I'm going to use Control-C to cancel it out. And we'll just take a look at what happened here. So I'm going to scroll up to where I ran sudo strace on pinggoogle.com. Ran through a few things. It opened up a socket. It tried connecting to a few things, sent some data. And here we see the print command. We see that it printed out to the screen pinggoogle.com, so it's kind of telling us what it's doing. And what we see here is really the details of it. We see it's actually sending some data. That's what's happening here. Sending data to the socket it opened before, and then receiving a reply back. And since the ping command is really just an ongoing echo reply, right? If we run pinggoogle.com, we can kind of see it just repeats itself, and it shows us all sorts of network information about what happened. We can see in the strace output, we can see the same thing. We can see that it sent some data, and then it received some data. And then it prints out to the screen the same thing that we see below when I run it without strace. And we send some data, and we receive some data. So it's just showing us the low-level network socket details of what the ping command is doing under the hood. Finally, let's just kind of check out one more example. We can actually use strace to connect to a running process. A process that's already running we can attach to and look at the system calls that are going on, and then we can cancel it. So we could, for instance, start ping and put it in the background. So let's just pinggoogle.com. We don't want to get any output. We don't want to see that 64 bytes received from. So we're going to redirect the output using the redirect operator, which we learned about before. We're going to put it out to /dev/null, and we're going to run this process in the background. So right now this process is running. We can see it running if we type jobs. We can see that we don't see any output because it's redirecting to the null file descriptor. Now we can run strace on that running command. So we'll use some of our bash knowledge, sudo strace, and we use the -p flag, indicating that we want to attach to a running process. Normally it takes a process ID, like 6624, we could put right here. But if we didn't know the process ID, we could use some more of our bash knowledge. We could use the pgrep command to search for ping. And this is saying take the output from this command and place it as the input to this -p. So it's going to resolve to the same thing, 6624. And so we see it doing exactly that. We see some send and receive. We see the same thing we were doing before, only it's attaching to a process that was already running. So I'll go ahead and kill it now. And that's the strace command. Pull it out of your tool belt as soon as you need to do some low-level diagnostics about what a process is doing. Sometimes it can shed some light on what's going wrong on the system. In this sublesson, we'll learn how to use the cron daemon to schedule commands to run on an automatic basis. Cron is a system daemon. It's running all the time and generally starts at system boot. It executes commands on a scheduled basis in the background. The term cron jobs is used to refer to a scheduled command. It's known as a job or a cron job. It's created using a specific syntax in a file known as a crontab file. There's a command called the crontab command that lets you edit commands in the crontabs. And the cron daemon itself, known as cron d, reloads itself anytime it sees a crontab file change. So you don't have to manage the cron d daemon very much. You really just have to manage your own cron jobs in your own cron tabs. This is what the format of a cron tab looks like. We have the schedule first, so it's minute, hour, day of the month of the year, and then weekday, and those are generally given as numeric values in the ranges you see in the table, and then followed by the command. So it's basically, the idea is run a command at a given day, time, week. Here's an example. So this very first command on 10:31 at midnight, so October 31st, it says, boo, it's Halloween. Echo that to the terminal. It's just a very simple example. You could schedule a command to run at midnight on Halloween. Or here's another example. Here's a reminder. Mail yourself. Today's a work day. In the message in the second column here, the second row here. Every day of the week, Monday through Friday, that would be 1 through 5. At 7:30 in the morning, mail yourself a notification. Or here's another example, a little more involved. We can run the command uptime, which shows you how long the system has been up, as well as the system's current load. Run that command every 15 minutes and send that file to a file called uptimes in the owner of the crontab's home directory. So let's kind of break that down. The first column says */15 means run this command every 15 minutes, every day, every week, every month, every day of the week. It says run the command uptime and send that output or append that output to a file in the home directory, that's what the tilde is for, /uptime. So this would just be a growing list of the uptime command indefinitely every 15 minutes. Cron jobs have a number of different uses. You could use them to schedule backups. I could, for instance, run a backup every day or every hour or whatever scheduled basis I needed to take a backup of some software or some data I had on my system that was changing. I could send an email notification. I could run a script that searched to make sure the system was behaving or healthy, and I could have it send me an email if something got out of whack. I can use it for system monitoring. I can use it to clean up the file system. For instance, it's commonly used to rotate log files. Log files are always growing. Log files are when a command is running and sending output to a log, we want to have details about what the process is doing. The log is always growing, but eventually the log could fill up the disk. So you want to make sure that doesn't happen. So you rotate it and you delete old log files. You could use cron for that, and that's a very common purpose for it. You can use cron to restart services. If you had some service you knew needed to be restarted once a day, you could do that with cron. Or you could run some maintenance activity. Crons are very widely used and have all sorts of different applications. So let's jump into some command line examples of cron scripts. Okay, so first things first, we will look in the process list using our favorite command ps, and we'll search for cron and see if we have a cron daemon running. We do, and it's called cron d. Notice we also see our grep output. Grep was running at the time we executed ps, so it was caught in the ps output. In any case, we have cron d, so we can see that it's there running. Let's switch to the /etc directory, which is a common location for configuration files. And we'll look at all the cron-related files. So we have a few different ones here. Most importantly, we have etc crontab. So let's look at the crontab file. This is just general configuration information for the cron daemon. It shows you the same details that I just explained. It shows you that the first field is the minute, the second field is the hour, the day of the month, the week, the day of the week, and then the command that needs to be executed. Of course, this is an actual configuration. It's prefixed here by a hash value, so you know that it's actually a comment. We can look at all of the cron tabs on the system by looking at var spool cron. This is where cron tabs are kept. So here there's one cron tab for the vagrant user. So let's use cron tab, the cron tab command, which we can use to edit the cron. -e means edit. So here we have already in place the existing example that I had showed in the slide to run the uptime command every 15 minutes and append it to the uptimes. So if we go and take a look at uptimes, we can see it's running every 15 minutes. And since the uptime command prints a timestamp at the time it runs, we can see that it runs at least within a second of every 15 minutes. So sometimes cron takes a second to load and do certain things, but we can see that it's really running pretty frequently. And we do see some gaps in here. For instance, we see it ran at 1945 and then not again until 2300. Likely this means the system was turned off, or maybe my laptop was shut, or for whatever reason it wasn't running. What this indicates is that cron doesn't run when the system is not running, which of course makes sense. It's not going to go back and catch up with any scheduled tasks that it missed. We can also use the cron tab command to edit another user's cron. We can say cron tab -e, and then I could specify a user, B. Whaley. Notice that I'm using sudo in this command. It wouldn't make sense for me to be able to edit the B. Whaley user's cron jobs. So I have to be root in order to do that. So now I'm editing B. Whaley's cron, which I don't want to make any changes to right now. All cron jobs log their details to var log cron. So we'll take a look at that file quickly. We can kind of just see the only cron job that runs regularly is these guys here. This uptime command is running every 15 minutes as we expected. There's some other cron-related information in the etc directory. Remember when we ran ls cron star, we saw some other directories in here. We see cron.daily. These are default cron tabs. You can just put a script in here and it'll run once a day. Cron will just run it once a day for you. Or this one will run every hourly. The monthly and weekly directories are empty. So if I wanted to, I could change to cron.weekly and I could put a file in this directory and it would run every week automatically. So that's a pretty quick and dirty introduction to using cron to schedule system commands. Welcome to Lesson 6, the file system. We start by understanding what the file system is and how it's organized. We explore the various types of files and their attributes. You learn about how to manage file permissions and access control lists, which ties in closely with the account management discussion in Lesson 4. Welcome to Lesson 6.1, Understand the Linux File System. We will cover what a file system is and how it's organized and how an administrator interacts with the file system. So conceptually, a file system is a namespace organized into a hierarchy. And so what we mean by that is there's some set of names, like file names and directory names, and they're organized in some hierarchical structure separated by slashes, generally. A file system is also an application programming interface, or an API. It is a tool that processes, applications, programmers can use to interface with the underlying actual storage system. So it's sort of an abstraction layer, so you can have a file sitting on some disk device. It's also, it includes a security model. So we need to make sure that the users that are authorized to access a given file have permissions to do so, and the users that do not have those permissions. So a file system has structures in place to permit or prevent access to a given user. The file system is the software that takes all of these kind of logical notions that we just discussed and ties them into the underlying hardware, the disk underneath the virtual file system. The kernel itself supports many different types of file systems, many different implementations of them, and there's a lot of nuances and complexities to different file systems that have different features. The Linux file system is usually ext3 or ext4. That's just the type of file system that is the default on many Linux systems. There are many other types of file systems out there that support various features. The file system is used for a variety of purposes. It is primarily for the administrator's use. It's used to represent and organize storage resources. So if I have a CD-ROM drive and a solid-state disk drive and a rotating standard kind of platter disk drive on the system, those all appear under a single namespace, the root, the slash namespace. And the file system is just this nice abstraction that lets us interface with all of those different devices kind of through one common element. So it's also a way for us to interface with the kernel directly. Through the /proc file system, we can configure the kernel. So there's some nice abstractions there for us. It is also used for inter-process communications. If I have a process running and it needs to communicate with another process, it can do so through a file system abstraction. This is commonly the case with web applications, for instance. You might have a web server interfacing with the actual web application through a Unix file system socket. In the most general sense, it's a place for us to organize and store files for the system. So we've seen that throughout as we've been interacting with the Linux system. Touching the file system is the thing that we do very commonly. Let's check out a couple of gotchas with the Linux file system. First, let's understand what an absolute versus a relative path is. So I can check out the file Gettysburg address, the file we've been interacting with throughout this series so far. This is known as the relative path, meaning it's relative to the directory I'm currently in. I'm not giving it any qualifier, I'm just saying list the file. The fully qualified path would be /home/vagrant/Gettysburg address. So this is known as the fully qualified path. We can also refer to it in shorthand as ./Gettysburg address, meaning the current directory is known as dot, and then slash to separate the directory from the file, and then the file name. And yet another example would be tilde, my home directory, /Gettysburg address. These are all various ways to refer to exactly the same thing. There's some other nuances. What if I wanted to have a file called Gettysburg space address? I could use the touch command, Gettysburg space address. But now if I do a list, I have Gettysburg here and I have address here. It created two different files, so I need to put quotes around it. I need to say touch Gettysburg address with a quote. So you can have spaces in file names, but they just need to be quoted, because otherwise the shell thinks it's a separate part of the command, another argument to the command. As we learned before, hidden files always start with a dot, and you can view them with the -a command. Notice that if I just type ls, like I did in this example, we see all the files in the directory, but we don't see any files with a dot in front of them, like the bash files that we learned about before. These are prefixed with a dot, and so they're hidden unless you type -a. We can look at the current directory with dot. Or if I do a long listing with hidden files, I see dot here, which is referring to the current directory that I'm in. And then dot indicates the parent directory, or in this case, I'm in Vagrant, home Vagrant, so dot is home Vagrant, and dot is /home. pwd, which I've been typing all along, is print working directory and shows where I'm currently located. In Lesson 6.2, we'll understand how the file system hierarchy is organized. The file system is organized by the File System Hierarchy Standard, the FHS, which is a standard about how Linux file systems or Unix file systems in general should be organized. So if you go from one type of Linux, say CentOS, to another type of Linux, like Ubuntu or Arch Linux or Gentoo, there are some things that all of those systems will have in common thanks to this standard. So looking at some examples, we can use the tree command to look at the file system. And we'll just look at one level of recursion, one level of depth. We just want to look at root and the directories immediately off of root. And in order to do that, we can type this command tree minus L1 and then slash. So this is showing us one level of recursion. So let's try to understand through the Linux file system hierarchy standard exactly what each one of these directories is for. The bin file system /bin is for essential commands. These are binary files, command files, that will always be available to you. No subdirectories are available in /bin. /boot, which we've covered in some detail before, is where the kernel itself is located and loaded from by the bootloader. It's generally a separate file system on the disk. In this case, if we type sudo fdisk -l, we can see that here. We have cgroup, which is for, it's a kernel abstraction. We'll ignore it for these purposes. It's not a standard. /dev is where device files are located. So if you had a CD-ROM on the system, it might be under /dev/CD-ROM. If you had a TTY attached to the system, well, all systems have a TTY attached, there's a file under /dev called TTY1 for the terminal 1, /dev/TTY1. These are device files, a special type of file. Etc is where configuration files are generally located, things to configure the system. /home is usually where user accounts are located. /lib and /lib64 are library directories where shared library files are located. A library file is reusable code by multiple programs. For instance, any system call or abstraction that many applications might need to be used, it wouldn't make sense for each type of application to write that code itself. So instead, they're put in a library, and many different applications can refer to them. Those are often stored in /lib and /lib64. /media is where removable media might be mounted. If I had put a CD-ROM in my system or a USB thumb drive, it might be mounted in /media. /mnt is for temporary mounts. Opt is for optional software, where you might install something specific to your site or specific to your company or organization that might go under /opt. /proc is that sudo file system that exposes kernel configuration and process information separately to the user from the kernel. /root is a special home directory for the root user. So note that the root user's home directory is not under /home like the rest of the user accounts. /sbin is for essential system binaries that only root can use. So these are sensitive binary files. We'll skip a couple of these that are not super relevant to the context at the moment. /temp is used for just storing temporary files. You can use it yourself as the administrator to do an experiment or copy files into temporarily. On some systems, like on Ubuntu systems, /temp is cleaned out at a reboot. So if you reboot the system, anything in /temp is removed, so don't put anything important there. On a CentOS system, I don't believe it is removed, but it's still not a good place to keep long-term files. /user is where shared read-only data goes. So you might find general user binaries or things installed specific to the distribution. The files under here will be very different between Ubuntu and Red Hat, for instance. /vagrant is Vagrant specific, of course. It's just where Vagrant mounts a shared directory with the host system. So if I went into /vagrant and list it here, I can see files that are also on my laptop are stored in this directory. So this is shared between the Vagrant system and my laptop. Finally, /var, which is sort of variable data files. If I look in var log, I see log files. We may recall from the previous lesson that under /var spool cron is where cron tabs are stored. Sometimes databases put files here. There's also system lock files under /var/run. What we notice here is a number of .pid files. So if I looked at, for instance, var run cron_d.pid, it's only going to contain a number, 1274. And this is the process ID of the cron daemon, 1274. So in this way, a process can prevent itself from starting up twice. So what it will do is it'll try to start up. The first thing it does is look in wherever it's stored its PID file, If the PID file exists and it has a number in it, it knows, hey, there's already a process running. I'm not going to run again because I'm already running, and then it will just quit. That's a common use of a PID file. So that's how the Linux file system is organized. Welcome to sublesson 6.3, Understanding File Types and Attributes. So let's first talk about file permissions. We learned before that a file has an owner and a group, and it also has a set of permissions which we've not yet covered in detail. You'll notice when we do a long listing on a file that there are 9 permission bits that say who can perform which operations. Those operations include reading, which is allowing a user account to read a file, open the file, and read it. There's the write permission, or the write operation, which allows the modification of a file, but not the removal of a file. There's execute, which means that the kernel, the system, will actually execute. So you would never assign this to any file except a script or a binary, something that can be executed by the system. The execute bit on a directory means you can list the contents of that directory. So if the execute bit is not set on a directory, you can't list it, you can't perform operations on that directory. When we talk about file permissions, we discuss them in octal, which is a numbering scheme. You might be, of course, familiar with the decimal system, where you start counting at 0 up to 9, and then you go to 10. Or you might be familiar with binary, which is just zeros and ones. Octal is 0 through 7. And that's the numbering system used to describe file permissions. So let's look at some specific examples here. Here's an example of a long listing of the /user bin passwd binary. This is the file that we use to change the password for a user on the system. Let's look at the permissions in detail. So we have 10 bits here, but only 9 of them are relevant for our current discussion. So starting with RWS. These are user permissions. These are permissions that the owner of the file is allowed to take on that file. So in this case, we have permission to read the file, we have permission to write to the file, and then the setuid bit is set. We talked about the setuid bit before. Setuid means run this command under higher privileges. So if I ran the passwd command as the vagrant user, it would in fact increase its privileges to run as root, since the passwd command needs to do privileged operations. The next 3 bits are the group bits. So these are what operations a group is permitted to use on a given executable. In this case, the group is allowed to read the file, it's not allowed to write to the file, notice the dash, and it's allowed to execute the file. And finally, the last 3 bits are for everybody else on the system. So we have the user, which in this case is root, we have the group, which in this case is also root, and everybody else on the system. So everybody else is allowed to read the file, but not to write to the file, and they're allowed to execute it. So looking at our table, we can see what the octal representation of this would be as well. So starting with the user permissions, 4700. 4 means that's set for the setuid. It's a special version of the octal bit. For setuid, it's not so common to use that one. 7 means that the user has full permissions. Read, write, execute. They can do everything on this file. 50 is what we have for the group. 5 being read and execute. So we have we count 4 for the read and 1 for execute, gives us 5, and then 0. And then the last one is everyone else's permission, which is 5. So read and execute is octal 5. Let's learn a little bit more about the setuid and the setgid. So recall from the process's discussion that executable files can run with elevated privileges, and similarly for setgid, all of the files in a setgid directory inherit the group permissions that are already on that folder. So let's run through this example on the slide. First, we make a new directory, /temp/test. Then we change the permissions on it using the chmod, the chmod command. So we use chmod 2755/temp/test. Then we list it so we can see our work so far. We use ls-ld to list the directory. So the very first bit in that output, the D, indicates that it's a directory. We knew that because we used makedir to create the directory. The next 3 bits, rwx, that's the 7 from the 2755. This means that the vagrant user that created this directory has full read, write, and execute permissions on the directory. Next, we see r-s. So these are the group permissions, and we can see that the S is where the X would normally be. So this section is the 2 and the 5 from the chmod command. So the vagrant user can read, execute, and then any new file that gets created in /temp/test will inherit the permissions from the directory. And finally, all users can read and execute. So then we follow this up by just showing an example, touch/temp/test/file. So we make a new file in the test directory, and then we list it, and we can see that the vagrant user and the vagrant group both have read and write permissions to the file. Here's some further examples with octal notation of permissions. So let's kind of run through each row in the table. Symbolically, in the first example, this is what you might see on a file with no permissions at all. That will be represented by octal 000. User has no permissions, group has no permissions, everyone have no permissions. So that's the very most basic example. The next example is 111. This is everybody has permission to execute on this file, the user, the group, and everyone. On 444, we show that everybody can read this file. So if you're following along, we can see that you start at the left side with the R is a 4, the group is a 4, and everyone else is a 4. So that would be read, read, read. Writes would be 2s, and then we get into mixing some of them. So the 4755, this mimics the user bin passwd command. This is a setuid with the 4 indicating setuid, and then 755 means that the user can read, write, execute, the group can read and execute, and everyone else can read and execute. Another really common permission is 644, meaning the user has read and write access, group can read, and everyone else can read as well. Let's talk about file types. There's more than just files and directories, although those are very common types of files on the file system. There's more than just that. So when you're looking at the file permissions, we're talking about the very first bit here. It's always represented by some letter or a dash. If it's a dash, the file is just a regular file. You can edit it, so it might be an application. It's just a file on the file system. If the first bit is a D, it means it's a directory. But then there's several other types. There are character device files and block device files that start with a C or a B. You'll often see these under /dev, for instance. There are local domain sockets. These are used for inter-process communication when one process needs to talk to another. There are named pipes, which are also a way to communicate with a process. And there are symbolic links, which means that one file points to another file. They're created with the ln-s command. So let's see some command line examples of editing files. So I'm logged into my CentOS box as the vagrant user. First command I'll do is touch file, and I'll use this command to list the file immediately after I touch it. So I've created a new file. We can tell that it's a file because the first bit is a dot. Next I show rw-. This means that this would be octal permission 6. Means I have the ability to read that file. I have the ability to write to that file, and that file is not executable. So if I tried to execute it, like if I tried to do /file like I would an executable file, you can't do it because there's no permissions. The next one is rw-, so the group. These are the group permissions. Also have read, write, and no execute, and everyone else has no access to the file at all. So that was the octal way to refer to it when we discussed terms like 660. I can change the permissions. I could use the chmod command, and I could say 600 file. And let's look at it again. Now I've given read and write permissions to the user, and I've taken away read and write permissions from the group, and the everyone permissions stay the same. I could also change it to be 400. And now it's only read-only. I've taken away write permissions. So we subtracted 2 there. I could get everybody read-write permissions by typing chmod 666 on the file. And if I list it, we show read-write, no execute for the user, read-write, no execute for the group, read-write, no execute for everyone else. So that's the octal representation. You can also refer to these with the chmod command in mnemonic form. And this is maybe a little easier to get started with until you fully understand the octal version. I can say for user, give read-write to the file. Now if I list it, the user has read-write. Now under this version, unlike the previous examples, because we're only specifying user permissions here, we're not specifying group or everyone. So all we see is change to the user. If I, for instance, ran chmod u equals r, that would say give read permissions to the user. Now I've subtracted write permissions for that user. Or if I wanted to add execute, I could say it like this. We can use a different mnemonic form to just add or subtract permissions from a given user. We can say chmod u plus rwx, saying give the user full read, write, execute. We can say group minus read, write. We don't want to give the group any permissions, read, write, x. And everyone else, represented by O, minus rwx. So this should give the user full permissions, the group, and everyone else no permissions. Oops, and I have to specify the file. Now if I look at the permissions, it's just what we anticipated. So we can refer to it either through octal or mnemonically. So let's look at some more examples of messing with the file system and file permissions. So under /temp, we'll just write a quick script. Here's a handy shortcut you'll find sometimes. We can redirect all the output until we see end on the screen and send all of the output to script. So we're going to write to a file called script in sort of a non-traditional way. So I'm going to create a new script. This is the syntax we learned in lesson 2 when we talked about scripts. And I'm going to say echo hello world. Very common programming example. And I'm going to say end to end the script. So if I take a look at that file now, it's just like I had edited a file called script with VI and typed it in. It's just a different way of editing it. You'll find that handy sometimes. Now if I wanted to execute this new script, I can't currently execute it. I can't just say /script, which I normally would do. First I have to change permissions on it. So I need to make sure that this script has execute permissions. I might do chmod 700 script. So let's look at the permissions to make sure we have them right. Read, write, execute. Now if I type /script to execute that script, it prints out hello world as expected. So now we can kind of get an understanding of what the execute bit does. Let's look at what a symlink might look like. So if I touched a new file, we can see this is just a blank file. Read, write, read, write, read. Now I can make a symlink to this file. ln minus s to file. So ln means create a new link. Minus s means make it symbolic. And then I want to make a symbolic link to file called, we'll just call it symlink to make it really easy. Now let's take a look at the symlink file. We can see here, symlink, it starts with an L, so we know it's a link. The permissions on a symlink are meaningless. The symlink permissions are the same as the file for which it's pointing to, and we can see what it's pointing to here. We can see that file is a shortcut to file. So if I type cat symlink, it prints out file because that's the contents of file. One additional example we'll give is changing the ownership and the group of a directory. I can make a new directory, make dir/temp/new dir. And I can change ownership with the chown command, chown. And I can say, well, let's just look at the file permissions first. Temp new dir. We can see, oops, I need to use the -d, ls -dl, temp new dir. Notice that the flag order doesn't matter. dl, ld is the same thing. So we can see that this is a directory because it's prefixed with a d. We can see that vagrant user has read, write, execute permissions on it. The group has read, write, execute, and everybody else has read and execute. Now I can change the permissions. I could say sudo chown -r to be recursive, meaning that directory and every file underneath it will be changed. I could say bwhaley::vagrant. So I'm changing the ownership from the current owner of Vagrant to the new owner of B. Whaley, temp neuter. And now if I list it again, B. Whaley owns the file, owns the directory rather. I could also change the group. I could, for instance, say sudo chgroup -r to recursively change, or I could drop the -r to not be recursive on this directory. I could chgroup to B. Whaley. Oh, we'll use admins, which is the group we created previously. Neuter. And now if I list it, notice I use bash shortcut. This indicates the last argument of the previous command. Shortcut for /temp/neuter. Now the directory is owned by the group admin. So we've just changed the ownership of the directory. So those are how you can manage permissions and ownership on the Linux command line. To finalize the discussion of file systems, we'll talk about access control lists. We're not going to go into a whole lot of detail here. It's just a way to manage granular permissions for files. So let's look at some examples. On my CentOS system, I will change to my home directory. The first thing I'll do is just touch a new file called file, and I'll list that file's contents. So this file has read-write for the user, read-write for the group, no execute, and read for everyone else. But what if I wanted to give a very special permission? What if I wanted to give B. Whaley access to read this file, but B. Whaley and Vagrant aren't sharing a group? How could I do that? I couldn't do that under the normal Linux access control model. So we need to use extended file access control lists, the POSIX access controls as they're known. To do that, we can use getFACL to get the current ACLs on the file. So I type getFACL file, and it shows me just what we talked about. The user has read-write, the group has read-write, other has read. Now I can say setFACL, and I use -m, user, B. Whaley, read, write, x. So I actually want to give B. Whaley read, write, and execute permissions to the file. Now if I get FACL on the file, I can see that the user has read, write, except for B. Whaley, who has read, write, execute. Special permission. Group has read, write, and then there's this other field. So if I do ls -l on the file, notice that there's just a funky X here showing, well, somebody else has permission to execute, but we don't know who that is because the standard access control model doesn't leave a space for that in the output. There's also a plus sign at the end indicating that there's additional controls available to you, additional file permissions, which we can, of course, view with getFACL. So look at man pages for getFACL and setFACL for more examples. Welcome to Lesson 7, Log Files and Syslog. In this lesson, you learn what log files are and why they're so important to system administrators. I cover syslog, the logging daemon that makes our life easier. You learn how log files are managed by a rotation daemon to avoid clutter and filling up the file system. You also learn how to send log files to a central system or service for convenience and security. Welcome to Sublesson 7.1, Explore Linux Log Files. We're going to skip slides for this lesson and jump straight into looking at command line examples. So let's dive straight in on the CentOS command line. I'll start by switching to /var/log, where all the log files are. And I'll do a long listing. I'm going to scroll up a little bit so we can see from the very beginning. This is where all the system log files are kept. A few of the examples. Audit is for kernel log audit messages. The kernel can basically log any event that happens on the system, and if you configure that, it happens in varlog audit. Boot.log is just what it sounds like, where boot messages might be. Cron is where any time a cron job runs, the output of that command, if it outputted anything to the standard out, if it just wrote anything to the screen basically, since it was running in the background, there was no screen to capture it, so it puts it in the cron file. It also contains just a log of every cron job that runs. Dmessage is a special file for boot sequence. So there is a sequence of events that happens. We might recall back from the booting and shutting down lesson that there's a whole lot of output printed out to the screen. You can capture that output after the fact by looking in the dmessage file. HTTPD is a directory for the Apache HTTP web server. It will only be here if Apache is installed. Last log is a log file of the last users logged into the system. So you can use the last command and it will read this last log and show you who logged into the system at what time. We can see the mail log, which is a log of any mail that the system has attempted to send, any email that is. Messages is the general bucket for all system log messages. So the name of this file differs between systems. On CentOS systems, it's varlog messages. On Ubuntu systems, it's varlog syslog, and probably other systems have differences as well. We can see that it's a fairly sizable file. For many of these, we can see versions of them with another date. For instance, this file, messages-2013-08-26. So these are known as rotated log files. Once a week, an automatic cron job runs that rotates the log file so that we can just organize the file system better. We see that there are 4 weeks worth of log files here. There's, in this case, from 8/26, September 1st, September 8th, September 15th. But prior to the August 26th, we don't see any. So those have just been discarded, and that's, of course, configurable. Varlog secure. Secure is for security-related events, of course. If you execute a sudo command, it will be logged in here, and we'll take a look at that in just a minute. And those are the most important ones. So let's take a look at varlog messages. Starting at the top, so we see a date and timestamp at the beginning. We see a host name next, and this system is just localhost, but it could be that other systems were sending their log messages to our system, and then this would be an important field. Next, we see the process, in this case, rsyslogd. We can see exactly what the log message was. So this content that's highlighted now after the process, this is sent from whatever is sending the log message. So this field is going to vary widely. For instance, in the next command, this is yum. Yum is running some update. It's installing a new kernel, or in this version below, it's installing a new bash package. So this text right here was sent by yum itself. We can just page down through and we can see all sorts of additional messages through varlog messages. Let's also take a look at secure, varlog secure. So here we're seeing SSH logs. So it's the same format, date and time, host name, and then the process along with the process ID. And then we see what the message is. So this is saying user disconnected from the system. And this line here is saying we accepted a public key for the user vagrant. This is a new user logging into the system. Here we see sudo. We see this is output from sudo. So this is saying the vagrant user on this specific terminal, PTS0, in the working directory home vagrant, ran as the user root this command fuser111/tcp. And so we can see all sorts of different examples. We can see every sudo command logged on the system. So I'm at the end of the file now. We can even see the sudo command I just used to view the varlog messages file, as well as varlog secure. So this is known as an audit log, and it's required by some compliance, for some compliance purposes, to have a log of every privilege command executed on the system. Next, let's take a look at the dmessage command. I can type dmessage, and in fact, I'm going to retype it, and I'm going to pipe that output to less. This is kernel boot time messages. It's information about the boot process. And this is sometimes important. You sometimes need to find information about what happened during the boot. You can kind of page through this and you can see at what point in the boot process certain drivers were loaded. Sometimes you can search for error messages in this output and you can debug problems this way. It will help you identify drivers and very specifics. For instance, here we see this line, ETH0 is the first network adapter on the system. We can see that it came up, it became ready. So it's just information about hardware on the system. We can look at the last command. So I typed last, and it printed out a whole bunch of information. We can see lots of logins and logouts here. We can see reboots. We can see bwhaley logging into the system, vagrant logging into the system. This is interesting, especially on a very busy multi-user system where there are a lot of people with accounts. You might need to go back and look at this for audit purposes or to see what the timing was for different events on the system. And this goes back quite a ways. You can see this goes back, there's events from June 30th in this system. Finally, let's take a look at the HTTPD Apache logs. These are really interesting, and it says permission denied, so I'm going to use sudo to list it. So there's the access log. This is a list of every time a specific HTTP URL is requested, Apache logs that request to this access log file. And if there was an error, it writes it to the error log. So looking at this output, right here, the highlighted portion, this is the size of the file. So if it says 0, it means there's nothing in that file. That means that Apache hasn't received anything for this time period. But here's a rotated log, and we can see that this has some content in it. So let's take a look at that file instead of the empty file. I'm going to use sudo less httpd and then that file name. We can see exactly an example. So here is the date and time. Here's the URL that was requested, just the root URL. Here's the HTTP status code. This is sometimes, you'll see error 404 not found, or in this case 403 forbidden. This is just saying what the Apache web server responded with when this URL was requested. This is the content size. This shows the user agent, whatever was used to make the request. This would be a browser most commonly. Curl is a command line utility to do HTTP requests. So that's what was used in this case, probably me testing something. So that's what the Apache logs look like. That's all there is to looking at the logs from the user standpoint. Sometimes log messages don't end up in /var/log. This is most common with custom applications. You might see this with a Java application that writes its output to a custom directory or any custom user application. It's very application specific, and you often need to consult the application's own documentation to find out where it writes log files. Welcome to sublesson 7.2, where we'll manage syslog in order to manage our log files on our system. Syslog is a unified approach to capturing system log files, written originally by Eric Allman out of Berkeley. In syslog, logs are captured and sorted by two categories: the facility, which is kind of the source, and the severity, the importance of a given log message. The syslog ecosystem is composed of the syslogd daemon, that's the running daemon that handles the actual logs, the open log library, which is what is used to send messages to the syslog daemon, and the logger tool, which is a command line interface where you can, as the administrator, test and use logging directly from the command line. Any syslog-aware program uses these open log library routines to send messages. So for instance, we were looking at var log messages and we saw the yum packages being updated and other information there. Those must have used the open log libraries to write the messages to syslog. The syslog daemon running in the background reads the messages sent to it from clients and writes them to whatever the configured destination is. The syslogd original daemon is a little bit dated at this point and has now been replaced by a number of new tools. rsyslog is one very common tool on our CentOS system. That's the one that we'll look at. There are a number of others, including syslog-ng, which you'll see on some other systems. In any case, a lot of the same concepts remain, but there's some just extensions in place. So what's a facility exactly? It has a number, just a numeric identifier, and then a keyword to identify what the source was, and then a description. So for instance, the kern facility is a kernel message. The user facility is a user level message. We'll see some examples of this. There's also the severity. So an emergency would mean a very critical emergency system event. That's severity level 0. The system's basically unusable. There might be a critical or a warning message. These are just different severities that can be used to indicate how serious a log message is. It might even be as simple as a debug message. And you can tune the syslog daemon to log messages at or below certain facilities and severities. So let's see some examples of that. On our CentOS system, the first thing we'll do is look in the process table for syslog. We can see /sbin/rsyslogd running, and that's just its command line. So we know there's a syslog service running. We can send a message. We can say logger minus p info, so we're sending it at info level severity. Hello syslog. And so let's see if we can find out where that log message went to. We know from the last sublesson that syslog is sending to var log messages. So let's use the tail -1 to see if that was the last log message sent. And indeed it was. Hello syslog. So the logger command just wrote to var log messages on our behalf. It sent to syslog, our syslog actually, which wrote for us. So what configures our syslog? How does our syslog know what to do with that file? Let's look at the rsyslog configuration file, which is /etc/rsyslog.conf. So there's a whole lot of details in here, and it kind of looks like code. Most of this you don't really need to edit very much. But let's look at some of the most basics, and that's under rules here. Anything with a hash mark, like just as convention, is a comment, so you can safely ignore it. So this is the first line without a comment. This is our severity, and this is our facility, separated by a dot. So what this line is saying is any message from any facility that's at info level, as well as, the semicolon is just saying, is appending, as well as no mail, no auth, and no cron messages. So it's saying from any source except mail, auth, and cron, send the output to varlog messages. For auth messages of any severity at all, put them in secure, which makes sense. You would want anything authentication and authorization related sent to the secure file. Mail messages, in this case mail.star, all the mail messages go to varlog mail log. Cron messages go to varlog cron. So you can see that rsyslog is configured to sort logs in a predestined, pre-configure way. We'll just make a custom entry here. So let's look at etc/rsyslog.conf. We'll edit it with vi. And I've got here at the end, I've added local3.info. And we have var log live lesson. So this is saying any message sent from the facility local3, just this is a custom facility that you can use, with the info severity, put it in this custom live lesson instead. So let's see how can we use this. How can we get a log message from rsyslog into live lesson? I can quit out of this, and I can say logger -p. This is how I can specify a facility and a severity, and I can say greetings. And so now if we looked at the varlog messages, we see greetings. And if we look at varlog live lesson, we also see greetings. So why do we see it in two places? Let's take another look. So I'm back at the etc/rsyslog.conf. Remember that this line is saying anything at info level severity or above, send to varlog messages. That would include local3.info, which I sent before. And we also see it in varlog live lesson because I specified anything sent specifically from local3.info, send it to varlog live lesson. So this is additive. That's what this means, is when rsyslog starts, it reads all of the rules in this file and it applies anything that it sees. We didn't specifically exclude it, so it logged it as we would expect. We can also send messages to a remote server, which you might need to do, for instance, for security purposes. Imagine that there's a system daemon that's been hacked, and it's sending log messages that give some evidence that it might have been hacked. You wouldn't really want that to be sent to the local system because the hacker could then just cover his own tracks by removing the log files. So instead, you configure your syslogger to send its log messages to a remote server that the hacker may not have hacked. And then you have some evidence and an audit trail as to what might have happened. So in order to do that, you can use a specific syntax. Let's look at rsyslog.conf again. Here's my local3.info line. I could say something like, send anything at local3.info to @192.168.10.10, say. That would send over TCP any messages sent to this facility and this severity, local3.info, over TCP to this IP address. Or if I wanted it to be UDP, which is the normal protocol for syslog, I would just use one @ sign. So that's a really quick overview of our syslog and managing its configuration file. Welcome to sublesson 7.3, where we'll rotate and condense log files. Let's jump right into an example. Here we are on the CentOS command line. I want to examine how we rotate log files. So we've seen how our syslog creates log files, but if the log files just grew indefinitely, especially on a busy system, they would fill up the disk, and we need to make sure that doesn't happen. Fortunately, Linux has a built-in method called logrotate to handle that for us. We can check out the /etc/logrotate.conf file. This is where the general configuration for logrotate. This will set up log file-wide global defaults that can be overridden on a per log file basis. So let's look at how it's configured. This is saying rotate log files weekly. So once a week, as we saw with varlog messages, it's going to rotate files. This is saying keep 4 full weeks worth, and after 4 weeks has gone by, then drop the log file. This is saying once you rotate a file, create a new empty file. This is saying use the date suffix. So when the log file is rotated, use the date as the rotation indicator. This compressed line is commented out, but if it weren't commented out, then the log files would be compressed, which can be very useful. If it's a really large log file taking up space on the disk, compression can save a lot of space. On the other hand, it consumes CPU cycles, and if it's a really big file in the many gigabytes range, that can take some significant system resources. This line is saying to include the etc logrotate.d directory. This is where you can configure log file specific configuration settings. So let's go take a look at that directory. We have a few different files in here. Let's take a look at syslog. I'm just going to cat it out to the screen. We covered most of these files when we talked about /var/log earlier. This configuration is saying all 5 of these log files share exactly the same configuration. Logrotate is going to do the same thing to all of them, and once the rotation is finished, that's what this post-rotate line means, it's going to kill and reload itself. Remember when we talked about signals, kill-hup does a reload. So here this fancy bash line is saying our syslog is going to reload itself and reload the files that it was watching, that it was sending log messages to. This is necessary so that when a log file gets rotated, our syslog still has the right file handle so that it's writing to the correct file in place. We could also look at the httpd logs. This one's a little different. So this is saying anything under varlog httpd, it's okay if it's missing, it shouldn't be empty. It just does some very specific things to the Apache log files. Notice that rather than reloading syslog, it's reloading Apache itself. That's what this service httpd reload is doing. That's because our syslog isn't handling the log messages for Apache. Apache is writing to itself. Logrotate isn't tied to syslog. It's an independent application that can be used for any application that needs log files rotated. There's also the need occasionally to reduce log files. Just due to the sheer volume you'll get on a very busy system, there's a lot of redundancy. You need to be able to sort the signal from the noise. One tool to help you do that is known as the simple event correlator. It's an event processing tool, so it helps you look for a specific pattern in log messages for security or for monitoring, and then take some action based on it. So the idea is it reads lines as a stream of input. It might read through the varlog messages file one line at a time, looking for a specific regular expression or pattern. Once it finds the pattern that it's been configured to look for, it should take some action. It could send you a message, for instance, when it sees 100 consecutive login attempts from China. Or it could say, run a script to automatically ban that IP address that was trying to log into your system so that it can't log in. So it can be a handy tool. It's definitely powerful. It's fairly complex to configure, but you can find it online if you Google simple event correlator. In sublesson 7.4, we'll talk about centralized logs and logging services. We talked a little bit when we were configuring our syslog about how to send log files to a central server. it's worth expounding on that a bit. So as we discussed, local log files are not necessarily completely accurate. They're subject to being interfered with. A local user could modify them or delete records or move them. Central log servers can help you consolidate logs so that if you have many servers across your environment, all of those log messages from those various servers could go to a single server, gives you one place to look. It's just a simpler approach. You can configure rsyslog in the manner that we saw before, using the @@ syntax or the single @ for UDP to send messages to a given IP address at a given port. An alternative is to use a service for this purpose. Cloud-based services are very common these days, or even local log services. One very common one is Splunk. Another up-and-coming service is known as Sumo Logic. The idea with a logging service is that it sends messages to some collector running. For instance, this is the Sumo Logic method. There's a Java daemon running on a given server. All of these log messages are added together and put into a message to the collector service, which then sends it over the internet to Sumo Logic's backend. At the Sumo Logic backend, you can log in with your own username and password, search through your messages, graph them, sort them, perform all sorts of queries and analytics on your log messages. This is a really nice way to get super powerful details about your environment and is really valuable in an environment that collects a lot of data. So check out Sumo Logic or Splunk when you start to have complex logging needs. Welcome to Lesson 8, TCP/IP Networking. In this lesson, you learn how to configure a Linux system for a TCP/IP network. I cover the common tools, files, and commands used on the network. I discuss how to configure a Linux DNS client, including using the dig command to query DNS servers for information. I also add some tools to your tool belt for diagnosing and troubleshooting networking problems. Welcome to Sublesson 8.1, where we'll discuss Linux's versatility on the network. Linux, from its very earliest implementation, was designed for the network. It's really where things get interesting with computers when you connect them to other computers to enable advanced communications. Linux's network stack is extremely flexible. You can configure it for just about any type of network out there. Of course, it's very powerful and has a large impact on the internet. It's also present in mobile devices in the form of Android and can be configured to do really whatever you need it to do. It has very widespread acceptance among vendors. This means that virtually any network driver that you need, any network adapter, whether it's a brand new piece of technology or something really old, likely is compatible with Linux. And the great thing about Linux is, even if it's not compatible out of the box, some developer out there can write source code and it will be compatible. Linux is an early adopter of brand new technologies. For instance, the brand new TCP fast open, or fixes for the network problem on the internet known as buffer bloat, were built into Linux before pretty much any other operating system. This means that you can test out new features of the internet that are just being developed early, and you can write applications so that they take advantage of these features. Linux is really a great multi-purpose tool. It can serve a lot of different functions on your network. Let's explore a few of them. On the web, Linux has a great presence. It has a number of powerful web servers. A couple examples are the heavy, very process-based servers such as Apache HTTPD. Out of the box, Apache HTTPD starts as root and spawns a number of subprocesses. It can also be configured to use threads rather than processes. In either case, it's a very thick and powerful web server that can be configured to do what you need it to do. Alternatively, you could use a different approach to web server technology such as Nginx. Nginx is really a lightweight event-based web service. It's actually just a proxy. It accepts inbound connections and proxies them to some application server behind it. Because of this, it's very lightweight, very fast and efficient. It's also asynchronous. You can modify HTTP traffic in transit. It may not have as much features or as much functionality out of the box as Apache, but it certainly suits the needs to run a really large number of today's websites. In addition to front-end web servers, Linux also has support for a number of powerful application server technologies. For example, the very common scripting languages such as Python, Ruby, and PHP are very widely supported, and there's large communities out there to help new programmers get familiar with how to use them, and as well as system administrators how to implement them and scale them properly. PHP is used to power Facebook's entire site, so you know that it's a powerful technology that will serve almost any purpose. On the other hand, there are additional programming languages such as Java and C++ that have great support and application containers on the Linux platform. These are used often for heavy back-end application processing purposes. Linux is also great for a database server on the web. You can run a traditional relational database management system, such as Oracle, or you can run an open source version that would be free and very widely supported by communities, such as MySQL or PostgreSQL. Today, other technologies, known as NoSQL technologies, are gaining prominence as a very fast, performant, different approach to managing data stores. Cassandra and MongoDB come to mind as very popular back-end platforms for supporting high-scale websites without SQL. Linux can also perform as network infrastructure. For instance, Bind is the de facto DNS server. It is measured as the standard by which all other DNS servers are based. It runs the root name servers for the DNS system as well. DHCPD, also from the same organization that writes Bind, is a de facto reference implementation of a DHCP server. So Linux could be used to serve dynamic addresses across your network. Linux can be used as an SMTP email server. SendMail comes to mind as a commonly deployed email server. In addition, there are Postfix and other mail servers out there that you can use to send email across your network. Linux can sometimes be deployed as an NTP time server. You can configure it to make sure that all the systems on your network are in sync and serving exactly the right time. This is important for lots of purposes. For instance, for maintaining security. When a log message is printed, you want to make sure that it had the right timestamp so you can find out what happened at what time. It can also be important for databases to maintain integrity and consistency, especially when multiple database servers are hosting a similar set or shared set of data in a cluster. Linux can be even configured as network gear. It can be configured as a router, so it sits between your network and the internet and routes traffic between multiple networks. It can be configured as a firewall. In fact, it is the core of many professional firewall products from companies such as Linksys. Linux can be configured as a monitoring server, where it takes as input metrics measured from different systems around your network and alerts you when things aren't quite what they should be. It can be a logging server, as we learned in the syslog section, or it can even be used for analysis of incoming log messages or for network traffic. Finally, Linux can be a configuration management server. Tools such as Puppet and Chef can make sure that the configuration of your network stays in sync at all times, and it helps to prevent different systems from drifting. It's called configuration drift. When systems are changed over time, Puppet and Chef can help make sure that those systems stay the same. Welcome to Sublesson 8.2, Configure TCP/IP. In this sublesson, we'll jump straight into some demonstrations of how to configure TCP/IP on the Linux command line. We are now logged into the CentOS box as the user vagrant. We want to examine the current network configuration, and we'll make some adjustments to make sure that TCP/IP is set up correctly. First, we'll take a look at dmessage. We learned about this when we covered logging in the syslog lesson. What I want to show here is I'm going to search for the string ETH0. In order to do that with less, I press a / and I type ETH0. I press enter and it finds occurrences in the output of dmessage. And the reason for this is that ETH0 is our first network interface. By default, this is the name of the network interface on many Linux systems. This is just showing us that E1000 is the driver for our network interface. It shows that it's a 1 gigabit network connection. It's an Intel chip. So when we see this message, we know that Linux has recognized our network driver. In most cases, this just happens by default, and you don't have to make any changes. The next thing to look at is the PCI bus. We can use LSPCI to examine the PCI bus. This shows us anything attached, any adapter, any hardware attached to our PCI bus. And what we're looking for here is our Ethernet controller. This is our network card. We can see just a different view of the same thing we saw in the D message output. We can see the very specific device that our network card is, 82540EM. It's a gigabit Ethernet controller. Just further confirmation that Linux has seen our network device, so it knows it's attached to the system. Now we can examine the card at a layer 2 level. So thinking back to our knowledge of the OSI network stack, we're looking at layer 2 here. And we can see information about our network card. So there's all sorts of information specific to this card. It shows, for instance, that it's set to auto-negotiate, meaning that it negotiates its rate of exchange with the upstream network switch that it's attached to automatically. We don't have to set it to a gigabit. It tells the switch that it's capable of a gigabit, and if the switch is also capable, then they begin communications at a gigabit. It shows us that it's set to be at full duplex, the type of port that it uses. Importantly, here at the bottom, it shows link detected yes. So this means that the machine believes it has a network connection. It senses a cable plugged in and a connection on the remote end. If you were looking at the back of a computer and the network cable was plugged in, you would see a green light. That would indicate that the link was connected as well. This is Linux's confirmation that it also sees the link. So now let's examine the commands to explore and configure the TCP/IP stack. One command is the IP command. This is really a suite of tools that lets you configure the network. IP adder shows information about addressing. And if we say show, we can see that. First thing to notice is that there are actually two links configured on my Vagrant box at the moment. There's the link LO, which stands for, this means loopback. Every system has a loopback interface. This is just a local interface that processes can use to communicate with each other via TCP/IP, but never leaving the host. So imagine if you had a network card and you plugged a cable into it and then you plugged the other end of the cable right back into the computer. So it never actually went over the network. That's sort of what a loopback interface is. The loopback interface is configured with the IP address 127.0.0.1. Anything in the 127 range will always be loopback. And by convention, 0.0.1 is the loopback interface. So you'll see this on any Linux system you encounter. Next, we see ETH0. This is our primary network interface that's actually attached to the network. We can see that it's been assigned the IP address 10.0.2.15, and that it's configured on a network that is a /24 network, a Class C network. This is very common. We can see its broadcast address. We can see its MAC address, which is its layer 2 Ethernet address. We can show here, importantly, that it's up, meaning it's up and ready to communicate on the network. So this is the most basic way to view information about our network. This is also a brand new tool, or I shouldn't say brand new tool, but it is the replacement tool for the historical tool known as ifconfig, which is still present on almost every Linux distribution. However, it is now deprecated in favor of the IP route suite of tools that we just used. In any case, if you type ifconfig, you'll see many of the same details. You can see that it's an Ethernet attachment to the network as opposed to, say, a fiber attachment. You can see its IP address is 10.0.2.15. You can see its broadcast. Notice that rather than the CIDR notation that we saw here with the /24, we actually see a network mask notation used under ifconfig output. Just a subtle difference in how it's displayed. Ifconfig is also showing us some statistics. This particular display is showing us that we've received 395 packets and we've sent 249, so not a very busy card at the moment. It shows us the same information in bytes. It shows us error information. Sometimes if you look at this output, you might see errors or dropped packets. That almost always indicates some problem either with the cabling or upstream on the network. In any case, it's an error condition. These numbers should always be at or near 0. And we also see our loopback interface, just as we did in the IP adder show output. Linux can also be configured to show multiple IP addresses on a single interface. If you're wondering why that's useful, one example is for SSL. SSL, if you set up say an HTTPS website, must have a certificate tied to a specific IP address. Sometimes you wish to host more than a single SSL site on one host. And if you need to do that, sometimes you can just add a second IP address to the same interface. It can communicate with the network via all of those IP addresses, but you could host an SSL certificate for each subinterface. So let's show how to do that now. We can type sudo, we need to run this as root, IP adder add, and then we need to give it the IP address, and I'll pick one in the 192.168 range as one of our RFC 1918 address spaces available to us. We say /24 to indicate what the subnet mask is, and we say which device we want. And in this case, it's going to be sharing ETH0, but we're saying :1 to differentiate it from the default ETH0 interface. So it didn't give us any error output, indicating that it probably took it. We can investigate this by showing IP adder show. Now, unlike the previous example, we show our new interface added here. Now, it doesn't mean, just because we added this IP address, it doesn't mean it will instantly be able to communicate on the network. The rest of the network must understand also how to route this IP address and how to access it. If the network isn't configured for the 192.168 address space, it won't do anything. But now we know how to configure it on the host itself. We can later remove that address if we wanted to by just replacing add with del. And if we investigate our output again, we see that second interface has been removed from the system. As Linux system administrators, we often need to configure routing properly for our box so that the Linux system knows how to access different networks as needed. In order to view routes, we can use the IP route show command. This shows us that, for instance, in this first line of output, in order to access the 10.0.2.0/24 network, we go from the device ETH0 and we go out this configured IP address. So it's saying use this interface to access that network. Or for instance, in the 192.168.10 network that we configured by manually adding that second device, we also go out the ETH0 interface, but we take the other IP address. So it's just telling the Linux system, in order to access this network, leave via this interface. Importantly, we have a default route. The default route is what the Linux system takes whenever it doesn't have another route to use. So most commonly, when you're out there accessing the internet, you don't want to have to configure every possible network on the internet. It would be impossible. So instead, we set a default. We send all of our traffic to that upstream default gateway, and that's where it will send packets if it doesn't have another configured network to use. The deprecated tool to show the route table is via netstat-rn. So this shows us a lot of the same information as the previous command, only in a different format, via a table instead. So we can see, for instance, our default route here is 0.0.0.0. That's indicating every other network. Go via this IP address, this mask, so this is really telling us every network out there. And this little G indicates that this is our default. So it's a lot of the same information, just displayed in a different format. Again, this command is deprecated, but still present on basically any Linux system that you'll encounter. It just might not be maintained forever. So far we've seen how to view IP addresses and add new IP addresses and configure routing only via the command line, but these wouldn't persist. If the system were rebooted, all of this information might change. The IP address that we statically configured would disappear, and sometimes clearly you want that to persist between reboots. So in order to do that on a CentOS system, this is a detail that varies between Linux distributions, we go to etc sysconfig network-scripts directory. There's a lot of files in here. We can ignore most of them safely, but the important one is this file ifcfg-eth0. So this is the configuration for the ETH0 default network adapter. First line is the device name, ETH0. The next line says boot protocol, that stands for, and it's saying obtain your IP address automatically via DHCP. So this Linux system doesn't have a static IP address. Many servers, certainly servers in corporate networks, will have static IP addresses configured, in which case you would change DHCP to the word none. We have optionally specified here the hardware address. This is the MAC address of this system. And I have some additional details. On boot says yes, so this means that you want to bring this interface up at boot time. It's an Ethernet adapter. It shows its UUID. Notice there's no IP address configured here because it's DHCP. If we needed to configure a static IP address in addition to changing boot proto to none, we would specify IP adder in all caps and set the IP address manually. We'll add a second static configuration file so that another interface comes up at boot. So in order to do that, I'll just make a copy of the previous one to save myself some typing. So we'll add the same interface that we added manually earlier, only this time it will persist between reboots. And I'll go ahead and edit that file using my bash shortcut for the last argument on the previous command. Okay, so this time we'll set it up as a static address. So we'll set it to eth0:1 as the device name. I'll set boot proto to none. I'll go ahead and delete these lines because they're optional and I don't need them. And here I'll set the IP address, and I'll set it to what we had configured before, 192.168.10. Actually, I'll set it to 10.11. And I use :WQ and VI to save that. Now I can use the ifup command, which is a command that will read this configuration file and bring my interface up. So sudo ifup eth0:1. It's attempting to bring up the interface. And now it's up. If I look at the output now with IP adder show, I show 10.11/24. I also show 10.10/24, which I had configured previously. But this is showing me that it's a secondary interface. It's also visible in the ifconfig output. We see it here. Shown up as 192.168.10.11. And if I were to reboot my system, which I won't do now, it would also come up automatically at boot. In order to bring it down, I can type ifdown eth0:1. And if I retype ifconfig command, I don't see it in the output anymore. Notice that I didn't bring up or down the eth0. The reason for that is that I'm currently logged into my Vagrant box over that interface via SSH. If I were to bring it down, I would lose my connection and my host would no longer be accessible. This is a common thing you might encounter when you're accessing systems remotely over the network doing normal system administration duties. You want to be very careful not to make changes to interfaces when you're logged in remotely, as you might lose that connection. This configuration file anymore, I'm going to go ahead and delete it. Sudo rm ifcfg-eth0:1. So now we've seen how to add new interfaces, bring interfaces up and down on the network, make sure that interfaces will start at boot time. It can sometimes also be useful to examine current network connections. In fact, this is very often the case for a busy server system. You want to see how many network connections that system has at the moment, what state those connections are in, what other systems on the network your Linux box is talking to, and Linux has built-in tools for that. So one such tool, part of the same suite of tools as the IP command, the IP route suite, this is the SS command. So we can use SS-A to show us all active connections. So there really aren't very many on this not very busy virtual machine of mine. We see in the very first column, we see the state of this connection. We see that this is a listening connection, so there's something listening on this port. And we can come over here and we can see what's listening. It looks like it's on at least the same port that SSH uses, which is 22. So what we see is the state that it's in. We show if anything is queued there. We show what the local address is and its port. And we show what the remote address is and its port. So let's look at the last line. This is an established connection, meaning it's open and in use. It's to the SSH port on the interface 10.0.2.15. and it's communicating with the peer 10.02.2. That would be my laptop. This is showing the connection from my laptop SSH'd into my virtual machine. So this will show us all of the connections out there. Now, one thing that's interesting is we're not seeing a number here for port. We're seeing the interpretation information. So it shows SSH rather than 22. Sometimes it's useful to actually see what the port is, and we can do that with the N flag. So now we show that rather than SSH or SMTP, we see 22 and 25 in place of that. You'll often want to add the N qualifier when you really need to see what the port number is. This information about what name it should use here is pulled from a file in the system called etc services. So we'll just take a quick peek at etc services. This is a list of registered ports. So we can see, for instance, port 21 is registered to the FTP protocol, port 21/TCP, port 23, which is Telnet, is registered here. This is a little less frequently used these days, but used to be the standard way of accessing systems remotely. And there's really a lot of registered applications in this file. Anytime you see something in the output of SS-A that you're not familiar with, you can consult etc services. What I like to do is say grep for SSH and /etc/services, and it shows me various places here, and you want to look for the exact match. So if I'm searching for SSH, I look for exactly SSH in this output, not SS shell, not SDO-SSH, but actually just SSH. So that gives us the name to port mapping information. We can see the same information using the netstat command, the deprecated tool that will maybe one day be phased out. We can show netstat -an. So netstat shows us not only TCP information, but also UDP information. So we can see here that we're listening on UDP port 68, and it's listening for anybody to connect to it. And we can also see Unix socket ports. So we're not seeing that in the SS output as it's limited to just TCP IP or UDP as well. This might be removed in a future update. We can type sudo netstat, and we'll give it some different flags. The last time we typed -an. And this time we'll add some more qualifiers. We'll add -ANLP. And we'll see what the difference is here. One difference we can see is that we're actually now seeing the program output. We're seeing which service, which running process is using that port. So port 22, we knew it was SSH because we just know that that's a convention, but now we can actually see the process that's running. It shows us the process ID, the PID, and it shows us the name of the program. So finally, we can use the fuser command, and we can explore very much the same information, but in a different way. I can say, in Linux, everything is a file. So even TCP IP sockets are files, and you can explore them with the fuser or the file user command. You can find out what program is using this file, or in our case, a socket. We can use this syntax, and we can see that these PIDs, 1201, 1273, and 1275, are using port 22 TCP. And I could search the process table for that information. So here I can see SSHD is using that port. Here's the process. So that's a quick way to understand what application has a given port open, and that can be really useful. One final thing to investigate, and we've seen this a bit in the earlier examples under processes, under /proc/sys net IPv4, we have a whole host of TCP and IP configurations. This is how the kernel is configured to manage TCP. So an interesting one, for instance, is the IP forward. Currently it's set to 0. So if this Linux system, my virtual machine, received an inbound packet and was asked to forward that on, say it was asked to function as a router, it wouldn't do it because it's configured not to do so. But if I wanted it to, I could change that to a 1. I could say sudo, I like to do it this way, open a subshell with sudo and say echo 1 output to IP forward. And now we can see it set to a 1. So now this Linux system will act as a router and forward packets to other networks. So that's the real quick and dirty of configuring Linux for TCP/IP. We learned how to add and manipulate IP addresses on different interfaces and show what IP addresses are configured. We looked at the route tables with the IP route show command. We also configured static interfaces and learned how to investigate the status with sudo ss-an, for instance, to show us what the current connections look like. This is really a core competency for Linux system administrators, and you should take the time to really understand in depth all of the commands here. Welcome to sublesson 8.3, where we'll configure DNS on a Linux system. So, on a Linux system, we use DNS to resolve remote host names. The first thing to know about is how to configure the client side, how to do a lookup, how to point to a different DNS server and examine those configurations. So there's a few places to look. First, there's the etc hosts file. Let's take a look at that. etc hosts. So this looks like a pretty boring host file. What we show is the IP address 127.0.0.1, this is our loopback interface as we learned in the last sublesson, is configured to be the hostname localhost and the domain localhost.localdomain. So this is how I can say ping localhost and it knows who to talk to. It uses the host file to translate the term localhost into 127.0.0.1. So that's pretty boring. Let's see if we can make a change there. I'm going to edit my host file and I'm going to put another entry in here. I'm going to say 127.0.0.2. So all of the 127 address space is reserved just for local loopback. I can do whatever I would like with it. And I'll just call this, say, live lesson. And I'll go ahead and quit. Now if I ping live lesson, the Linux system knows who I'm talking about. It knows I'm talking about 127.0.0.2. But you can see that this method doesn't really scale very well. You couldn't possibly add all of the internet hosts to this big host file. It just wouldn't work. So instead, that's what the DNS system is for automatically resolving those through a server. Those servers are configured in etc resolve.conf without the E. Notice that, resolve without the E.conf. As we learned before, my Vagrant box here is configured to be a DHCP client. So DHCP is automatically configuring the name server for us. So this is telling me that 10.0.2.3, this IP address, is configured to be my DNS server. When I try something like ping google.com, first we look up the IP address against our DNS server, and then we start pinging it. We translate google.com into an IP address, and it starts sending pings, which we'll learn about in just a few minutes. So we can change our DNS server really easily. We can edit that file, resolve.conf, and I could put a comment here if I wanted, so I just want to save that. I don't really want to change it, or I don't want to lose it. And I could say name server, and I'll just use another name server. A public name server that's available is Google's name service 8.8.8.8. Or we could copy that and say 8.8.4.4. These are name servers that Google makes available just for public use. And now, if I ping google.com, I'm no longer looking up against 10.0.2.3. I'm using 8.8.8.8 instead. So this is how you can configure a name server manually on a Linux system. Now, how does Linux know when to use the hosts file versus when to use DNS, and what order does it go in? That's configured in another file, the nsswitch.conf file in /etc, so /etc/nsswitch.conf. And there's a lot of information on here. NSSwitch talks about what order to do things in, but the one that we're really interested in right now is hosts. This line right here, hosts line. So it begins with hosts, followed by a colon, and then it says consult files, and then DNS. So this is the order. First look at the files, then look at DNS. So the first thing a Linux system does when it's trying to resolve a host name is look in the host file /sc/hosts. If it doesn't find the entry there, it tries against the DNS server. If it doesn't find the entry there, it gives up. Let's see if we can confuse the system. We know right now, since we did a ping google.com, it resolved to the 74.125, whatever Google's address is that was resolved from my current network. This might change, by the way. Google has a very vast and complex network. The East Coast of the United States will have different IP addresses than the West Coast. But in any case, we will go ahead and edit the etc hosts file, and let's just confuse it. Let's say 127.0.0.2 is google.com. So now if I ping google.com, my system thinks that it's 127.0.0.2 instead. This can be pretty handy sometimes, to be able to trick the computer into thinking that one site is another site. It's great for development purposes, for instance. You don't want to be editing and testing against your live site, so you go to your local hosts file and you point it at your development server so that it acts exactly like it might act in production, but you're testing against your own development server. This is a very common, pretty useful hack to use. And then on the other hand, we can try things like, well, I want to ping some name that doesn't exist, like benwhaleylivelesson.com. That doesn't exist at all. So it tells me unknown host. What it tried to do was consult the hosts file and then consult DNS, and then it just failed because it couldn't find that domain because it doesn't exist. Another useful thing to know how to do is to change the system's host name. And there's a couple things you need to change in order to change the host name. We can type sudo hostname, the hostname command. Without any arguments, it tells us what the current hostname is, but I might want to change the hostname to, say, live lesson. So I can just say sudo hostname live lesson. Now notice the hostname didn't change on our command line yet. Currently it still says localhost. In order to see that change, I need to log out with Control-D or the logout command or exit, and I'll log back in. Notice now we see that it's changed to live lesson. I can also change it in etc sysconfig, and then I look at the network file. And in here we see hostname equal localhost.local domain. I could change it to live lesson. And now its hostname will be live lesson going forward. So anytime you need to change a hostname, you use the hostname command and you edit etc sysconfig network. Let's quickly learn how to query DNS, which is a very important tool when you're troubleshooting DNS problems. And the command that I like to use first and foremost is dig. This is a tool to query DNS. So if we take a look at our name server configuration, remember that's in resolve.conf. We're still pointing at Google's name servers, 8.8.8.8 and .4.4. I can say dig google.com, and let's take a look at this output. Google has a fairly complex configuration. We can see that google.com resolves to a whole bunch of different IP addresses. And if I look them up again, I'm just going to press the up arrow and repeat the same command. Notice this number, this second number has gone down a bit from 197 to 181. This is the time to live field. This is how long that address is valid for. And so if I'm actively doing some work and repeatedly querying google.com, I might resolve this is my IP address for google.com, and that might change. This is so that Google is flexible on their back end. They can move their servers around, and not all of the clients will be impacted. If something goes wrong with one server, they can quickly just update the host. So that's a pretty simple example. What we just did is we resolved a host name to an IP address. Sometimes it's also useful to do the reverse, to resolve an IP address to a host name. And in order to do that with the dig command, you use the -x flag. So I'm going to use dig -x in the IP address. And so what this is telling me, this is returning a PTR record, a reverse lookup, and it's translating this IP address into this host name. So this is just some random host name that apparently Google uses for its network, 1e100.net. If we wanted a little more summary output, we could say dig plus short, and then we could say google.com. Notice we don't get all the same output we got here in this above example. This is telling us all sorts of information up above, like what the question was, what the answer was, how long the query took. Here, it's also, notice it's telling us what the server is. We know that because we had resolve.conf configured to use that, but it's telling us that output. Here, in the short example, all we get is the answer to our question. What does google.com resolve to? It resolves to all of these IP addresses. If we wanted some different information, say we wanted to know what Google's mail exchange or MX records were, what handles mail for google.com, we could say dig google.com MX. And here are the various MX records for google.com. And of course, we see what the order is. Google says this is the first one. Here's our ordering right here, 10, 20, 30, 40, 50. So if you're trying to deliver mail to google.com, you'd use this one first, this ASPMX. We can see text records for google.com with text. So the idea is that you can just query a specific type of DNS record by adding the type to the end of the query. If we wanted to specify a different server to use, so say I wanted to revert and query my local one that was set by default. I've changed it to Google's public server, but now I want to go back. Just for one query, I can just say the @ sign, and I could say 10.0.2.3, which is what it was configured to do by default, google.com. Now I get mostly the same output here, but notice the server field is different. So now it's querying a different DNS server. In this way, you can query against DNS servers that your system is not configured to use by default. Sometimes it's useful because you can have different views of the world from different DNS servers, especially if things are out of sync or if there's some problem. Just a couple quick additional tools. You can use the nslookup command, which is a deprecated command. It's still around, but dig is far more powerful. Here I get dropped to a subshell, indicated by this little arrow, and I could say google.com, and it gives me much the same information. It tells me what the server is, and it tells me a number of different A records here. It's just kind of a different layout. Or I could alternatively use the host command, host google.com, and it tells me a lot of the same information as well. It shows me all of the addresses, it shows me an IPv6 address, and it shows me the mail exchangers. So that's the quick and dirty on how to query DNS, the DNS client side of a Linux system. Welcome to lesson 8.4, where we'll troubleshoot networking. It's a very common task for administrators to need to troubleshoot different problems on the network or determine where problems exist, and we have a whole suite of tools available to us. We'll examine a few of them now. One of them is ping, which you may already be familiar with, having had some network experience. It sends ICMP echo requests and wait for a response. So it's basically asking, are you up? Like, is another host up on the network? And then the other host, if it's up and configured to allow it, will say, yes, I'm up. It'll reply back with an ICMP echo reply. Very useful tool just to determining whether you have network connectivity, whether a host is available or not. One of the first things I do to check if my network is up, even on my laptop here, is I try to ping google.com and I see if it's replying. We have the trace route or trace path commands. These are used to trace the route that it's taking, that a given system is taking to get to a remote host. So when we talk about routing before, when we're examining the route tables, sometimes if the route tables aren't configured correctly, you can use the trace path command to figure out exactly what path it's taking, or you can determine if you're trying to get to some remote host and you know the remote host is up but it's not replying to your system, you can figure out where on the problem the network lies. We also have the netcat command, which is a pretty handy, very simple tool. It allows you to do arbitrary TCP or UDP network communication. So I can just send arbitrary packets over the wire to a given host at a given port. I can also set it up to listen for incoming connections. So that can be pretty useful for troubleshooting firewall problems. I could log into two separate systems and set one of them up to listen and set one of them up to send data and see if I'm sending and receiving the packets on both systems. Finally, there's the very useful TCP dump command. It puts the network interface in what's known as promiscuous mode. So it's able to investigate the network at a really deep level and tell you exactly what's going on with network packets. You can use it to troubleshoot firewall problems or to see exactly what's going on in a given network communication. In addition, there's a tool called Wireshark, which is not strictly a Linux command line tool, but a very useful tool to use in tandem. You can capture packets. What I like to do sometimes is capture packets on a Linux server somewhere with TCP dump and save them, and then copy that file to my laptop or wherever, and then load it up with Wireshark, and I can view, in a graphical format, I can view that communication. So we'll see some examples of that. For this discussion, I've just set up a really simple network between two virtual machines running on my laptop. So I have my CentOS box that we've been using all along for examples, and an Ubuntu box that I've configured to have a private network. So we're using the 192.168.10.10 and 10.12 addresses. This will allow us to demonstrate some of the tools that we're going to be looking at. So let's jump into that now. So now I'm on the command line and I have two screens open. On my left is my CentOS box. We renamed it from localhost to live lesson. And on my right side I have Ubuntu. So we have the network that we depicted in the slide set up between these two hosts. We'll use that network to do some examples and troubleshooting. First things first, we'll use the ping command. I'll just ping google.com. I won't even use the Ubuntu host yet. So I sent a packet to google.com. I sent 2 packets, and I got replies, and I used Control-C to cancel out because we just wanted to show an example here. So it showed that the first packet was ICMP sequence 1, the second packet was sequence 2. It took 34.8 milliseconds the first time, and the second time it took 33 milliseconds. That is the measure of latency that it took, the amount of time it took for the packet to get to Google and come back. It gives us some nice statistics. I often use ping to determine whether I have a lossy network or not. I'll let a continuous ping run for, say, 500 or 1,000 packets, and then I'll cancel it out, and I'll look at these results. I'll see if I have some percentage of packet loss. Ideally, you want 0% packet loss. If you see packet loss, it always indicates that the network is not optimal. You'll often see it on wireless networks. For instance, if you're using your laptop at a coffee shop and you start a continuous ping, you'll see some packet loss. It's very common. It's less common if you're plugged into the network, if you have a physical connection. But in any case, you want this to be a very low number or percentage, especially on a server. You want this to be at or near 0. Other important information from the ping output is here that shows us the round trip time minimum was 33 milliseconds. The average was 34, and the max was 34. It shows us a standard deviation. We only sent 2 packets, so that's not very interesting. But sometimes that can fluctuate pretty widely, and if you see a large number of packets with high latency, you can usually deduce that there's some problem there. So let's try to ping our Vagrant box. Let's take a look at our network config on both of our boxes here. So on my CentOS box, I have ETH0 with this IP address and ETH1 with this 192.168.10.10 address. On my Ubuntu box, I have the same private address. This is, they're not in conflict because they're not sharing a network here. But then the other one they are sharing, ETH1, and so this guy is 10.12. So these guys can communicate with each other over a private network between the two of them. I'll start a continuous ping example from my CentOS box on the left to my Ubuntu box on the right. They're going to communicate over their ETH1 interfaces. This one is from 10.10 and the Ubuntu box is 10.12. So in order to do that, I can say ping minus capital I and the interface that I want to ping from, which is ETH1. And I want to ping to the Ubuntu box, which I know his IP address is 10.12. So that ping is running here, which is great. It means that the network is up. So now I'll just show an example. I'll bring that interface down. So I can say sudo ifconfig eth1 down, and I'm going to stop this interface on my Ubuntu box. Now notice on the left side here, I hit enter a couple times just to show it's not receiving packets anymore. So far up until that point it had been receiving all sorts of packets, and now it's stopped. So it's sending ping packets, echo requests, and it's not receiving any replies. So just to demonstrate, I'll bring it back up now I'll replace ifconfig eth1 down with ifconfig eth1 up. And instantly on the CentOS box it starts receiving replies again. I'll use Control-C to cancel that out, and we can show we got about 50% packet loss. We can show that we sent 46 packets, we received 23. So it's just telling us information that we lost some data in transit there. That's how you can use ping to determine some useful network information. Next up, let's try a trace route example. We'll type trace route, and we'll trace route to google.com from my CentOS box. So I started the trace route to google.com, and what it's doing is it's determining every hop along the path until the destination server. So it's taking some path, these are all IP addresses of remote systems, and it's telling me how long it took to get to those systems and what their IP addresses are. Sometimes you'll see stars, for instance, in this first case, and there might be others that show up here. That indicates that it wasn't able to determine what that hop was or what the latency was to that one hop. On the path between your host and whatever remote host you're tracing to, in my case google.com, it can say, well, where's the latency spike happening? What system is starting the failure? You can determine exactly where a problem along the way started to occur. So now I've cleared the screen and we'll show an example of Netcat. We can use Netcat to send and receive arbitrary TCP and UDP connections. So I'll just start on my CentOS box here. I can say NC for Netcat minus L 8000. So this is telling my CentOS box, just open a connection, open a port, start listening for a new connection on port 8000. On my Ubuntu box on the right, I can say netcat nc -v for verbose mode, -z says just try to open a connection. I'll specify the CentOS box's IP address, and I'll say port 8000. So this is saying try to connect to 192.168.10.10 port 8000, and it says succeeded. So it was able to send a packet to this box, and this box stopped listening, the CentOS box stopped listening, and the connection was successful. So we know that network traffic between the Ubuntu box and the CentOS box is in place and working just fine. So we can show some additional examples. Let's look at something a little more interesting from the Ubuntu box. Like we said, it's arbitrary network connection traffic, so I can say something like echo hello world, which we know that would just print it to the screen. But if I pipe that output to netcat, and I'll send it to the CentOS box, 10.10 port 8000, we see on the remote system we received hello world. So we sent hello world from the Ubuntu box, we echoed it to netcat, which put it through the TCP network over to the CentOS box, which received it. So that's an example of using netcat. Now let's look at TCP dump, which is a tool we can use to look at in detail network traffic as it's crossing over the wire. So I'm on my Ubuntu box, and I'm going to use TCP dump, and I'm going to specify -i eth1. This is specifying a very specific interface, the eth1 interface, which we know is the interface that we have a connection with our CentOS box on. And I'm going to say a filter here, port 8000. So this is saying only show me traffic that occurs on port 8000. So I just pressed enter, and it's listening. So now I'm going to send some traffic from my CentOS box. So I'm just going to say echo hi and pipe it to netcat 192.168.10.12, which is the Ubuntu box, and I'm going to specify port 8000. And we have some output here on our Ubuntu box. I'm going to press Control-C, and we'll just interpret this a little bit. So the very first line of output here, we show that it's sending a TCP SYN packet trying to establish a connection. This is coming, so it shows us the source address is 10.10, that's our CentOS box. It's sending our destination address. It tells us it's 10.12 with port 8000, just like we would expect. And then on the response here, the packet from the Ubuntu box to the CentOS box coming from port 8000 to the random ephemeral port selected by CentOS, it's a reset packet. So this is Ubuntu telling the CentOS box, sorry, I'm not listening. And then the CentOS box tries again with another SYN. And it replies, sorry, I'm not listening. So basically, the Ubuntu box is not listening on port 8000, and it's telling that much to the CentOS box. So now let's do another example. Let's listen on port 8000. We don't need sudo for this. We're going to listen on port 8000 on our Ubuntu box. And we're going to put it in the background. And now we're going to start our TCP dump again. Now let's repeat it from the CentOS box. So we're going to do exactly the same thing. We're going to send hi over port 8000 to our Ubuntu box. Okay, we got some output here. I'm going to cancel my TCP dump. Now we have some more interesting information. From the CentOS box to our Ubuntu box, the same information, and it tried a SYN packet, just the same as above. And this time, the difference is the Ubuntu box was actually listening, and it replied with a SYN-ACK, saying, yes, I'm listening. And then finally, the CentOS box completed the three-way handshake, the three-way TCP handshake, and then the conversation happened. So this would be the packet where the word hi was being sent over the wire. And then finally, we have the teardown, the FIN packets being sent. So you can see a full TCP conversation happening with TCP dump, and this is very powerful. This really helps you to debug in detail exactly what's happening on the network, and it's one of the first tools that I turn to when I'm, even for something simple like trying to determine whether a system is seeing data or if it's blocked from the firewall. TCP dump is a great tool to use for that. You can perform all sorts of fancy filters. For instance, I could say port 8000 and not port 22 and not ICMP, so this will look for anything on port 8000 but not these other ports and no ICMP traffic. Or I could say not UDP 53, So this would filter out DNS traffic, which occurs on UDP protocol port 53. So you can apply lots of filters, and there's additional flags. So I can repeat the previous example. Let's see, I will listen with netcat again. NC-L 8000, I'll put that in the background. I have my TCP dump, the same exact TCP dump example, only this time I'll add 2 more flags, minus little n x, little n capital X. So it's the same thing, and I'll repeat my echo to netcat example. Now look at, we have a lot more information here on the right side. I'm going to cancel out of it. So most of this is kind of gibberish and it doesn't mean much to us, but importantly, we see our SYN, our SYN-ACK right here, and our ACK, and then the conversation happens. Here it is. We see our hi. So we can see the network traffic on the wire from the CentOS box to the Ubuntu box, and that can be useful to determine exactly what you're seeing on the network. You can capture this output into a format using the -W flag to TCP dump. You can write it to a file, and you can copy that file off disk and open it with Wireshark and view it through a graphical interface as well. So that was an overview of using troubleshooting Linux networks and setting up Linux networks. There are, of course, many advanced networking features out there. For instance, you can set up multiple network interfaces on a single Linux box and bond them together, known as channel bonding. This gives you improved redundancy. If one of your 2 network interfaces has some problem, say the network cable comes unplugged or the network adapter itself experiences a failure, which is very rare, but it happens, the second network interface will still be up and you won't lose a connection. That's an important aspect to having a high availability network. You could also use them to increase bandwidth. So if you bond 2 interfaces together, they have double or near double the bandwidth than a single network would have. You can use the Linux kernel to establish an IPsec virtual private network, a VPN. You can use Linux actually as a VPN server using either Strong Swan or Raccoon software. You can set it up as a full-featured router, just as nearly as powerful or just as powerful as, say, a high-end Cisco or Juniper router. You can set up an IP tables host-based firewall, which we'll see in the security lesson in some further detail. You can even set up your Linux server as a Wi-Fi hotspot. You might not need to go buy a Linksys server. If you have some system in your basement, you could just put on a wireless network card on it and turn it into a Wi-Fi hotspot. So these are all sorts of features available for networking on Linux for you. Welcome to Lesson 9, Security. In this lesson, I cover how to secure a newly installed Linux system. I cover common tasks like patching the system, identifying and closing unused ports, and reducing process privileges. I go over many of the features of the Secure Shell, a powerful daemon that can be used to access systems remotely and to transfer files. I also cover the use of IP tables, which is the Linux kernel's host-based firewall software. In Lesson 9.1, we'll learn how to secure a Linux system. We'll start by taking a pessimist's perspective on security, because that's really the best perspective to have when you're a security person, is to really be pessimistic about everything that somebody's trying to do on the network. Assume the worst, and in this way you'll be prepared for the worst. So the question to ask yourself is, how paranoid are you? Because when it comes to security, it's not if an attack happens, it's when it will happen, because any system attached to the network nearly always gets attacked. Certainly any system attached to a public network will come under close scrutiny and will be attempted for exploit by attackers. A few years ago, there's all sorts of statistics out there, of course, but you could attach a Windows 95 computer to a public network and it would be hacked by somebody with a bot network, for instance, within just a few minutes. 2 to 3 minutes it would be hacked and owned on the network. Linux statistics are a little better, mostly because they have a smaller footprint on the network, but they absolutely are just as vulnerable to attacks. So what are some of the most common attack vectors? Here's a few of them in no particular order, really. One is software bugs. This is probably the most common vector for attack. A software bug can come in a lot of forms. It could be a bug in web server software. It could be a bug in the kernel, the Linux kernel itself, and how it listens on the network. It could be a bug in your own software running on the web. So no matter what that interface is, software is malleable and buggy and is the most common vector for attack, various bugs in software. Social engineering is another source of attacks. So that means that somebody calls you up and convinces you to change the password for another user. If you were convinced, then you were the subject of a social engineering attack. Another example is somebody trying to get into a secure area. They follow somebody who has credentials, who has their key card and lets themselves in, and they do what's called tailgating. They just follow right behind them through the door that was already open. That could be also considered a social engineering attack, and that's a very common way that systems end up getting hacked. It could be through compromised credentials. That might mean a number of things. It might mean that somebody guessed your password, so they're trying to log in to, say, your Google Mail or your Yahoo Mail account, and they knew your username because they knew your email address, so they just had to guess your password. And once they guessed it, they've brute forced your password and your credentials have been compromised. Or in the example of SSH, if you have a public-private key pair, if your private key is stolen, then your credentials there are also compromised. That's a very common attack vector. It could be physical theft. You could be, on an airplane and you have your laptop in the bag and your bag gets stolen. At that point, you can consider any data and possibly any credentials that were available on your laptop are stolen, and that's now compromised. That's a source of attack. Could be in a business context, it could be a malicious insider, somebody that has been given access, trusted access to the information, but does something nefarious with it, uses that information in a way that was not expected or anticipated. That can be considered an attack vector. It could also be some third party, some outside party who has nefarious intentions. For instance, you might consider the NSA, the federal government, to actually be an attacker because they've compromised the fundamental security of the internet. So you might need to protect against your own government in some cases. So there's a lot of things, fortunately, that you can do to improve your security. They say that in Linux or in systems in general, there's nothing that you can do to fully secure your system if it's on a network. In order for a system to be secure, it needs to be put in a metal cage to prevent electronic interference and not connected to any network. Clearly, a computer not connected to a network is not very useful, so instead we have to do some things to secure it. So here's a few of those things, and we'll demonstrate them as well. You should install patches first and foremost. The first thing I do when I attach a new Linux system to the network, or in some cases before I attach it to the network, is install patches on it. Patches fix security bugs in software. So there's been some time that goes on between the time the operating system is installed on your Linux server and the time that your Linux server is attached to the network. Maybe this is a month, maybe it's a few days, whatever it is. Some bugs have likely been discovered, and some of them may be about security. And so by patching, you go out to the internet and you download the newest versions of software and install it, and you're no longer vulnerable to those security bugs that have been found. You should also disable any unused services. So these are things that might be listening on the network on your system. By default, you install a new Linux system, it's listening on several ports. You might not be using, say, the print service that is listening on a port, so you should disable that. It reduces your footprint on the network. You should remove any unused software or any other users. In general, a minimum system is the more secure system. So if you have user accounts on the system that aren't being accessed, if nobody's using them, they should be removed. You can take a few steps to secure your TCP/IP stack. For instance, we learned about the IP forward flag. If your system doesn't need to forward TCP packets or IP packets, it should disable that feature. You can tune OpenSSH. OpenSSH is enabled by default on most Linux systems and is really a common thing for system administrators to need, but it can be tuned for better security. Obviously, you'll want to back up your system and send some logs off to a remote system. Those are a few steps we've already learned about. You should use sudo in all cases because it gives you auditability, an audit trail about who ran which command. You should also configure IP tables, which we'll learn about in some detail, to have host-based firewall to permit access to services for trusted hosts and prevent access to those services from untrusted hosts. So let's dive into some examples of securing a Linux box. So I'm logged in now to a fresh CentOS box, a new virtual machine that we haven't been using for examples so far. Like I said, the first thing that I like to do is to patch the system. And so to do that, we use the yum command. We learned about yum as the tool that we use to install new software on the system. That's how we also update software. So I can type sudo yum update. And what it does is it goes out to the internet and finds out from the Yum repositories what software is available. And we can see here that there's a whole lot of software. We have a new kernel out there, there's a new bash package available. So we don't know which one of these were security updates. If we wanted to, we could investigate in detail and figure out which of these were for security and which of them are bug fixes. But in general, it makes sense to update your software on a pretty regular basis. So we're going to go ahead and just say yes, install all of these. So now Linux and Yum are going out to the software repository, they're getting the package details, and they're going to install them all on this system. This is a pretty easy way to patch a Linux system, but you can imagine if you have hundreds or thousands of machines, this can be a little trickier. The other thing that's concerning or troubling about patching software is that this might be a live in-production system. It might be serving web traffic or database traffic, whatever it's doing, whatever its job is. If you update the software, it might introduce some new bug. And this is pretty common, actually, where it's up and running and live and everybody's happy, and you run a patch, and suddenly it stops working. So you often, in a large organization, you'll time patches. You'll do it for a period of low downtime, or you might even need to reboot the system if you need a new kernel install, such as in this patch. In that case, the system needs to be rebooted in order for the new kernel to start to be used. So you have to plan for system downtime, and organizations often have very careful scheduling around this sort of thing. So our patching is still running at this point. It's downloaded all the new packages from the repository, and it's installing the new versions. We can see at the moment it's installing the kernel, 2.6.32. So it's still just kind of going through its patching process. Now it's cleaning up old packages. It's kind of finishing things up. And after this, the system will be fully patched. So we can assume that any security updates that it needed have been installed. Now, of course, this doesn't mean that there won't be additional updates in the future. So you really need to plan to update your system on some regular basis. There are actually compliance objectives. For instance, PCI, the PCI security standard says that you need to install critical patches, that is, patches of critical security flaws within 30 days of them being announced. So this is something you need to get in the regular habit of doing. It's one of the things that will keep your system the most secure. Now we've finished with patching. All of the packages have been updated. It says it's complete, so we can assume that patching is done. So one question you should ask yourself, of course, is how can I trust this repository? How do I know that the software repository upstream, where on the internet, where my server went to get all of the packages from, how do I know that that repository has not been compromised? And absolutely, that is a valid question. In the past, a number of distributions have actually had compromises of their software repositories. This happened to Debian, for instance, a few years ago. So it's a valid question, and you just have to decide how paranoid are you. If you don't want to trust all of those sources, you can set up your own repository and hopefully trust your own repository. Most of us don't take that step. In a highly secure environment, you might need to, however. So the next thing we can check out is to remove unused software. So I use the rpm-qa command. So what this does is query all of the available packages on the system. So this is all the software on the system and their versions. If I pipe this output to wc-l, this is giving me a line count. wc-l does a line count. So we take all of this output and we give it as input to word count. And so it's telling me there are 276 packages installed on this system, which is really not a huge number. This is sort of a minimal system. But I bet if we look hard, we can still find some things we don't need. For instance, one risky thing on a server is to have a compiler. This is something that's just common sense to remove. On a production system that doesn't need to compile software, you can often get away with not having a compiler because an attacker could upload source code and compile it locally and not need to go out to the internet to download any of his hacking tools. So in order to remove it, I like to use sudo yum erase, and then I'll give it the package name. This is the C++ compiler on the system, gcc-c++. And it asks me, am I sure I want to remove it? And I say yes. So now I've reduced the footprint on my system a little bit. I have less software. That's less of a footprint for an attacker to use for nefarious purposes. Another thing to check out is installed kernel modules. So I can type sudo lsmod, and it shows me all of the kernel modules on the system. I might not need all of these modules. In fact, I almost certainly don't. For instance, I've got a few of them highlighted here. These are parallel port drivers. So if you have a printer and you have some old system with a parallel port attached to it, you would print over the parallel port. I almost certainly don't need a parallel port. Unless you're a Linux print server with a parallel printer, you won't need it either. So we can turn those off. And the way I do that is in the etc modprobe.d blacklist.conf. This is where I can blacklist any drivers I don't want to use. So I've just used Shift-G in VI to get to the end of the file, and I'm going to blacklist those drivers that I saw. That was parport and ppdev, and I'll copy and paste, and I'll change this word to parport PC. So here's the 3 drivers I had highlighted. And so the next time this system boots up, these 3 won't be loaded. If I wanted to remove them without rebooting, I could say rmmod ppdev, and I could say parport PC. I could just do the same thing I did in the blacklist.conf. And now if I do sudo lsmod, I don't see them in any of this output anymore. They've been removed, and we know that since we put them in the blacklist.conf, they won't come back after reboot. So just another way to reduce the footprint of the server. We can also remove unnecessary users on the system. So if I look at the etc passwd file, there's a whole lot of users in here. I don't really know what they all do. I know that I don't need some of them. Like I don't really need the games user or the gopher user. I might not need, for instance, the shutdown user. So I could say sudo userdel gopher and sudo userdel games. And so we're just reducing the number of available users. Now, this isn't adding a ton of security. These are little things. The games user and the gopher user we can see here, they had a shell of no login. So you couldn't even use those user accounts anyway, and they didn't have a password set. But we're just talking about reducing the system to the bare essentials in order to operate. So another really important step is to reduce the number of services the system is using. If I use our favorite netstat command, -tnlp, and I'll use sudo for this, we can see that this system is listening on SSH, it's listening on port 111 and port 51337. We can see what service these are listening on the right side here. We have RPC bind, we know that port 22 is SSH. We probably don't need all of these ports open. So what I like to do is to just turn off anything I know I'm not going to need. I do know that I'm going to need SSH, so I'm going to leave that one running. But I'll go ahead and look at PS output, and I'll search for 1076, and I can see here's the RPC bind service. Services are started and stopped, as we learned, under etc init.d. And if I list this, there's a whole bunch of output, one of which is RPC bind. So I can say sudo service RPC bind stop, and that will stop that service. And now if I look at my netstat output again, I don't see RPC bind in the output anymore. So this is stopping it for this session, but I really need it to be off permanently. After a reboot, say I patched my system and I rebooted, right now that service will come back on. I want it to be turned off permanently, and so in order to do that I use the check config, chk config, and I say RPC bind off. Now I know it's not going to come back up, and I can investigate it by check config --list RPC bind. We can see it's off at every run level. Think back to when we learned about run levels. Those are different stages of the system boot process. Right now they're all turned off. So we know this isn't going to come back after a reboot. Now some of this is just some knowledge you gain over time. For instance, I know that the rpc.statd service, this is another listening port on 51337. This is the NFS lock service. So I'm going to also say service NFS lock stop. And I might also say service check config NFS lock off, so it doesn't come back after a reboot. Now let's look at our netstat output. I used my reverse search. I used Control-R and typed in net, and it brought up my last netstat command. Now we see I only have SSH listening. So at this point, we've significantly reduced our network footprint. You have to think about any listening port is sort of like, imagine a house, and the house has windows and doors, and when your house is getting attacked, an attacker could pick any of those windows and doors to come through. Any one of them is a vulnerability or a weakness. And the same thing is true of ports. So we want to reduce the number of available ports, so just to reduce the footprint that an attacker has to try to compromise. So we've turned off a bunch of services, we've removed some unnecessary software, we've removed some kernel modules we didn't need and some users, and most importantly, we've patched our system. At this point, we've taken some steps to improve our security posture. If you needed to learn more, and you almost certainly do, to properly secure your system, here's a few different resources you can turn to. The Red Hat Enterprise Linux Security Guide, you can Google that, or you can look at the link I've posted. Ubuntu has some really nice security steps as well. All the security steps are similar but slightly different between distributions, so you'll want to take the steps appropriate for your distribution of choice. And to keep up on current Linux security trends or to communicate with other Linux users on forums, use linuxsecurity.com as a great resource. Welcome to Sublesson 9.2, where we'll use SSH for secure remote management of our Linux systems. SSH, also known as the Secure Shell, is a cryptographic network protocol for secure network services. It is, I like to think of it as the administrator's Swiss Army knife. It's a really nice tool that you can use for securely accessing and performing functions on remote systems over the network. And it does a lot more than just logging you into a remote server. That's a really common use for it, is to log into a remote system and execute commands over that system. We've been demonstrating all that throughout this live lesson series. As we've been going by using Vagrant SSH, we're logging in over SSH to our systems, but it does more. It can do file transfer. For instance, I can use the SCP or SFTP commands to copy files from my local system to some remote system over the network. It also does port forwarding. This is a little bit of a complex concept to just explain, but if there's a port available to a remote system, a network port, that is not available to my local system, I can use SSH, an SSH tunnel. Basically, I can establish a tunnel to the remote system, and then I can, over SSH, access that remote port. So it gives me secure access to network services that I otherwise wouldn't have available. You can use the SOCKS protocol feature of SSH to web browse through an encrypted connection. So if I had an SSH server somewhere out there on the internet, I could use it as a proxy, and I could establish a SOCKS tunnel to my remote server, and I could browse the web securely, and it would look to remote web servers as if my connection was coming from the proxy server instead. So that can be really useful if you don't want anybody spying on your network traffic, for instance, or to help you get to web resources that you might not otherwise have access to. You can also use it as a secure remote file system through the SSH-FS file system protocol. So this will mount a remote system's file system over SSH to your local system. So I could start writing files to a remote server, and it looks to my server as if it's local. So those are a few of the features. Let's show how to configure and use SSH on the command line. So now I'm back at our network where we have a CentOS box on the left and an Ubuntu box on the right. So I'm going to log in from the Ubuntu box to the CentOS box. First things first, I'm just going to change my password on the CentOS box so I know what my own user account password is. Okay, my password is set, and now I'll SSH to bwhaley. I need to specify my username. By default, it's going to use the username Vagrant, and I don't want to use the username Vagrant. So in order to do that, I can say bwhaley @ or alternatively, I can do -lbwhaley. Use the bwhaley username to log into 192.168.10.10. That's my CentOS box. It says, what's your password? I can say my password, and now I'm logged in from the Ubuntu box to the other box. If I type W or who, I can see Vagrant users logged in from 10.0.2.2. That's this window, logged in from my laptop. And I can also see bwhaley logged in from 10.12. So that's the one I'm logged into right now. So that's a really simple example of using SSH. Now, that was using a password. I set my password on the CentOS box, and then I typed it in when I logged in here. So this is one way to do access control, but there's other ways that you might need to do access control. Let's check that out now. So I'm going to log back in out of the CentOS box back to my Ubuntu box, so I close the SSH connection. And now I'm going to generate a public-private key pair and use that to log into the system rather than a password. This can be a more secure way to access the system. So first on the left side, I'm going to become using sudo su minus, I'm going to become the bwhaley user. I'm going to make sure I don't have any keys in there already, which I didn't, so that's fine. And now I'm going to generate a new key pair on this side. I'm going to make sure I don't have any key pairs on here as well. Great. So we can use the SSH minus keygen, and then we specify an algorithm we want to use. Now, there is recently, due to events on the internet, some of these algorithms have been called into question. I can't say which of them are secure and which are not secure anymore. I'm going to go ahead and use the RSA algorithm, and I'm going to specify a 4096-bit key, which is probably more than enough, but it's the standard I like to use now. So it's generating a random cryptographic key pair. It's asking me what file would I like to save it to. I'm going to go ahead and say that. Now here it's asking me whether I want to use a passphrase or not, and this part's important. You can set up a key pair to not have a passphrase. This can be useful if, for instance, you have two different systems on the network and they need to do something automatically where there's not going to be a human there to type in the password. For instance, maybe there's a script that runs out of cron and it copies a backup file from one system to another. You wouldn't want to have a passphrase because there would be nobody to type it in. But for human use, anytime you're generating a key pair for your own use, you'll want to have a passphrase just for additional protection. I'm going to leave this one blank for now. So I'm not typing any passphrase. It's generated a key pair for me. Those are stored by default in my home directory, /.ssh. If we cat out our private key, if we print it to the screen, we can see kind of what it looks like. It's just a lot of cryptographic key garbled nonsense. It's not very readable to us. You'll notice that the size varies according to the bit length that you use when you use SSH keygen. We specified a 4096-bit length key pair. If you use 1024 or 2048, I would never recommend 1024, by the way. This will be shorter. In any case, we can actually use this if we say SSH minus I, ID RSA, minus L. We still need to specify our user account, which is bwhaley. And 192.168.10.10 is our CentOS box. And notice that it logs us right in. Welcome to the Linux System Administration Live Lesson image. This is our CentOS box running over here. We didn't have to type in a passphrase or a password because we generated a passphraseless key pair, which, as we just discussed, is useful for automatic scripts, but is a little bit risky because if somebody compromised your key, then they could use your account without a password. So that's what it takes to use a public-private key pair. Getting the permissions exactly right can be a little tricky the first few times you do it. One thing to help you debug, if I revisit my same command, so this is the same command I used to log into the CentOS box from Ubuntu, I can add the -v, little v flag, and it spits out a whole bunch of information to me about what that key exchange. Sometimes this can help you. It'll tell you if the permissions are wrong or if there's some other problem with your key pair. Let's show another example of using SSH. So I have some file, echo hi, I'll output this. So I've got this file called file with the contents hi on my Ubuntu box. I can use the scp command to copy that file, and the syntax is source. The source in this case is file, and I can copy it to the CentOS box, 192.168.10.10, and I can put it in some different file, say /temp/ some other file. Oops, so I don't want to use the Vagrant user. This is what, well, it uses Vagrant by default. I need to use bwhaley, so I say bwhaley at, and it just copied it over there because the key pair is set up. So it copied a file from my local box, so now if I go into the /temp folder on my CentOS system, I can cat some other file, which I just transferred, and we see hi, so that was how I can use SCP to transfer files. Similarly, I can use SFTP to create an interactive file transfer session. So I could say bwhaley at 192.168.10.10. Now it's connected me to the remote CentOS system. I'm in my home directory by default. I can use shell commands to get around. So now I'm in the /temp directory. I can ls/home. I can get a file. Say I go to Etsy, I can get Red Hat-release. This is just like a release file that tells me what version of Red Hat I'm running. This wouldn't be present on an Ubuntu system, of course, since it's not Red Hat. Now that I've gotten it, I have it here in the directory that I was in. and it tells me it's a CentOS 6.4 box. If I go back to my CentOS system on the left and cat that file out, it's the same file. So this shows you how to transfer files around using SCP and SFTP. So I want to demonstrate one final example of SSH port forwarding that allows us to connect from a system to another system and access network services that otherwise would not be available. To demonstrate this, on the CentOS box, I have the Apache web server running. And it's listening, and we can see this with our netstat output. We can see that port 80 is listening, and it's the HTTPD service. So if we use the curl tool, we can see the HTML output. This would be rendered really nicely in a browser, but curl is a nice command line way to access servers. I can still use ping to talk to my CentOS system, so that network is still up. And if I try that same curl command from my Ubuntu system here on the right, 192.168.10.10, I can't access it. So let's use port forwarding to establish that connection. So the first thing I'm going to do is I'm going to bring up yet a third window in my terminal here. And I'm going to go to my work directory, and I will SSH to my Ubuntu box. I need two windows to demonstrate this. So on my top Ubuntu window here, I'm going to set up the port forward. So I'm going to port forward my localhost port 8000 to the remote host's port 80, and I need to then log in to the host. I need to specify my username as well. Okay, so now I logged in from my Ubuntu box to the remote CentOS system, and I'm doing some port forwarding. And so let's look at that on our bottom window here. If I look at my netstat output here, I show that here's port 8000 listening. This wasn't listening before, and it says that SSH is using it. All right, that's what we're seeing here. So port 8000 on my local system is mapped to port 80 on the CentOS box. And now if I curl my localhost port 8000, I see the same HTML output. So this allowed me to map my local host's port 8000 to the remote host's port 80. And this can be a really useful feature for accessing remote systems that might be behind a firewall, for example. So let's take a quick look at the SSH configuration on my CentOS box on the left side. If I cd to /etc/ssh, there's a few files in here. We see the SSH server's public key fingerprint. We see some other information. SSH_config is the client configuration, and SSHD_config is the server configuration. If I look at this file, SSHD_config, I got permission denied. I need to use sudo for that, sudo bang bang. Here's all the server config, and the nice thing about this config file is it's very verbose. It shows us there's a lot of commented out sections. So we can see, for instance, it's listening on port 22. If you see a hash mark in front of a configuration item, like any of these lines I have highlighted here, that indicates that that's the default. So you could uncomment it and change it to, say, port 25, which is very non-standard. But by default, it's going to be port 22. It's only allowing version 2 of the SSH protocol. Version 1 is insecure, and you should use version 2. And there's all sorts of other configurations. Here's a couple important ones to point out. One is this line here, permit root login yes. This is commented out. By default, it's permit root login is no, and you should leave it at no. We don't want to allow root to log in. We have password authentication set to yes. Often you'll see password authentication set to no, which means only allow public-private key pair authentication, which we demonstrated just a minute ago. Often cloud systems, like for instance Amazon's web servers, will not allow password authentication. They'll only allow public-private key pairs. It's a more secure setting. And there's all sorts of other configuration you can add here. In general, just like securing any Linux system, you should disable anything you don't need. For instance, I might disable X11 forwarding. X11 forwarding no, because I just don't need it. If you need to make a change, you have to restart your SSH server. But here's a catch. If you make a change and you've made a configuration mistake and you try to restart SSH, you may lock yourself out of the remote system, because SSH will try to read its config and restart, and the config will fail. So just be really careful about how you handle that. So that's the basics on configuring SSH on a Linux system. In this sub-lesson, we'll talk about IP tables, which is the Linux kernel's firewall. IP tables is a stateful packet filtering firewall. What this means is that the IP table software is aware of connection state. For instance, it can distinguish between a brand new connection and a connection that has already existed. In fact, it's aware of that for every connection across the system. It can have a performance impact if you get to too many connections, but it's really a powerful feature because I can allow certain connections or disallow other connections. It's a full-featured packet filtering firewall. It's implemented directly in the kernel through its netfilter suite of system calls and hooks. And netfilter was introduced in the Linux kernel version 2.2, given that the kernel is now at version 3.11, I believe. It's quite a mature product. So there's several concepts we need to master in order to understand IP tables firewalls: rules, chains, and tables. So rules search for specific criteria on incoming or outgoing packets, or just network packets in general, and then apply some predefined action against a target. So let's just hold that thought for a minute. A collection of rules are applied to chains, which determine when packets are examined. And then finally, there are different tables that say which targets are valid and which chains exist. This might be clarified by looking at a graphic. So let's look at this example of a host with two network interfaces, or maybe just even one, but in this example, let's say there are two. So we have inbound traffic to a given interface. This would be for the NAT table, which is one of the tables available under IP tables. We have several different chains. The pre-routing chain is what takes action when a packet is first received and before the kernel has determined what to do with that packet. We have two choices then. If the packet is not destined for the local system, then it goes on to the forward chain. So if you can recall, we configured IP forward to yes or no when we were looking at the /proc file system. If IP forward was no, the forward chain wouldn't be valid. But if it's yes, then we can forward packets along and it might hit the forward chain. Alternatively, it could go down the input path, meaning that this packet is destined for this system and it should go look at the input chain. On the bottom of the diagram here, we show the output chain and the post-routing chain. So they're just like what they sound like. Output is for packets leaving the system. So it searches that rules in that chain match against outgoing packets. So my system is initiating a connection outbound to some other system. And post-routing is after all of the routing rules have been applied, just before the packet goes on the wire onto the network, that applies some rules. So let's look at a few existing targets. Some of these are pretty self-explanatory for the most part. First of all, accept. This means accept that matched packet, allow it through the system, so the firewall is not blocking it. Drop means we'll drop the matched packet, don't allow it through the system. Reject is very much like drop, but rather than just dropping it and not saying anything, it drops the packet and it tells the system that made the request, sorry, I'm dropping this, it's not allowed. There's also a couple more rules. The log target, the kernel will log that this particular packet matched, so this can be useful, for instance, to see if somebody's trying to hack your system. You could log hack attempts. And finally, redirect says to send this packet on to another host. So let's see some examples on the command line. I'm logged into my CentOS system, and I can type sudo lsmod, and I can pipe it to grep for table. Oops, I need to not have typos. So we can see the module is loaded. So it's implemented as a kernel module, and you can see that that it's currently loaded, so it should be available to us. One way on CentOS to examine the firewall, the current firewall, is sudo service IP tables status. So let's go through this. So we're looking here at the filter table. This is the table that filters inbound and outbound packets. It's a very common table to apply rules to. Let's look through the rules kind of one at a time. First of all, we see that all packets are accepted from all sources to all destinations if they're in the state related or established. So this is saying that if the connection already exists, just go ahead and allow it. We don't need to do any further analysis of it. It's already been established anyway. So we're distinguishing here between new connections, which would be like I have a web server listening and somebody wants a new request. That would be a new connection, versus related or existing connections. Here we're saying this next line, line 2, chain rule number 2, is for ICMP packets specifically. Look at the column header here, it says proto for protocol. ICMP packets specifically. So this is basically, it's allowing pings or any other ICMP traffic on all interfaces from all sources to all destinations. This line we're going to come back to in a moment. It looks like it says all protocols allow from all sources to all destination. It looks like it's wide open, but this is misleading, and it has to do with the fact that we're just missing some output here. In fact, let's just go ahead and show that now. If we show IP tables minus V minus L, so this output is showing minus L without the minus V. Minus V shows us verbose information, and we can really see, if we look at the same rule, this rule, we can see an interface. So it's showing us that it's applied to the loopback interface only. So that means it's allowing all traffic to and from, but only on the loopback interface, which is the local system. It's not very risky to do that. The next line we're looking at, this is saying accept these packets. This is the TCP protocol. No interface is specified, so it's for all interfaces. It's from anywhere to anywhere, and these are for new connections, and it's for SSH. Destination port is what this DPT stands for, SSH. So this is saying allow new connections to port SSH. It's allowing inbound SSH connections. This is why from the Ubuntu system to the CentOS system, we're allowed to establish SSH. And finally, at the end, we're rejecting everything else. We're saying reject with ICMP error message, don't allow anything else, and tell them that they're not allowed. So this is on inbound, incoming packets to our system. On forward, we're rejecting everything. This is the forward chain. Don't allow any packets to be forwarded at all, and we don't have any rules at all on our output chain. So that's kind of what a default firewall might look like. Let's see if we can change this at all. We might want to, say, add a new rule. We could cd, the rules are configured and saved in etc sysconfig IP tables. I need to use sudo to look at this. So if we look at this, we can compare this configuration file to our output in the command above, and it should all match. So we're saying here, allow or accept establish and related connections, or allow all ICMP protocol packets, which we talked about, or allow everything for the loopback interface only. Here's the rule that allows for destination port 22. Now you remember that we did a port forward example using SSH, where we allowed the Ubuntu host to connect to the CentOS host by using SSH port forward on port 8000. What if we just wanted to allow the Ubuntu host to talk directly to the CentOS host on port 80? We could add an IP tables rule for that. So what I like to do is edit this configuration file, IP tables, and we'll try to copy an example of a rule that's already in place. So this rule looks like a good one because all we need to do is change port 22 to port 80. SSH is on port 22, web traffic is on port 80. So I'll copy and paste this line, and I'm just kind of going through all of this. I want to allow new connections on port 80. And now I can say sudo service IP tables restart. This will reload the IP tables configuration. Now if I do sudo IP tables minus L, now you can see that port 80 is allowed. HTTP has been added. So new connections. At this point, a connection from Ubuntu to CentOS on port 80 would work, would be successful. Now sometimes you just want to disable the firewall. You don't want to have a local firewall running. Sudo service IP tables stop will disable it, and sudo check config IP tables off will turn it off permanently. Now this is risky. At this point, the system doesn't have any firewall in place, so any remote system could connect to any port that this host is listening on. It's really a good idea to have a firewall running if you can. That's the basics of covering IP tables on a Linux system to configure a host-based firewall. Thank you for watching this live lesson video on Linux system administration. I hope you found these lessons informative and beneficial. Now that you've learned all these topics, what's next? Now it's time to run some Linux systems. You can set up your own home network using Linux servers. Set up a bind DNS server, Linux DHCP server, and a Linux router and firewall to manage the network infrastructure in your home. If your business or organization uses Linux, get an account on the system and poke around to see what it's doing, with your local administrator's approval, of course. Or start exploring web technology by building a Linux system on Amazon Web Services, Rackspace, or another cloud infrastructure vendor. Remember that the system administration discipline is radically dynamic. The most successful administrators are always learning. That's all there is to this live lesson series. If you've learned from these videos or have feedback to share, keep up with me on Twitter @IamTheWhaley. Thank you and happy administration.